for everyone showing up. We should do this more often. I think it's a wonderful opportunity to get audio devs and those interested in audio dev development. Now I'll use the mic. Whoa, it makes me sound so much larger. Yeah, what a wonderful opportunity to get people together. So this was an experiment to do a one-day pop-up for ADC, ADC being the Audio Developer Conference that normally happens in London in the November timeframe. The idea was to do one-day pop-ups in different cities across the world. This was our first kind of try at it. You'll see that there'll be other pop-ups announced soon. We hope to come back and make this a regular thing in the Bay Area. But I'd also would love to chat with folks during the breaks and networking times to see if we can come up with ideas for doing just get-togethers, meetups with other technical groups that are involved in AV in the Bay Area. I think we need more opportunities to just get together. I look around the room, a lot of familiar faces, a lot of people I don't know. I look forward to meeting everyone, and I just love when people get together and share great ideas, and yeah, this is where the magic happens. So thank you to all the speakers that, I mean, proposed amazing topics. It was a shame to have to deny probably 2/3 of them, but it was clear that there are people who want to talk and share and just share their great ideas. So thank you. Make sure you take full advantage of the networking times. There is networking breaks in between each of the 4 and 5 talks. And then we'll end the day on the rooftop with a lovely little reception and some live music, and hopefully the fog will clear. We shall see. So thanks, everyone. Have a great time. Also, I want to point out the JUCE team is here. So I should have mentioned that. The entire JUCE team is here, -1, because someone had left, mostly in the front row. Ali is back, but we'll say Ali. Hi, Ali, if he can hear us. Please meet the JUCE team. If you don't know what JUCE is, I hope you'll find out by the end of the day. It's a wonderful opportunity to speak with everyone that is typically out in the UK, not here in the States. So it is a really great opportunity. Okay, with that, have a great time.
All right, good morning, everyone. Welcome to ADCx. I am so psyched to kick things off, and I get to be the first, so super excited. I'm here today to talk to you about smart algorithms. And we're going to hear a bunch of talks today that are going to focus on various machine learning techniques and detailed presentations on specific topics. And I want to give more of a general overview. And for the purpose of this talk, I'm going to define smart algorithms as algorithms that resolve ambiguities. Customers increasingly expect our products and applications to magically just work and infer what the user wants to do and what they intend to do. And when we resolve ambiguities for them and do something sensible in the face of ambiguities, that's when our applications and products feel smart. And so while it would be pretty silly to assert that, for example, a wake word detection algorithm or a tempo estimation algorithm possesses some sort of intelligence, when these kinds of algorithms resolve ambiguities, our applications feel smart, and that's what we care about, and that's why I'm calling them smart in quotes today. So machine learning has given us a wonderful set of tools for creating new smart algorithms that we never were able to create before. Often, though, I also see developers turning to models that are large and hard to deploy when that's not necessarily the best solution. So in this talk, I hope to give you some basic principles and guidelines for figuring out how to approach a smart algorithm design, and also where it makes sense to leverage machine learning techniques and where it makes sense to leverage more traditional DSP. So I'm going to start by talking about domain knowledge, because the types of domain knowledge that are available to us strongly inform our approach to a smart algorithm design. A smart algorithm is going to have to extract some salient features from input data that are salient and relevant to the result we are trying to compute. And if we have a priori knowledge of our domain, then an engineer can design salient feature extraction because they know what makes features salient to the result. In contrast, a machine learning model has to learn from a posteriori knowledge, namely a data set of examples, to extract salient features from the input data. And when it comes to audio applications, we often have a lot of a priori knowledge at our disposal. For example, we know how the human vocal tract works, so we can do things like extract mellow frequency substrum coefficients. We know a lot about how human perception of audio works. We know how to create critically sampled filter banks and why those are efficient, and so on and so forth. And so if you're using MFCCs or even an FFT or constant Q transform in your algorithm, you're already leveraging a priori knowledge. So domain knowledge informs what we can do with machine learning or with traditional DSP. And application constraints and priorities are going to inform what's actually practical for us to do. Those constraints and priorities might include things like execution speed, memory use, and power consumption of the deployment platform for our algorithms, but also things like effort, schedule, and skill sets of our team for algorithm development and for algorithm deployment. So in the next few slides, I'll briefly go through some side-by-side comparisons of machine learning and more traditional human-engineered DSP algorithms. This is fairly basic stuff. I'm sure many of you know all of this. I'm just going to make some broad generalizations and provide a bit of context to see how these considerations play out. So I'm going to start by talking about data sets. I'm sure no one here is going to be surprised that for machine learning, we need much larger data sets than for human-engineered DSP solutions. And again, making a very broad generalization, for machine learning, we need hundreds to millions of examples. And for a human-engineered DSP solution, we might need dozens to hundreds of examples. Also, for machine learning, we really need to annotate and very carefully curate our data set so that our models learn what we want them to learn and not some unintended artifact of our training data. For traditional DSP, we also need to annotate and curate our data set, but really that's only for quantitatively measuring the efficacy of our algorithm, so we can generally be much more lax and spend much less effort. Working in both audio and machine vision domains, I've worked on projects where machine learning required multi-person-year efforts to design, create, and curate a data set. And I've also worked on projects where a pre-existing data set was readily available or data could be synthesized, and so there was very little effort involved at all. Regarding compute and memory requirements, machine learning models typically require more compute resources. So machine learning models are universal approximators. They need to be able to learn any function from the input examples of the training set, and therefore they need the capacity to represent any function. In contrast, a human-engineered DSP solution implements one specific bespoke function, and therefore it bakes a priori knowledge and simplifying assumptions into the very structure of the code we write to implement that function. So intuitively, you can imagine that any portion that we can implement with DSP can theoretically be more efficient than implementing the same portion of our solution with machine learning. Deploying machine learning models is very different from deploying a human-engineered algorithm. With machine learning, we're going to use a framework like TensorFlow Lite or an API like CoreML. And if we're deploying cross-platform, then we might have to deal with multiple APIs, or we may need to integrate our machine learning framework multiple times for different deployment platforms. And so the effort to deploy can be quite large. We also may need to consider the storage for our machine learning model and whether it's small enough to bundle into an application or whether it needs to be downloaded or run in the cloud and so on. For a human-engineered DSP algorithm, we're going to generally deploy a bespoke code module. And depending on the complexity of the algorithm and how it was developed, that could require months of porting and optimization, although more often, recently, I've been finding that I can leverage some existing optimized function libraries and often just recompile my algorithm into an application, and it just works. So now I want to show you how I think through an algorithm design problem. I want to teach you the one neat trick that I think really captures how we resolve ambiguities, and therefore it's the one technique that makes smart algorithms smart. So I like to summarize this technique as score many candidate results. What we want in order to resolve ambiguities is for our algorithm to capture every reasonable result that we might need to return. Then we want to quantitatively score how well each of these candidates solves the problem we're trying to solve. And once we have those scores, we can either return the best scoring candidates, multiple good enough candidates, some sort of weighted average, or some other aggregation based on the needs of our application. We're going to propose and score results by extracting many salient features from the input data. So let's look at a simple example of how this might work. Imagine a polyphonic note detector. So this algorithm, let's see if I can get my pointer here. It's going to analyze a short time window of audio at the bottom of the diagram. And it's going to attempt to determine what musical notes are present in this audio. So we can imagine that doing a very brute force proposal of candidates, we have every semitone within some range of octaves. We're going to extract salient features using an FFT, and we're just going to pick out the peaks from the FFT magnitude. So now we have our candidate results. We have our features. We're going to score each candidate note by iterating over all of the spectral peaks and aggregating a confidence measure for the presence of the note in the signal. I'd like to point out that machine learning models are also going to score many candidate results. A machine learning-based note detector could have the very same set of candidate notes. It will just learn to score those candidates by training from a bunch of examples. Next, I want to get into detail about how we score the candidate results. We're going to score by feature relevance, feature intensity, and feature agreement. By feature relevance, I mean how meaningful or salient is the feature to the specific candidate. So for example, we're going to look at a spectral peak, and we're going to see if it's close to an integer multiple of the fundamental frequency of a note. And if it is, then it's probably a component of that note, and it increases our confidence in that note a little bit. By feature intensity, we mean how strongly do we measure the feature in the signal. So for example, we might look at peak magnitude, maybe peak magnitude relative to some estimate of noise floor, maybe a perceptually weighted version of that magnitude. By feature agreement, I mean the combined effect of many features. So for example, if many spectral peaks are near perfect integer harmonics of some fundamental, then that fundamental is very likely to be a musical note that's present in the signal. We can imagine many types of scoring functions that score by relevance, intensity, and agreement. For example, if we think about these things in terms of probability, we end up with Bayesian inference. But I want to highlight a particular type of scoring function that I find to be extremely useful, and it's essentially a dot product of the relevance and intensity. So for each candidate, we're going to compute a score by computing a sum over all the features of the relevance of a feature given the candidate times the intensity of the feature. It's often useful to threshold the result of the dot product to throw away weak candidates, and it's also often useful to clip the result of the dot product in order to avoid a particularly strong candidate from overwhelming a result. So now that we've gone through this function for scoring, I want to point out that, again, it's very similar to what neural networks do. A neural network computes a dot product of model weights and inputs. Each neuron, in fact, in a neural network computes a dot product of model weights and inputs, and that dot product goes through a nonlinear activation function, which essentially thresholds and clips the result for us. So this is not an accident. This is how ambiguities get resolved. For more complex problems, we want to build hierarchy. By building hierarchy, I mean that we want to think of feature extraction as its own smart algorithm. So let's look at a quick example. Let's imagine a chord classifier. So again, we're going to have a short time window of audio here at the bottom. And we're going to analyze that, and we're going to attempt to figure out what musical chord is present in that audio. So at the very top, in the green boxes, if I can get my pointer back. Here we go. At the very top, in the green boxes, we have chord proposals. And we know a priori that musical notes are salient features of chords, and we know how that works for music theory. So if only we had a polyphonic note detector, then we could propose a bunch of chords, and we could score each candidate chord from note features by note relevance, note intensity, and note agreement. And so you can see that we've built our chord classifier on top of our polyphonic note detector algorithm. Neural networks so for more complex problems, we need even more layers, and this is where neural networks really shine. Neural networks learn many layers simultaneously. It's very difficult for a human engineer or a team of human engineers to design many layers at once and converge on a good solution. So I believe that neural networks are so powerful and solve previously unsolvable problems, specifically because they learn many layers at once. So, wrapping all of this up, how do we approach a smart algorithm design? We think about our design in terms of a hierarchy of layers that each scores candidate results. We use traditional DSP to leverage a priori domain knowledge, and this allows us to improve efficiency, or if our deployment platform has limited resources and we're pretty sure that we're going to max out those resources, then leveraging a priori knowledge and using traditional DSP is going to allow us to achieve better quality for that deployment platform and those resource constraints. And then finally, we're going to use neural networks to manage deep hierarchy. Any long sequence of layers that we can imagine in our solution is going to be much easier to create if we can just learn all of those layers at once, so we can encapsulate them with a neural network and solve our problem this way. And that's it. That is my grand unified theory of smart algorithms. So I see we have 1 minute. Do we have any questions? And by the way, I'll be around all day, so feel free to ask me questions. I'm sure that there are many. Yes, Julius.
Wait. Oh, thanks. Very interesting. Have you thought about like combining them? In other words, you can have your deep neural net and then put in known good signal processing structure, such as you describe, but leave it all differentiable and have some fully connected layers on either side, and just let it all optimize from there. In other words, maybe you could think of traditional signal processing engineering as just giving the neural net a jump start on some decent modeling structure that it may be able to take from there.
Yes, absolutely. We can leverage a priori knowledge by imagining that the model that we need to end up with is going to need some sort of particular structure. And therefore, we build that structure into somewhere in our neural network model and then let it be learned from there.
Okay, I think we're ready to change. We have Chris Apple coming up.
Thank you.
All right. Hello, everybody, and welcome to my talk. It's called Taming Real-Time Logging, Lessons Learned from the Trenches. My name is Chris Apple, and in the last year for my company, I implemented a real-time logger, and I'm hoping to share those lessons with you today. So first, a little bit about me. My name is Chris Apple, like I just said. I'm the lead audio software engineer at Spatial, Inc. We design playback and content creation tools for immersive soundscapes that evolve over time. If that sounds interesting to you, please reach out after the talk. I've got 8 years experience in the audio industry, split between Dolby, Roblox, and now my first startup experience at Spatial. I'd say I'm a specialist in immersive audio. I've spent a lot of time in immersive audio doing playback and content creation in multi-channel audio formats. So diving right into the topic at hand, why do we need a real-time logger? You might ask yourself, I have a logger, it's perfectly fine. Why do I need to even listen to this talk? Well, there's a few reasons why you might need this. In your real-time log in your real-time thread where you're processing audio, you might want to do some diagnostics. Maybe your reverb algorithm fails, maybe some parameter being set failed, and you want to log error occurred, send some help. If you've ever diagnosed any issues after the fact, you know it's horribly bad to get a log and not have an event in there saying what went wrong. Next, metrics. At Spatial, we're really big on metrics, and one way to do metrics is to write a little blurb out to a log and have some other process scrape it and forward it up to the cloud. So specifically, we're always measuring average and peak render times, and this gives us a good platform to profile and improve our code over time. Last, and the reason that I really took on this task was at Spatial, we allow our users to write Lua code to evolve their scenes. And specifically, we had a content creator who kept leaving log lines in their Lua messages, or in their Lua scenes, and I like to call this logs you can hear, because when they played back, it was just horrible dropout after horrible dropout. Of course, you gotta fix the content, but it'd be nice if we didn't get into that situation to begin with. So let's take on version 0, the most simple form of logging. Let's say you're taking the very, very naive approach, and this is the real-time logger that you came up with. You can see the call down here. Of course, we want variable arguments and things like that. We're going to say hello world from our real-time callback. But this version 0 is just a simple wrapper around printf. This is all it is. It's the world's simplest logger. It's the most straightforward way. Well, when we're evaluating these things, we might want to say, are there system calls, are there allocations, or are there mutexes? We're all in this room, we're all audio engineers, so we all understand that we can't do time-unbounded operations in our real-time thread. There's tons of talks about that. I'm not going to go into all the details for now. You'll just have to trust me. So if we're looking at this first attempt, we might say, are there system calls? Yes. Printf, we're going to ask the operating system, hey, I'm going to write out to the terminal. There we go. Red box, we're totally blocked here. But furthermore, as audio engineers, we want to be a little bit skeptical. We can't just trust anything that we're given from the standard library. So we probably say, are there allocations going on in printf? I don't know, maybe. That's enough to disqualify it. And are there mutexes? Again, same answer. I don't know what the operating system is doing when I call printf, so I have to assume the worst. So let's take on the first improvement and maybe the biggest improvement towards our real-time logger, using a logging thread. What if we took all of that bad behavior and pushed it off on another non-audio rendering thread? That might look something like this. We have our audio thread coming along and calling a method called real-time log. Now, instead of printing directly to a file, we are going to enqueue some blob of data into a queue for processing later. Meanwhile, we have the logging thread coming along and periodically calling dequeue on this same queue and printing it out, whatever format you normally use, printf, cout, log, etc. But crucially, because we're synchronizing across threads here, we have to use a lock-free queue. One of our criteria is we don't use locks, but we also don't want race conditions in our code. So a lock-free queue is crucial. When I was doing research for this, I came across reader-writer queue written by this lovely human, Cameron314. If you're ever watching, Cameron, thank you for the lock-free queue. It has a couple APIs that are really, really important for us as audio engineers, in that you can reserve space for it up front. Here, we reserve 100 elements in the queue at initialization time. And it has an API to try to enqueue. So here it tries to put the number 18 in the queue, and if it fails, it just fails. There's no allocations performed, and this is super, super important because we cannot have allocations when these happen. So if you're ever interested in the dark, dark magic of lock-free programming, highly recommend. He wrote an article called A Fast Lock-Free Queue for C++, where he goes into the design of this lock-free queue. It's a really great read. So how might this look in code? Well, we're going to create some struct we'll call logging data. It contains whatever custom types we use. So at Spatial, we use a log region and a log level. Think debug, crit, whatever you normally log. But crucially, we're going to have a fixed size character buffer that we're going to print our message into. That fixed size is really important so we don't allocate. So this is our real-time log function now. So we are going to fill in our custom data and then use VSN printf to, instead of print directly to the terminal, we're going to print into the buffer instead. So you can see that here. And at the very, very last line, we are going to take this new data that we just created and put it into our lock-free queue. Meanwhile, while that's happening, in the bottom pane, we have our logging thread, and while this thread is alive, all it's doing is going through, emptying the logging queue anytime that there's something in it, and in this case, it's calling cout to log. So all of the system calls and all the mutexes and anything that's happening in cout is off our critical thread. So this brings up a good opportunity to talk about some of the downsides of this. You might say, Chris, I'm so convinced by version 1, I'm going to throw out my old logger, never look at it again. It's the most beautiful code I've ever seen. But you have to understand there's trade-offs to this type of programming. First off, like I said, we cannot reallocate our character buffer in the real-time thread. So we must pick a value at initialization time and stick with it. Any message that's over 512 characters is going to be truncated, and that data will be lost. Furthermore, we're going to fix size our logging queue, and any message over 100, in this case, is just going to be dropped on the floor. So it's really important to tune these two values to your application's purposes. So are we all done? Well, we've improved a lot. We got rid of at least the printf system call. That's really great. No allocations. We're using a fixed size character buffer and a fixed size queue right at the beginning. And we're synchronizing across threads, but we're not using mutexes. So this is looking pretty good. But the fact that I'm only 9 minutes into an 18-minute talk tells you maybe we're not all the way there, or I didn't plan my time that well. So what's wrong here? Like I said in the beginning, we have to be super paranoid as audio engineers. We have to take nothing for granted. And what looks fishy here? Well, maybe it's this call. Again, this was something just handed to us. Are we sure that it's real-time safe? Well, if you look in the man pages, it will say something like blah, blah, blah. Thousands and decimal separators are returned by localconv. And what does that mean in plain English? It means these three numbers are the same exact number, just in different places in the world. So if your computer's in Norway or Thailand or United States, when you call a printf family function, it's going to ask your operating system, do I use a comma here? Do I use a space here? Do I use a period here? Really unfortunate way to lose our real-time safety. But if you look at a profiler, you see a lot of words that I hate to see in my real-time callback, lock, slow, unfair, lib system, platform, dilib, all horrendous, not really what you want. You can see it's spending a lot of time here, so very, very unfortunate. So when we're looking at this, are there system calls? Yes, we obviously just proved that there's some system call to the localconv function. There's a mutex that protects that function, so that's unfortunate. And now I'm not even sure that there's no allocations happening. So we're paranoid. We have to be paranoid. We just lost our best friend, the printf functions. But let's turn to a group possibly more paranoid than audio engineers. And who might that group be? Well, luckily for us, they exist, and they're known as embedded systems engineers. And you would be paranoid too if you had a system with super limited resources, limited memory, a slow processor. You would hunt out every single mutex, every single allocation, and eliminate them. So luckily for us, embedded systems engineers have a lot to teach us as audio engineers, and they have re-implemented the printf family functions over and over again using no allocations and no locks. So the one that I settled on for my implementation was called STB. These are billed as single file public domain libraries, so just one header for one function. And crucially, the STB-sprintf header, the one that we're going to use, has only 2 includes in the entire file, and they're just to include different types. They're all listed here. You can look in the entire function for malloc or new or mutex or lock, and you will not find a 1. It's beautiful, and you can use it, and it's real-time safe. So what might this look like? You take in your variable arguments just like you did before, and it's a drop-in replacement. Instead of VSN printf, you're going to use STB VSN printf, pass in your VA args, and you are all good. But this brings up an important side note. Is using VA args real-time safe? I'm saying we have to be paranoid and not trust anything. Well, the answer is yes, VA args is real-time safe. The way that VA args works is all your parameters are passed in on the stack. Your first one, in this case A, you just add the size of A and you find your next parameter. You add the size of B, you get your next parameter, and you go up like that. Everything on this slide, totally real-time safe and good to go. However, the real answer, as always, is a little bit murkier than that. If you look at some man pages, it will say, finally, on systems where arguments are passed in registers, it may be necessary for VA start to allocate memory. We were so close to something perfect, but luckily, in CPP or C++ 11, there is a solution to this in variadic templates. So variadic templates, a very, very dense topic that I won't be able to get into here fully, but it might look something like this. If you're interested, please check out this talk from CPPCon. And further, this unlocks the ability to use lib format, which is the modern type-safe way to do printf functions. So you can see the call. It looks a little bit different than we're used to. It has the curly braces. But for the rest of this talk, please bear with me and trust that printf is real-time safe on my system, at least. I don't have time to go into all of the nuances of variadic templates here. So when we look at this version that we just wrote, which is the logging thread, plus our new real-time safe printf function, it might look something like this, and we got rid of our system calls, we're sure there's no allocations, and there are no mutexes. So this is all good and well, but there's one more improvement that I want to make, and this is a note on ordering. So let's say you are the scheduler of your system, and you are trying to print out the numbers 1, 2, and 3 in order in the most convoluted way possible. Maybe you would do it like this across 2 threads. So user interface thread logs the number 1, your real-time callback logs the number 2, and then your user interface thread calls the number 3. Maybe that looks like this in a diagram. So the UI thread logs the number 1, and it goes directly to the file. That's really crucial. Your audio thread calls real-time log, but again, we're not going directly to the file or directly to the terminal. We are putting it in the queue for processing later. UI thread logs 3 in the meantime, and sometime way, way longer down the road, we're calling process log and printing the number 2. What this looks like is 1, 3, 2. You thought you could count to 3, but you were off by 1, so unfortunately, you won't be able to do it. So how do you solve this issue? Again, go to the issue of you got logs from a customer and you're trying to figure out what happened, but now you have a huge block of your UI logging and a huge block of your audio logging, and there's no way to re-interleave them. So the way we solved this at Spatial was an atomic sequence number. So this gives a number to the logs that you can go through and sort on and figure out what happened and what time. So in your non-real-time log function, you'll increment this number when the log line is printed to the file. In your real-time log function, you're going to increment this number when the data is enqueued on the queue. Again, these are the 2 opportunities or the 2 places in which these things are happening synchronously in the threads in which they're called. So non-real-time log when it's actually printed, real-time log when it's put into the queue. So we get all the benefits of before, nothing has changed. We're using atomic numbers, so everything's real-time safe. And relative ordering is preserved. So down here on the bottom, we actually have an excerpt from one of our logs. We use a JSON flavor of a real-time log. And you can see down here at the very bottom, we can see our audio region has come in and logged sometime later on. This must have been when process log was called. And it has a sequence number 2, so we can just write a quick command line script to resort things by sequence number and get the relative ordering out. So an implementation summary. This is everything we've learned, and this is the recipe to create your own real-time logger. On initialization, we're going to create a lock-free queue containing type log data plus a buffer to print into. We're going to create a thread to periodically call process logs. In the real-time log function, we're going to create a new variable of log data. We're going to fill in its buffer, and we are going to put a sequence number in it to preserve relative ordering. And we'll try to enqueue the data and not cry too much if it's dropped on the floor because we understand that trade-off. In the process log function, we're going to periodically dequeue the messages in the queue and log them. So if this seems like too much work or you just want a running example, I have put up this code in this repository on GitHub. Please check it out. It's somewhere between a usable library and an example. I just know that I learn a lot better when I have usable, runnable code here. So please check it out. If you want to chat on the GitHub issues, please file an issue. So in summary, what did we learn? Do not use normal logging in your real-time thread. You'll cause dropouts, and it'll be very sad. A real-time logger is a glorified lock-free queue that you can print messages into. Beware sneaky system calls to localconf in the standard printf family code. You can use sequence numbers to ensure your loggers have proper ordering across real-time and non-real-time logging. Beware the possibility of data loss using the real-time logger. You will truncate and lose log lines if using the real-time logger improperly. And lastly, VARgs is real-time safe on many platforms, but variadic templates are probably the best general solution for all systems. And the good news is it unlocks the use of lib format, which is type safe as well. So that's my talk. Thank you to all my reviewers and the open source libraries. Does anybody have any questions?
Right, so you can control the real-timeness when you enter into your printf statement, but your arguments may be evaluated at that time and they could not be real-time or other problems like that. Have you found any techniques to help with that? I mean, if you're using the various templates, could you inspect to see if you're being passed a function and say, hey, don't give me functions, don't cause me to call log or something like that and some number and be slow.
Yeah, I think that's a really clever idea. I will say my template knowledge is definitely lacking in my C++ world, but that seems like a reasonable thing you could do. Of course, all the normal rules of real-time processing occur. You know, if you have to grab something using a lock and then log it, everything's out the window. So yeah, it's up to you to enforce that or just have good real-time hygiene in general.
Thanks for the talk. This was I learned a lot. I was wondering, if you care about ordering, why not just have every thread put stuff into the logging thread instead of logging from different threads?
Yeah, so that goes back to one of the trade-offs of you have a fixed size buffer that you have to choose at initialization time. So let's say you have 100 messages and you say, okay, I'm never going to resize this thing. If you end up logging too much, which maybe your database thread like spams the logs at some point, you're going to continuously drop things out. So that's definitely one approach, but you trade memory to do that, right? You have like some big stack of memory that you have to allocate right at the beginning, and that's the trade-off that you use. So we use a mix of both, and the sequence number was a good way to get some of that memory back.
All right, let's give it up for Chris. And next we have Romain. Come on up, Romain.
Okay, hi everybody. My name is Romain Michon, and I'm a research faculty at INRIA in France and a lecturer at Karma, Stanford University. And I'm going to talk about high-level programming of FPGAs for real-time audio signal processing applications. So we're going to be more on the embedded side of things, and I don't know, maybe like some of things that were presented in the previous talk could work for this. Anyway, so this is the presentation outline. First, I'm going to tell you what an FPGA is, because I'm sure that some people in the room probably don't know. I'll show you how FPGAs can be used for real-time audio signal processing. I will talk about our system, which allows people to program FPGAs at a very high level for audio processing applications. And finally, I will talk about potential applications, performances, and research avenues. So what is an FPGA? So usually in the field of audio, the type of processors that we use have a fixed architecture. So people are going to use DSPs, people are going to use CPUs, people are going to use microcontrollers, and all these systems have a fixed architecture. Unlike these kind of processors, FPGAs have an architecture that can be modified to serve a specific purpose. So basically, an FPGA can be seen as a make-your-own processor kind of system. So basically, the way FPGAs are programmed are using what we call a hardware description language. So you can't really program FPGAs with traditional programming languages like C, C++, or whatever. You have to use a programming language which basically describes an electronic circuit, which is why FPGAs are considered more as hardware than software in some respects. So the resources that you have on an FPGAs are a set of programmable logic blocks, and basically the way you program your FPGAs by connecting them together. So the performances of FPGAs are limited by two different things. Basically, it's usually the amount of resources that you have available on the chip. So basically, the number of logic gates, the number of block RAMs, or things like this. So it's really like the physical resources that are available in the FPGA that matter. And a little bit like other kind of architectures, the maximum clock at which FPGAs can be run is also important. So as many of you probably know, FPGAs are known for their high level of parallelization, which means that potentially you can gain significant performances figures if you have an algorithm which can be heavily parallelized. And that's due to the fact that because you can make your own processor, you can decide to have as many cores as you want, basically, and that's why you get a very high level of parallelization. The two main manufacturers of FPGAs are Xilinx, which was recently acquired by AMD, and Altera, which was less recently acquired by Intel. But there are others. Those are like the two main manufacturers. So how can we use FPGAs for real-time audio signal processing? So the first thing that I want to say is that FPGAs offer really unique features in the context of real-time audio DSP. So first, you can do sample-per-sample computation, which can be very useful, especially if you want to have low latency performances. You can target super high sampling rates in the megahertz range. You can go like far above 20 megahertz if you want, so potentially that can be interesting. You get very low latency because of the sample-per-sample computing. You have a lot of GPIOs, which means that if you want to interface your FPGA with hardware, especially if you want to do, like, say, multi-channel, FPGAs can be very interesting. They're very well adapted for audio DSP algorithms, which present a high level of parallelization, like spatial audio, model synthesis, and we're all talking about real time here, right? So just want to emphasize this. FPGAs are already used at the heart of some high-end professional audio products, and I'm going to give you a couple of examples of that. So typically, you're going to find FPGAs in a lot of Dente audio interfaces because you need to actually treat a lot of parallel audio streams together, basically. And because FPGAs can really deal with a lot of parallel processing, you're going to find FPGAs a lot in Dente audio products, basically. So in that very specific case, the resources of FPGAs are used mostly to deal with parallel processing of audio. Another kind of products where you're going to find FPGAs are some analog or digital analog synthesizers, where basically you want to have a very high audio sampling rate. And that way you can potentially get rid of more aliasing if you're doing virtual analog or things like this. So that's the case of the Novation Summit keyboard, which has an FPGA to run some oscillators at 24 megahertz in terms of audio rate. Another kind of products you're going to find are products where people use FPGAs to do like heavy computing for audio processing. So here you sort of take more advantage of the performances afforded by FPGAs, so like the computing performances. And that's the case of the Antelope Audio Synergy Core series. So if FPGAs are so great, why don't we see more of them, both in the industry and also in academia in general? Well, the answer is very simple, and it's because basically they're very hard to program. And also, if you are not used to deal with low-level problems, then FPGAs are definitely not for you. Okay, so usually when you deal with FPGA systems, this is kind of the architecture you're going to have for audio-based systems. So usually on an FPGA, you always have a CPU as well, and they communicate. They share DDR, which is usually outside of the FPGA, and so there is always like this sort of loop between those three elements, basically. So you want to do some computation on the CPU. But anything that needs to have very low latency or super high performances, usually you want to run that on the FPGA. And then you can control the system using sensors or GUI, and that usually goes through the CPU. And then you have an audio codec for retrieving audio inputs and producing audio outputs, right? So this is kind of the basic architecture of how most of these products actually work. So why is it so challenging to program FPGAs for audio applications? So the first one is you have to deal with interfacing the CPU and the FPGA, which happens at a very, very, very low level, and so that's annoying. Another thing that's hard to do is interfacing DDR with the CPU and the FPGA, which also happens at a very, very low level. You can't really just allocate memory and use it. You actually have to access memory by hand directly in DDR, which is potentially hard. Balancing computation between the CPU and the FPGA can also be a lot of work, like what goes on the CPU, what goes on the FPGA. All of those things imply potentially important design decisions on what goes where, and so it's definitely more complicated than regular architectures. Interfacing the FPGA with audio codec chips can be hard too, dealing with clocking issues, because that's really at this level that you're working, dealing with hardware description languages like Verilog or VHDL, and implying the use of fixed point arithmetic. You can't really do floating points on this system, so it means that if you want to do audio processing, you have to do it the old way, and that can also be pretty rough. Thinking programs as a hardware circuit instead of software is also another issue, because usually if you're a software engineer and you're trying to program an FPGA, well then it's going to be pretty tough for you because of that. Anyway, so this is an example of an FPGA board that we've used for this project. And so what we propose people to do is to use Faust to actually program FPGAs. So briefly, what is Faust? Faust is a functional program language for real-time audio signal processing. So it's a DSL, domain-specific language. It's been developed for the past 20 years. And Faust allows us to generate C, C++, Java, LLVM, WebAssembly, Rust, and many more types of programming languages. And so you can go from Faust to any of these languages and potentially program an FPGA with it. The Faust compiler provides a high level of control on the generated code, so we really master that aspect a lot. And one of Faust's strengths is that it has hundreds of DSP objects which are pre-implemented and that are completely open source, thanks to JUCE, for example, in particular, who really contributed a lot to this. Faust is completely open source. How do we use Faust with FPGAs? So we developed this thing called the SyFaLa toolchain, which is also completely open source and that you can potentially use for this. And it basically allows you to program FPGA platforms using Faust. SyFaLa relies heavily on this technology, which is called high-level synthesis, which is provided by Xilinx, and which allows you to deal with FPGAs at a slightly higher level than you wouldn't normally do if you were using hardware description languages. So here is what kind of happens. You go from Faust, you generate C++. It's very specific kind of C++ that is really specifically designed to work with HLS, and then you do high-level synthesis, and finally you generate an intellectual property, because that's how compiled objects are called in the world of FPGAs, which is kind of funny, right? So a specific Faust backend was created for this, and Faust really takes care of balancing computing between the CPU, the FPGA, and deciding on what goes into DDR and what doesn't go in DDR and just remains on the FPGA. SyFaLa already supports a lot of audio codecs, which are all audio codecs that are kind of aiming for low latency. So this is the case of the analog devices, ADU 1777, 1787. So those audio codecs are specifically designed to have very good audio latency. A series of open source modular sister boards have been designed for this, and finally the SyFaLa toolchain can be optionally used now with Linux. So it means that you can actually use this as a hardware accelerator, so you can run Linux on the CPU and process all your audio DSP on the FPGA, and the SyFaLa toolchain is compatible with this. Anyway, so this is an example of a sister board that we implemented as part of this in the team, and so they basically just go on top of the FPGA, and this is more like a side project. So yeah, briefly, I want to talk about the performances, applications, and research avenues for this. So the first thing is ultra-low latency. So the main reason for doing ultra-low latency is potentially to be able to do active control. So basically, what you do with noise-canceling headphones can potentially be exported to the size of a room, and to do this, you potentially need very low latency. And so this is one of the things that we're targeting. So the system that we have now runs with this figure, so you can have 11 microseconds of round-trip latency for like analog to analog. Basically, if you run the whole system at 768 kilohertz, so you need specific audio codecs for this, obviously. So potentially, you can get a lot of audio inputs, a lot of audio outputs using this. So this is good for spatial audio with these latency figures, which is also important. And most applications for this are targeting towards active control, basically. And yeah. So we have currently a project, like a research project around this, which is called the FAST project, and it's between multiple institutions, and the whole goal of this project is to develop this platform and also use it in the context of active control of room acoustics. So we're currently developing things like this, where it's like big sister boards for FPGAs, where you get a lot of audio inputs and a lot of audio outputs, but with latency as low as 11 microseconds for round-trip latency, right? So this is what we're currently doing. Another project that we have is around ultra-high audio sampling rates. So basically, this is a project that we do with Victor Lazzarini and Joe Timoney at Maynooth University in Ireland, and the whole idea behind this is to basically be able to do audio at more than 25 megahertz in terms of audio sampling rate, which opens the doors for lowering aliasing, or doing all sorts of things in terms of the way you approach audio DSP. And currently, we have a fifth-order sigma delta DAC running on the FPGA, and so it means that this is already kind of working. Sorry, I'm going a little bit faster because I think I was a little bit ambitious in terms of the number of slides that I prepared, as you can tell. So we have another project around multi-channel, where we try to use FPGAs to basically do WFS, and this is also all based on the SyFaLa toolchain. So here we have an example of a WFS system, which basically costs very little money because it's based on those I2S amplifiers that are all controlled by the FPGA. So basically, you can do very, very cheap WFS using this kind of system. So this is kind of an overview of what we have. So 11 microseconds latency. We could probably lower this if we manage to get a sigma delta ADC implemented directly in the FPGA. And also, we can get a lot of audio inputs and audio outputs out of the system. Okay, I'm going to skip this for now because I want to take questions. And I will just say thank you to all of you. And I just want to say one more thing before I stop talking. There is going to be a Karma Summer workshop on this topic, and we are still taking registration. So if you're free at this time, it's a 5 days workshop back in Palo Alto, and it's going to be taught by Maxime Popoff and Pierre Cochard. Thank you very much. Yeah.
Are you familiar with System C, the programming language that was an attempt merger between VHDL and C++? And can you comment about it?
Yeah, of course, yeah. So, I mean, I think HLS really replaced, I think if you go to Xilinx or if you go to Intel, I feel like HLS is really like the kind of tool that they are trying to promote to do this kind of things, you know. And so, but yeah, no, we know of this, but I don't know if it's still like super active, you know. And currently, like for high level programming of FPGAs, I think that HLS is kind of the go-to tool that people are using nowadays. So, but yeah.
So I've only known FPGAs from kind of in the past, like large chips. Like how small do some of these chips get?
You mean like physically?
The physical
or?
size, yeah.
Oh, they're as small as like a microcontroller or as a CPU. Like if you basically go back to this picture, like I mean the physical footprint is very low. You know, like this is, I mean you see like the size of the jack connector here. You know, like that's the FPGA here. You know, and that's the heatsink for the FPGA. You know, like so they're actually fairly small. You know, and this FPGA is like a rather large one. You know, like you can have like FPGAs that are like as small as like the tip of your finger. No, so they're actually very small. Yeah. Yep.
What is the is there any hope of M1 Max support or Mac support overall? Looking at the page for the upcoming.
Oh,
yeah.
That is a good question. Probably no. And it's not really our fault. It's mostly Xilinx's fault, basically. You know, because for some reason, traditionally, people in the FPGA world use more Windows than the Mac. You know, and so much of their toolchain only works on Linux or Windows, basically. And so I think they never really thought about this. And since it's very hard to deal with Windows for this kind of stuff, you know, like Linux is just the way to go. But yeah, good question.
Romain, thank you.
Sure.
We are ready to switch over for our next module.
Thank you. Good luck.
All right. Thanks, everyone, for coming today. My name is Shaikat Hossain. We heard some great talks this morning on software and hardware. My talk's going to be coming from more of a hearing sciences, psychoacoustics kind of vantage point. I currently work as an acoustic engineer at Apple, working on spatial audio. And prior to that, I conducted research in the area of cochlear implants, which is what I'm going to be talking about today, focusing on how to improve sound coding to facilitate better spatial hearing and music perception for CI users. So today I'll be presenting on how cochlear implants work and how to simulate aspects of their signal processing using vocoder simulations, which can be useful research tools in the field. And I'll also share some code and audio examples from a MIDI-enabled vocoder plugin I developed using JUCE, which can be useful as a tool for creating music that's inspired by CI processing. So my first ADC was actually 5 years ago in London in 2018. And I presented a poster that year and got a diversity fellowship, which Josh recommended I apply for. Shout out to Josh, aka the audio programmer. This is a picture of me with my luggage, taking a picture of the ADC logo, and about to head back to the airport straight from the conference. I wanted to be able to come back to ADC to give a talk, so I'm like incredibly thrilled to be here today. And I thought I would first start with providing a little bit of a background a little bit about my background as it relates to audio development. I first got my start working as an intern at Output, where I worked on the Portal granular synthesis plugin. I got to cut my teeth on just getting involved in some of the audio effects for the plugin. After that, I worked at Meta Reality Labs, working on AR/VR audio for their smart glasses and Oculus Quest devices. And my current role is working on spatial audio for AirPods at Apple. But the work I'm presenting today relates to research I got involved in while I was in academia, prior to my industry experiences. And with that, I'd like to start today by considering the cocktail party problem, which simply stated has to do with how we navigate complex listening environments consisting of multiple sound sources, including different talkers and background noises. And in such situations, auditory scene analysis is the term which describes the process by which we're able to parse an auditory scene into distinct sound objects, making use of different cues. And these cues can include differences in voicing and spatial cues for different sound sources. So for people with normal hearing, this task is quite natural and it comes without much effort. However, for individuals with hearing loss, this situation is substantially more difficult. For mild to moderate hearing loss, typically a hearing aid can provide sufficient amplification to restore audibility. However, for moderate to severe hearing loss, a different approach must be considered, and the most common approach in this case comes in the form of the cochlear implant. So cochlear implant devices have been around for over 50 years now, and instead of amplifying sound like hearing aids, cochlear implants bypass acoustic transduction and stimulate the auditory nerve directly. So for those of you who are unfamiliar with how cochlear implants work, sound is first captured by the microphones, which are positioned on the behind-the-ear unit, or BTE sound processor, as it's commonly referred to. The sound is digitized and passed through various noise reduction stages, including beamforming, before it's transmitted as an FM radio signal by the transmitter to the internal implant, which receives the signal through electromagnetic induction and then generates a sequence of biphasic electrical pulses, which are sent to the corresponding electrodes along the cochlea. And cochlear implants make use of an elegant aspect of the architecture of the auditory system, where pitch is encoded in duplex, both in terms of the place of stimulation along the cochlea and in terms of the rate of firing of auditory neurons. So the cochlea is arranged like a piano, where the frequencies of the auditory neurons are arranged spatially. If a given electrode is stimulated near the base at the entrance of the cochlea, it elicits a high-frequency pitch percept, which progressively lowers in pitch as we move towards the apex. And this is referred to as tonotopy, very simply describing this type of frequency-to-place mapping. The Greenwood function is a function based on psychophysical research which has mapped the relationship between pure sinusoidal tones and the position of the hair cells that they excite along the length of the cochlea. So this function, which is specific to humans, relates millimeters along the cochlea, the variable x in this equation, to specific characteristic frequencies. And so it's commonly used as a guide in surgical procedures to ensure that the electrode array is inserted deeply enough into the cochlea, because aligning the electrode array so that the intended frequencies are being delivered to the correct locations is critical to successful outcomes for cochlear implant users. In addition to coding pitch by the place of stimulation, pitch can also be coded by the stimulation rate in a cochlear implant. So if we were to look at a given electrode channel, we could present a low-frequency pulse train and a high-frequency pulse train, where the high-frequency pulse train would be perceived as being higher in pitch. So now let's take a deeper dive into the signal processing that's implemented in the CI sound processor. After sound is captured by the microphones on the sound processor, it's split up into a fixed number of frequency bands. The envelopes of each of these bands are extracted and used to modulate the pulses, which are then delivered along the electrode array. And this kind of processing is equivalent to a channel vocoder. And this is why vocoders are commonly used for CI simulations. It's important to mention that a high-rate carrier signal, usually around 1,000 pulses per second, is typically used. And the carrier signal has no relationship to the incoming sound signal. It serves merely as a way of sampling the envelope modulations with high fidelity. And during the envelope extraction stage, the fine structure information within each frequency band is discarded. And this has negative consequences to speech and noise and music perception. You could think of the distinction between envelopes and fine structures in terms of drawing. The envelopes could be thought of as providing the outline of the drawing, whereas the shading details could be thought of as the fine structure information. And another helpful way to visualize the signal being sent to a cochlear implant is the electrodogram. So for those of you who are unfamiliar, a spectrogram, as pictured on the left of this slide, plots the spectrum of frequencies of a given sound over time. In this case, the spectrum that's plotted is of the speech signal wheel. The right figure is an example of an electrodogram, which is similar to a spectrogram, and it plots the current levels of each of the 22 electrodes in a cochlear implant, where each electrode can be thought of as corresponding to a single frequency band in a vocoder. So given that CI processing is based on the channel vocoder, vocoders are actually used quite often in the research field as CI simulations, where listening studies are conducted with subjects with normal hearing. And this has benefits in terms of controlling for factors which are highly variable in the CI population, such as duration of deafness, duration of implant use, and level of neurological functioning. And it's also important to mention that these simulations don't necessarily sound exactly like CI devices, but they do give an impression of the level of speech intelligibility that can be achieved with a dramatic reduction in spectral resolution as produced by CI devices. And studies have demonstrated similar levels of speech intelligibility between CI users and normal hearing listeners using vocoders. And these types of CI simulations typically make use of bandpass noise or sine tones centered on the center frequencies of the filter bank channels. So to provide a visual example of how vocoders can limit spectral cues, let's take a look at these picture examples. When the number of pixels is limited to a very low resolution, such as the picture on the left, you can't really tell what you're looking at. But as you increase the resolution by adding more pixels, you can start to see the face emerging from the fuzziness. You only need about 20 pixels to know who the face belongs to. And now I'll play you some examples of how this might work for speech. First, I'll play you an example of a speech utterance that's processed by a one-channel vocoder. Yeah, and then the same utterance processed by an 8-channel vocoder.
This is an example of an 8-channel processor. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Hopefully you're able to tell the difference in intelligibility when more spectral channels were added. So there are two approaches to designing the filter banks used in these vocoder simulations. The first approach is the IIR filter bank approach, where a bank of fourth-order Butterworth IIR bandpass filters are used. And these filters approximate auditory filters in terms of bandwidth and center frequencies. The envelopes from each band of the filtered waveforms are then extracted using low-pass filtering and used to modulate the carrier signal. And the obtained waveforms are then summed to generate the final acoustic simulation. The second approach is an FFT-based filter bank, where the FFT of the input signal is calculated, and the FFT bins are then combined to form N bands with bandwidths corresponding to those of auditory filters. Using this approach, the primary parameters are the FFT size, which determines the number of spectral bins, and the number of frequency bands, which the FFT bins will be subsequently grouped into. And depending on the specific type of vocoder implementation, the FFT-based approach can be computationally more efficient, but it's important to choose an FFT library that's efficient enough for your given application. After taking the FFT of the input signal, the FFT bins need to be grouped together to approximate the bandwidth of auditory filters, since FFT bins are linearly spaced in frequency. And the Bark scale can be useful for this kind of mapping. For those of you who are unfamiliar, the Bark scale is a psychoacoustic scale based on subjective measurements in which equal distances along the scale correspond to perceptually equal distances. So for example, if you were going from the first to the second Bark band, that'd be as big of a change in perceptual pitch as going from the second to the third. And weights can be calculated for the purposes of combining these FFT bins into Bark bands, and there's some useful scripts available in Python and MATLAB that allow for the calculation of these weights. So with all that in mind, how do we create a real-time vocoder plugin? For that, I turned to JUCE, the JUCE framework, which many of us here use. There's a number of helpful classes which facilitated the development of my plugin. For the filter bank, the IIR filter and FFT classes provided really intuitive and easy-to-use methods. And for the synthesis of the carrier waveform, the synthesizer, synth voice, and synth sound classes were super helpful. I also used the Maximilian library to create oscillators with different waveforms, including square wave, sawtooth, and noise. Now, let's jump into some code. To start, let's take a look at the plugin processor for the vocoder. We're only going to focus on a few of these methods in my talk today, so just these ones at the bottom. So starting with the function at the top, the calculate RMS amplitude of block function simply calculates the mean RMS amplitude of a block of audio samples of size FFT size. The smooth spectrum function takes the average of the signal magnitude as a kind of low-pass filtering operation to help extract the envelope of the signal. The get magnitude of interleaved complex array function calculates the magnitude of a complex array, such as FFT data. And the function at the bottom simply multiplies the carrier signal by a sinusoidal envelope. If we take a look inside the synth voice class, which is responsible for the synthesis of the carrier waveforms, the most important part of this class is the render next block method, which gets overridden, and it handles the generation of different waveforms using the frequency which it receives from the MIDI note number, as well as start and stop note triggers for driving an ADSR envelope that's multiplied with the carrier waveform. Instead of showing you the process block of the plugin, I thought it might be more helpful showing just the vocode method itself, which implements the actual processing of the vocoder. First, the FFTs of both the modulator and carrier are calculated, and the magnitude of the modulator is then computed and subsequently smoothed by averaging. The for loop at the bottom loops through the number of filter bands in the vocoder and multiplies the carrier with the smoothed envelope that's extracted from the modulator. So here's my current UI for my plugin, which I've named the Cochlear implant vocoder. I've got a very simple layout for now, which consists of just a waveform selection section with a group of buttons, but I'm planning on adding a drop-down menu so that users can select the number of frequency bands, which is an accessible parameter in the plugin currently. So here's a little demo of speech processed through the plugin using 16 channels.
Testing 1, 2, 3. Testing 1, 2, 3.
Okay, so in summary, after presenting an introduction on how cochlear implants work, I've shared about the design and code behind a real-time vocoder with MIDI functionality and parameters for waveform selection and the number of frequency bands. For next steps, I'd like to consider how to simulate other aspects of CI sound coding. In cochlear implants, it's possible to use a technique called current steering, where you can create virtual pitched percepts by steering the current between two neighboring electrodes. And I'd like to see if I could possibly simulate that using additional weightings with my FFT bark band-based filter bank. And lastly, I'd like to consider how to use real-time vocoders such as this one as a way of experimenting with sound design approaches in ways of treating cochlear implant processing like a musical instrument, so we could think about how to reverse engineer music that might sound more pleasant to CI users. And with that, I'd like to thank the ADC team and the audience, both in person and online, my old lab at the Bionic Ear Lab at the University of Southern California for providing me with the opportunity to learn about cochlear implants. And I'd also welcome any questions you might have. Thank you.
How fine-grained are the bands in terms of, is there a limit to the resolution?
Great question. Different cochlear implants have different numbers of electrode channels. Some manufacturers have 22 channels, some have 16, so it really depends on the physical manufacturing of that electrode array. But you can create virtual channels by steering current between two neighboring electrodes, and that's kind of how they trick the auditory system into having more resolution, better resolution. Yep.
So I'm sure you could have done a lot of the work, say, in MATLAB with some simulations, but you developed a real-time tool. Has that felt like you can develop ideas quicker? Tell me about that real-time system.
I'm glad you mentioned MATLAB, because MATLAB is what I use to calculate the bark band weightings, and I actually implemented the whole plugin in MATLAB first as a prototyping environment, because there's a really useful class in MATLAB called Audio Plugin class, and you can develop a real-time plugin and test it in MATLAB, which is what I did. So that was super helpful, and then I turned to JUCE to try to port that to C++. Mm-hmm.
In terms of evaluating how this would sound to a cochlear implant user, Is there something you could do with like headphones and HRTF to get closer to what they might experience, or?
Absolutely, and that's what we do with listeners with normal hearing. But there's also very interesting use cases with subjects with single-sided deafness who have cochlear implants on one side. So they have effectively normal hearing on the other side, and we could bring them into the lab and have them do matching experiments where they can match the vocoder specifically to the cochlear implant. So that's something I've done before, and it's super interesting.
Hi, Shaikat. Thank you for the talk. I have a quick question about the cochlear implants. Do they ignore the labyrinth of the pinna to kind of capture the spatial information?
Well, it depends on the manufacturer. Advanced Bionics has a microphone that's placed within the pinna, so it captures the HRTF information to a certain extent. But other manufacturers have the behind-the-ear unit, which is positioned above the ear, so they don't capture that HRTF. But even if they did, it's very crude. That information is very crudely represented in cochlear implants.
Yeah, thank you.
Right. Good morning. I'm Avrosh, and along with my friend and collaborator, Chris, we are talking about plugins that take audio in and produce MIDI out. We hope this will be a good talk for even beginners. We'll try to explain the concept so it's accessible. Right, a little bit about ourselves. I'm a research engineer at Pindrop. I'm part of the research team that researches human voice and its characteristics. We build tools to detect who is speaking from really short snippets of audio given a previous recording of your voice. Apart from that, I have background in music information retrieval, and I develop plugins, play guitar. And Chris.
Thanks. And I'm Chris Latina. I'm an audio engineer at Dolby. I've been working on spatial audio tools for about a decade. Also studied audio content analysis and MIR with Avrosh. And I work on compositions, especially using real-time feature extraction and feedback.
All right, so we've divided our talk into 4 phases. First, we'll talk about why do we want to produce MIDI from an audio track. Then I will talk about how do we do this. We will create a simple example of an envelope follower. Then it'll be a little show and tell of our plugin that we are developing called Flux. You'll see it in action. That will demonstrate some of these ideas. And finally, it is a little bit complicated to map MIDI and use it in DAWs, and we will like to talk about some challenges. All right, let's get started. So first, to lay the groundwork, I want to just visualize our plugin API. We're very familiar with this. This is a process block. We have audio buffer, which can have input buses, output buses, multiples of them, where we represent our audio channels, which passes through the plugin. There is also a MIDI port, which provides us access to where we can write MIDI buffers to send the data out. JUCE has abstracted a lot of differences in how different DAWs and hosts see these inputs and outputs from plugins using these very simple preprocessor flags. And we just have to configure what do we want in a plugin, and the hosts are eventually able to figure that out. So I will keep these in the bottom right corner, so keep an eye on that to see how some of the different plugins will be set up in JUCE. So let's talk about a few standard types. There is audio effects, takes audio in, audio out. There are instruments that we drive using MIDI nodes, and they synthesize audio. There are also MIDI effects. A good example are arpeggiators that can take MIDI input, MIDI events, and transform them to either add or different harmonies to that. There are also plenty other types. There's music effect, which is very AU-specific, which takes it in MIDI as well as audio. And there are many other panners, mixers that act on multiple buses. But I don't want to get too much into it. I do want to mention that it's important to classify these plugins because we are building these tools for musicians and for producers. So it's good for these tools to be intuitive for them to understand what it is going to do. But the crux for talk is this type of plugin where we take a stereo input in, and we want to produce output as a MIDI. So we're trying to build a unit to extract some high-level audio features and output them as MIDI. So an example is a simple pitch detector where we can extract the pitch or chords and output them as MIDI in real time. But music is not just limited to melodies. There is timbre, mood, there's structure, there's rhythm in it. And these are all a function of time. They change over time as the music signal arrives. And there's a whole field dedicated to it. We heard some very interesting talks earlier about this that does audio content analysis and music information retrieval. These are the units that can extract information from the audio signal. And we can represent this information as what we would like to call a control signal and output it as a MIDI continuous control signals that can be very easily represented here. We can also threshold these control signals and produce MIDI events using that. And the reason we are doing this is so we can actually map these MIDI events to external devices, a synthesizer, DAWs, and actuate them. But we would like to go a little bit further into control signals, and for that, Chris, sure, take it over.
So when Avrosh asked me to collaborate on this, we sort of wanted to take a step back and revisit some of our older work. I think around 2016, we had developed some of these concepts. And a lot of them stem from old modular synthesizers and some of their constructions, especially as modulation sources like LFOs. Eurorack is all based on control voltage. Super Collider has the control rate signal. Of course, there are automations in almost every synth and tool, Faust, more currently Max for Live, Bitwig. So that was definitely the inspiration for this. In 2013, I developed an iPad app that worked to sort of hack NRP and MIDI for hardware synthesizers internally. Some of them used NRPN to do, I think it's called, I don't know if it's modulation source, but it's sort of a real-time override and recording of the filter or the envelope on devices like the Electribe. So what I did was I would learn the NRPN MIDI and then allow the user to draw periodic signals like splines or LFOs and create banks of them, and then send them over MIDI so you could override and play existing hardware like a modular synthesizer. I think the classic inspiration is the external signal processor in the Korg MS-20. So this is such a genius design because you take an input in, you can extract the bandpass filtered version, which can be controlled by the low and high cut. You have a frequency out, which tries to basically figure out what the pitch of the incoming signal is, some CV offset adjustment, and a threshold level to set the hysteresis of your trigger output, and also gives the envelope out of the signal, which is basically an envelope extracted level of the amplitude. And then itself with modular composition, routing is sort of the key to how compositions are developed with modular synthesizers. And in many ways, these wires, that you connect the inputs and outputs of these processors, they become sort of the virtuosic element of playing the instrument itself. And also that routing becomes the structure of your composition. So the idea of using internal or external generators is sort of the classic technique to animate or affect sound. You can think of a flanger taking the envelope of the input and modulating delay lines, or a compressor, a VCA. Using envelopes and envelope extraction, you can create extremely dynamic and sort of expressive approaches to very simple signals, and they become very musical. This is very inherent in West Coast style synthesis with Buchla's envelope followers, especially feeding them back into the modulators and operators to create sort of unique structures. So with modern tools, we can now do audio content analysis, and we have a lot of information, even in real time, about the style of timbre, like Avrosh was explaining, about pitch and sort of more abstract semantics of a signal. And this is a quote I've used before in presentations, but I think it covers the idea so well. One of my favorite composers, Asmus Tietjens, he said, "Our recent digital and analog tools enable us to derive nearly every sonic event from nearly every other set of sonic events, and that tiny nearly constantly holds unexpected aural surprises." So in many ways, it's sometimes the portions of the algorithm that don't work so well that provide very interesting outputs for live performance or composition. These are some relevant pieces, thanks to Ryan Friedrich for tipping me off on the Smart Electronics KT drum trigger, which is a very similar tool to what we had developed. Takes in an audio signal, splits it up into 3 bands. You can tune the parameters, especially of the hysteresis, and it outputs a MIDI trigger. This is Vocoder doubler, which is a real-time harmonizing vocal to MIDI harmonizer. And I think we will start explaining our tool.
Thank you. So let's come back from the modular world to our DAWs. And I want to talk about something that's very familiar, a simple sidechain plugin. It takes 2 buses, a sidechain bus, from which it extracts some parameter, and it tries to affect the original signal based on that. And there are compressors that do that. There are many effects that leverage the sidechain. What we can do with our approach is take that box out of that plugin and extract that control signal and emit it as MIDI, which allows us to control a plugin, but we can also control another plugin and extract something from that, do another, and many other, and create some interesting chaos that happy surprises that Chris was talking about. So let's build a quick envelope follower. And a note, an envelope following is trying to track the amplitude of a signal in real time. So, all right, here's a get envelope function. We are providing it the audio buffer that we got in our process block in JUCE. We're going to use a low-pass filter to do this envelope following. So we set our filter coefficients. At this time, we're only operating on the left channel. Based on whether it's the attack phase or the release phase, that is where the signal is rising or falling, we will choose a different coefficient. Different coefficient, and we'll apply the low-pass filter. In this case, we are looping over all the samples in the block, so I'm going to only capture the maximum level. So I will have 1 value of the envelope per block, but this is all totally up to you. We are going to decide the time domain resolution of our control signal, so we can capture a lot more values in this case and save them as MIDI events. Finally, for envelope following, you want low attack, high release for a nice smooth curve. Once we have the envelope and the envelope position that is in the buffer, which sample was the maximum, we can send this to this function, and write it as a control message where the value of the envelope can be scaled to a 7-bit control CC. Continuous control value. With MIDI 2.0, I'm excited we could go up to 32 bits, so we have even amplitude resolution. And we send this message. This is a simple visualization how the release, as you increase the release, you can shape the envelope. And we see as we go up to 100 milliseconds of release value, we have a nice signal resembling a sawtooth, kind of sync to the amplitude of our signal. We will like to present the plugin that we are working on that we call Flux, and hopefully we will play that. All right, so we have a plugin that we have dropped on an audio track, and I'm on a percussive track that you see on the left side. On the right side, these are the envelope being detected. Down here, I'm going to control the attack and release of this plugin to shape the envelope to get it to the states that I like. So in this case, I want really sharp attacks because I'm working in percussion. Okay, so it seems I'm happy with the shape. Now I have another MIDI track on which I'm going to try and receive the MIDI that my plugin is outputting. So the MIDI monitor set up there, and now you can see the CC values are arriving here. On channel 1. All right, what do we do with this? Let's play with the pan knob of our synth track, which is a completely different track, and map that CC signal to the panning knob. And we should start seeing the panning being affected based on our envelope of our signal. I've mapped it to the mute button and created a very cheap stutter effect with no effect plugin. All right, what else can we do? Let's bring a filter in and try to modulate the bandpass frequency. I can also set the range that I want to modulate in Ableton, so I can go from 80 Hz to 8,000. This is a nice wah-wah effect, synced to the beat of my track. And of course, we don't have to limit ourselves. We can map multiple parameters to this control signal. We're approaching some chaotic regions. Let's dial down the resonance a little bit. All right. That was my attempt to show off a lot of things in 3 minutes. Thank you. So there's a lot going on, but let me talk about how the mapping happens. So live allows you to control any parameter using an external device like control surfaces. But if we want to do it from within our DAW itself, so we have to route our MIDI messages to a virtual MIDI bus so that live thinks that's coming from outside. So to do that, we dropped our plugin on an audio track, which is now being routed to this other MIDI track, which is receiving the MIDI. And the output of this MIDI track is a virtual MIDI bus. And that's what makes it accessible. And finally, you quickly turn on MIDI mapping, select a knob, and you got your automation mapped to your CC control. Yes, there are challenges. So let's talk about how this VSTs and AUs will behave when they're trying to deal with MIDI outputs from a plugin. So to demonstrate one of the challenges, we have a VST version as well as an audio unit version of our plugin on different tracks. And you can see that the MIDI track only is aware that only the VST plugin is outputting the MIDI to this. So the MIDI coming from the audio unit is actually not even visible to our DAW. And Ableton does say that the audio plugin standard does not support MIDI, a direct MIDI output, and that's why we're probably not seeing that. So that means that DAWs that recognize VSTs are the only ones that can handle MIDI outputs, so we probably won't be able to use this kind of plugin in Logic, per se. But then that begs the question, do we want to tweak with the audio units API, or is it the hosts that need to handle this? So to explore that further, I was trying this in the JUCE's audio plugin host, and surprisingly, audio plugin host actually does deal very, very well with this MIDI outputs. And I did some digging in the forums, and I found a 10-year-old patch from Lucas Z, and I even messaged him, and he said he doesn't even remember submitting it. But probably because of this, our JUCE audio host actually does support that. So even after that, we look at these different inputs and outputs as these three style of tracks. That's how DAWs try to design it. You have audio track, instrument track, MIDI track. And it gets very challenging to route stuff around. And maybe, so I don't think we want to propose that we should open it all up and allow anything to be routed to anything. I don't think that that is really a solution, because this sort of classification allows musicians to intuitively understand what is this plugin or track supposed to do. And so it's more of a design challenge. We need to think of a user interface or user interaction, how we can make it easy to do this kind of thing. And that's why we think maybe an audio to MIDI could be a style of controller effects. And if we talk about these style of control signals being exposed from DAWs as a controller effect, maybe the hosts can actually expose controller tracks where it makes sense what is being mapped where, it's not just hidden away. Finally, closing remarks. We hope that this encourages more standards for hosts and plugin APIs to deal with MIDI outputs and control signals. And hopefully it also makes it easier for musicians and producers who work primarily with DAWs to do routing-based compositions that Chris was talking about. Thank you very much. You can contact us on these links. And please let us know if you have any questions. Thank you.
Hey, thanks so much. That was a great talk. I just had a quick question about how do you decide, what sampling rate do you go down to? Like in the example you gave, it was like the buffer size, but you might not necessarily always want to do that. Like, what have you found is the good standard for doing that, for getting consistent experiences across buffer sizes?
I can cover this one. I think that with Modular, since you are operating an analog, with FPGAs, you can have high-resolution workflows. We chose a very kind of standard buffer size of 512 and are only extracting a single sample, low-pass filtering it. I think it's up to the context of what you're trying to achieve. It can be low, it can be high. I know that MIDI CC resolution is 7 bits. I think MIDI 2.0, this will be very relevant because it's much higher resolution. Super colliders, control rate is 12 bits, I believe. So it varies. There isn't really a standard there. And I think it's dependent on the problem you're trying to solve.
And only thing I'll add is, if you want a classic compressor, you want sample accuracy. So in that case, you would want the highest resolution from your control signal. But at this point, this kind of mapping will not really make any use of really high rate control signal.
And I think projects like multi-channel FPGA-based workflows really open up huge opportunities for this, because you have high sample rate, you have parallelization. So the problems of threading and overloading existing workflows and protocols is sort of solved there.
Just a quick question about the routing confusions that happen with all the different hosts. has it been considered, or is it just like a real challenge to ship kind of just like a wrapper MIDI driver for Windows and Mac, so that it's like, oh, okay, we'll just pretend like we're a keyboard, and now the user can just select? Or is that just such a mess to deal with that it's its whole other world?
I've tried it. So so the first difference is between Mac and Windows. You could create a virtual MIDI. You can allow your plugin to create a virtual MIDI. But the thing is, the track receives a MIDI buffer which is synced to your time. But if you just start sending MIDI willy-nilly, so you don't have the concept of time anymore, so you have to schedule it if you're going to directly output MIDI to a random track. So it's possible, but is it worth it? We think that's why we think that it's more of a design problem that we need to approach it, that we want to think about control signals as something new instead of trying to retrofit it.
Yeah, and we also discussed even creating a virtual kind of MIDI matrix to solve this problem. And there are other solutions in other design contexts, of course, but it is a sort of open-ended problem.
All right.
All right. Thanks, everybody.
Thank you
We've
very
got
much.
a break. Come on out, get some coffee. Check out the roof for a minute. We'll regroup back in this room at 11:40. So we'll see you back here at 11:40.
I think you're Scott.
Yeah.
Hi, Scott. I'm Sophie. Nice to meet you. How are you doing?
Feel better now?
I wonder if if I could get you mic'd up, and do you want to do a little check of your slides and that sort of stuff? So I'll just take you to the AV desk.
honored and humbled to be here today. Just the presentations so far have been brilliant. I'm going to do something a little bit different. It's going to probably be a little more artistic and more aesthetic. But I hope you all enjoy this. So, my talk is called Microtonal Scale Design in the DAW. So first I'll give you some history about myself and context about what motivates and inspires me to make advances in microtonality. And I'll share with you some recent advances, fairly recent, that have really reduced the friction of using microtonality to tune up multiple software synthesizers in a DAW, which is a very, very exciting, long time coming sort of advancement. And then finally, wish me luck, I'm going to try and do some musical demos. I'm not going to play you beautiful songs or anything, but I'm going to show you some really novel microtonal scale designs that maybe you haven't seen, and I hope it blows your mind. So a little bit about me. My first career was a 3D computer graphics artist at Disney. I worked on many animated features, such as Lion King, Aladdin, Pocahontas, Hercules, et cetera, et cetera. And I was a software engineer that basically made art. And every film, I'd have an R&D budget, and it was my job to come up with a unique look for a film that made it different from other films. So I worked very closely with art directors. Art directors typically are background painters, and the very first thing I noticed working with them is almost every one of these folks had some kind of book about color theory and how to, make palettes, visual palettes. And I've always been a musician, always been making music, and it kind of struck me like, how come I don't have something like that? I just got these black and white keys on a keyboard, and these guys are that's what they do all day long. And so they would map out the emotional arcs of films. Movies are like, Disney is like a hero journey, right? So maybe in the beginning it's happy, and so there's like a beautiful blue and yellow and green, and they would just paint just lines with colors, and those were cues for everyone on the team to understand, like, this is the emotion that we're going for in this moment. Then maybe as you go through the story, maybe something traumatic happens, and there's a fight, and it's anger, there's a lot of red. And so I became very sensitive to color, but also just the idea of, I'm going to take you on an emotional journey. And as I was making music at night, these kind of two things kind of became conflated. So it's very important when you're making an animated feature, and of course many software projects, that you do things with intention, and these things need to be reproducible and they need to be editable. So if I capture an amazing performance, I need to be able to edit it. And if I want to change my mind a year later, I need to be able to come back, bring it back up, tweak it, and re-render it. So that was also kind of baked into my DNA. And that's one of the reasons why I like working in DAWs so much. So when I make music, my creative process is in a DAW, as opposed to, say, like the iOS ecosystem, where it's very performance-based, but you don't have quite the professional DAWs that you have on a desktop. I'm just going to keep going. So what is microtonality? So I'm going to have 2 slides on this. I'm going to come at it a couple different ways. So Johnny Reinhardt is the director of Microtonal University, which is a branch of American Festival of Microtonal Music. This is his definition. He says all music is microtonal music cross-culturally. So you guys may not know this, but you're all microtonalists. 12-tone equal temperament, which I'll just say 12ET from now on, and you're all engineers, so I know you like acronyms, is in itself a microtonal scale. Only it enjoys exorbitant attention and hegemonic power. So we focus on the other tuning arrangements, and I highlighted the word arrangement because I'm going to get more into that. And so my definition of microtonality is, we design scales, and the whole idea behind it is you're arranging pitches in some kind of sequence. Now, in the context of a DAW, that almost always comes down to 128 MIDI note numbers and mapping them to frequencies. When you design scales, you trade off between melody and harmony. Scales, there's very few scales that do both together. I think 12ET is one that does. But as you start designing other scales, you're like, melody's good, where's my harmony, blah. And the most important thing I want to say about microtonality is, I feel like when you play with these scales, I feel like your ears are hearing pitches, but what's really happening is your mind is reconstructing the geometry or the structure behind that scale design. And I think that's the magic of microtonality. So that's why I love it. And again, it's just tying it back to the Disney experience. When I design scales, I use interactive tools, and I'm literally pinpointing emotions in my brain, hopefully your brain as well. So I'm actually sitting there moving the needle and going, that one. Oh yeah, that. And I'm building a constellation or a palette of emotions. So that's my approach to microtonality. Some more context before we start getting into the good stuff. Irv Wilson was a famous microtonalist. His colleagues described him as one of the most intuitive mathematicians. This guy would find musical uses for mathematical objects that had never been done before. And so basically using math to make art, aesthetics. He describes his designs as organic. And so you'll see lots of organic, like farming kind of themes throughout Wilsonic. And then also fractal, because many of his designs are self-similar and they're built recursively. I have a link here, I'll show these slides later, that goes into detail about this conflation of Disney, my time with Disney and time with Irv Wilson, and how that influenced me. Oh, I kind of jumped to this slide too fast. So I've been making microtonal music in a DAW, I like Ableton Live, since 1996. And let me tell you, it is freaking hard. And I think that's why there's just not that much microtonal music or not enough musicians have access to it up until relatively recently. So incredible friction, just really huge barriers to entry. So most software synthesizers didn't respect the MIDI tuning standard. Most software synthesizers don't take SyFaLa files, which is like an old ubiquitous tuning file format. And even those that do, if you're a composer and you got 20 software synthesizers and you want to change the scale, you got to sit there and change it, and none of that could be automated. It's just awful. Odd Sound released a technology called MTS-ESP, and this completely lowers the floor. It's amazing. I can't read that number; it's so big. But Richard James of Aphex Twin was a big supporter of the project, and you've got 63 billion or whatever, the biggest double that you have, more frequencies to play with. And that's exciting. So how does this work? So MTS-ESP is actually a shared library, and plugins in the DAW load the library dynamically. One plugin gets to be the master, registers as the master, and Wilsonic is a master. And it is responsible for owning the global tuning state. So it owns the tuning table, the 128 MIDI note numbers to frequency mapping. The other plugins, if they support MTS-ESP, they register as clients. And so they just pull the master for, hey, I'm playing this note, what should its frequency be? Super lightweight API, very easy to integrate, very low risk. If your soft synth supports MTS-ESP in your client and there is no master, nothing bad happens. You fall back on 12 ET, so it's all good. There is no MIDI communication, that's not necessary, and there's no special routing in the DAW. So again, you just put them in there and it just works. So this is just a screen grab of their website of the software synthesizers that natively support MTS-ESP. Like I said, it's a very lightweight integration. I'm begging you all to put it into your synthesizers. Please, let's grow this list. But if you don't natively support MTS-ESP, but you support MPE, that works too, because Odd Sound provides a client that reads from the master and outputs polyphonic pitch bend. So you can put it on a track as a MIDI effect. And there's some free options as well. So again, I'm begging you, put it in your software synths. So microtonality is more accessible than ever. There's a lot of free solutions. You got to pay for the laptop, maybe MIDI interfaces, but there's a lot of free software synthesizers that support it, and there's free DAWs, so it doesn't have to be expensive anymore. All right, so this is Wilsonic. It's free. It works on Mac and Windows. Still in beta. I'm just getting it up to par with the iOS version. All of the parameters are automatable in the DAW, and this is a big deal because most of these scale designs that I'm talking about, the design itself has parameters that changes the nature of what you hear. And to be able to automate that in the DAW means you can, reproduce and edit your performances. And then also you'll notice when I get to the demos, there'll be a microtonal keyboard at the bottom. It displays metadata. Each pitch displays metadata on how that note was actually created. The keys are colored by pitch, again, harkening back to those art director, abstract color scripts. And then the other thing that's really cool is in real time, this is very lightweight computation. No matter what scale is being played, I can analyze it for certain types of aesthetics. So for example, in mathematics, there's arithmetic means, harmonic means, geometric means. These aesthetics, a lot of people have looked at visually, but they actually work for music as well. And so in real time, we'll actually go in and go, here's a triad, here's another one. And you'll see that on the keyboard in the demos. Okay, so I'm going to start you off easy. So the very first couple, I'm just going to show you Wilson's Garden. This is a curated list. If you're not into scale design, you don't want to make your own scales, but you're interested in just tuning up all your synths to a cool scale, like these first two are for you. And then SyFaLa file support, that's a legacy tuning format, so it's very important to support that. And then once we get past that, I might lose some of you, I don't know. I hope you find it as awesome as I do, but we'll see. So I'm going to show you 3 amazing scale designs. I only got 7 minutes left, so I'm going to get to it. All right, so curated scales. So Irv Wilson, a lot of folks spend a lot of time with him. I spent a lot of time with these folks, Craig Grady, Stephen James Taylor, Jose, Gary John Blah. So we've all contributed to this huge library of curated scales. And so I will show you what that sounds like. Time to wake up. Someone knew that I was going to geek out at this point. Okay, so this is Wilson's Garden. This is Wilsonic. It's in Logic. I'm a live guy. My computer died. Thank you, Ari, for loaning me your laptop. These are all the scale designs. In Wilson's Garden, there's a whole lot of presets. Some people tell me I put too many in there, but I think I love them. And so I'll start you guys off with some archetypes. So the harmonic series. Harmonic series occurs in nature. Any kind of string resonates with modes of harmonics. And also air in a cavity that's resonating, like a flute, something like that. So harmonics are kind of, I think we co-evolved with them. So they're very, okay. So if this was, so this is, I know the number says 2, but it's the second and third harmonics. And that kind of sounds like that's a fifth. If you invert that, this is called the undertone series, it sounds like this. It's like a fourth, right? Now, but we can keep going. So as we go further and further down the harmonic series, this is combining them, but here. So now we're going to go to a mode where there's 3 harmonics. So it sounds like a major triad. This is the inverse of that. And it is really fun, here, I don't need that, to hop back and forth, right? This is, oops. Oh, Logic, okay, sorry, I can't show you because Logic won't let me use my keys the way I want. So let's just keep going. This is a tetrad, so this is the 4th mode of harmonics. And this is the inverse. So that doesn't sound weird to me, that sounds freaking gorgeous. Now, these keep going. You can combine them. You can do any kind of order. I'll go to the pentad and I'll stop and move on because I only have 5 minutes left. So this is the pentad. So yeah, it's starting to get a little more complex. It's getting further and further away from those very simple things that we've heard. 12ET actually does a pretty good job doing those first, all the way up to the tetrad. So that's one of the reasons why it just works. Okay. So anyways, if you just want to explore, I got you. The other thing I'll show you is SyFaLa files. SyFaLa files, there's a massive online archive. I bundled it for you. Here's 5,000 SyFaLa files right here for you. Yes. And this is automatable in the DAW too. So you can say, ooh, I like scale number 1,800. And that's actually an automatable parameter. So you could actually have scale progressions in your song. And again, harkening back to Disney art director like color scripts, emotional arcs of a story, that you could build up some really cool, you could take people places. Okay, now we're going to get into the good stuff. I only have 4 minutes. I knew it was ambitious. Okay. So moments of symmetry. This is Irv's. He calls them nested two-interval patterns. I'm actually going to show you really quickly how 12VT is built. If you ever wondered, like, how did we get 12 tone equal temperament? Like, why is it a thing? So, I didn't save it. Bear with me, folks. It's going to be so worth it. Okay. So the way this works is I'm going to start with the octave. I'm going to start with a fundamental, and I'm going to go to the second harmonic of the octave. So that's my period, that's the interval of which I'm going to start subdividing. If we subdivide it by a fifth, which is actually the third harmonic, you get this. Sounds familiar, right? Now here's the thing. I'm going to keep going. So I took the number 1 and I multiplied it by 3. Now I'm going to take that 3 and multiply it by 3, and I'm going to keep doing that. And that geometry is a chain, right? So that structure that you're hearing is actually a chain of an interval. So this is what it sounds like, oops, with 2. That should sound kind of familiar too, because you kind of heard that before. So now I'm going to go out again. And this time, you notice we're jumping to 5 notes per octave. Well, what happened? If we jump to 4, we would have 2 interval sizes. We'd have 3 interval sizes. It wouldn't be a nested 2 interval pattern, it'd be a 3 interval pattern. Listen to this now. That should sound pretty familiar, right? That's a pentatonic scale. A lot of ancient cultures learned that one. Let's hop up again to the next level. This is 7. So that's a diatonic scale, and so forth. And then we get to 12, and 12 has all of that inside it. So that's how 12-tone equal temperament came to be. I got 1 minute. Okay, there's no way I'm going to be able to cover these. I guess the last thing I think I'm out of time to actually do this any justice. I usually do this talk, and it usually takes an hour, so I knew I was really stretching it. But anyways, I guess I'll just close on Irv Wilson tied a lot of mathematical objects to music. So I just showed you a chain. He also tied Pascal's triangle to so this is the 6th row of Pascal's triangle. You may have, when I was in school, they just said, oh, you do combinatorics with it and you do binomial coefficients, and that's it. But actually, you can drill into this structure. This is a 20-note scale, but inside it, this structure was built by the rows that came before it. So it's like an additive construct. So inside that 20-note scale are actually 6 10-note scales and 6 10 other note scales. And all of those scales are subsets of that 20 notes. And they all have their own structure. What does that sound like? So I'm just spamming the keyboard for now. But check this out. That's row 5 of Pascal's triangle. As you keep going, whoa, too far. Too far. Sorry, I'm not used to these keys. Okay, as you drill into that 10-note scale, guess what's inside it? All the things in row 4. So you have all these 6-note scales and 4-note scales. As you drill into the 6-note scales, all the structures from row 3 are inside it. So it's this incredibly symmetric, beautiful space of harmonics. So sorry, that's the best I can do in the time that I have. I have lots of demos online that I can share with you as well if you want to get into a little more detail and hear more musical examples. So, and with that, I'll just say thank you, and I'm looking for that Cambrian explosion of microtonal music. Let's go.
Hey, Marcus. So you, this is Ari.
Hi, Ari.
You didn't even mention that you did all the DSP for AudioKit Synth 1, and you put Microtonal in the hands of 2 million people on iOS. And I wanted to say, since then, he really wants to get into the DAW, but because iOS is getting the Logic DAW now, how many of the plugins and synthesizers out there do you know on iOS support MTS-ESP, and is that an opportunity for us and other people in the room?
That is a fantastic question. I'll have to consult with the Odd Sound folks on that. They had tried to make it work for iOS. Apple just locks down the devices and makes inter-process communication practically impossible. So, and I believe you still can't load dynamic libraries in iOS. I could be wrong, but that would be a key enabler. So if that were to happen, then this same tech would explode on iOS as well. So I'll follow up with you on that. All right. Yeah. Thanks, everyone.
Hello, hello, check, check. Hi, everyone. Before we start, I just wanted to say thank you everyone for being here today, both everyone here in person and anyone tuning in online. Yeah, it's really a pleasure for me to be speaking here today. For me, it's kind of like the situation of a long-time listener, first-time caller. I've gotten so much out of this community throughout the years, like throughout my time as a student, and then now working in the industry. So yeah, it's really a pleasure for me to be here today. And to start, so my name is Scott Murakami. I'm an engineer at Embody, working on the Pro Audio team, doing audio software development. And today the talk is entitled Leveraging JUCE for Developing Spatial Audio Plugins. And today we'll be focusing on a specific type of spatial audio plugin for virtual acoustic reproduction. So virtualizing a real acoustic space and rendering the playback through headphones. And yeah, today's talk will be sort of general best practices and some features of JUCE to utilize in developing such a system. So first, talking about the motivation, so why there's a need for virtual production tools. So first, mixing on headphones is on the rise. Everyone's on the go these days. There's an increasing amount of immersive content out in the world, streaming platforms. A lot of the bigger companies are starting to adopt and kind of focus on this as well, including Apple. Sort of like a lack of accessible multi-channel speaker setups, because it can be quite restrictive to work with multi-channel audio and spatial audio, because you have the physical restriction of, you need the physical space and this multi-channel array. You need lots of speakers, etc. So yeah, and then also, the ability to mix and monitor in different environments in the box, and to quickly change between these environments to, reference your mix or work in a situation that you're comfortable with, work on the go. So yeah, the question that we ask is, what if you can replicate the experience of working in a physical space with multiple speakers, this surround sound setup, but what if you can work in this environment anywhere and in headphones? So much more cost effective. And as I mentioned, the goal is to replicate real-life acoustic spaces, particularly these with surround sound setups. And yeah, basically just replicate it using only a computer and a pair of headphones. So here we have a real studio. This studio is equipped to do 7.1.6 Dolby Atmos setup. And this is the studio, this is Studio M at Hans Zimmer's Remote Control Productions. This is the lead engineer, someone by the name of Alan Meyerson. And so he's made his mark as one of the greatest movie mixers of the modern era. So his career is quite prolific, spanning more than 4 decades, over 200 credits, multiple Grammy wins. And yeah, he's well known as Hans Zimmer's engineer. So the question begs is, what if you can have his setup, but replicated virtually? So quickly, just to kind of talk about a key aspect of this whole spatial audio world, and a key piece is this idea of personalized head-related transfer functions, or HRTFs. So you see here, there's an image of 6 people's ears. This is taken from the SIPC database. I believe it's from UC Davis. But the key takeaway here is that basically, so the human pinna, or the exterior shape of the ear, is also known as acoustic fingerprint, because similar to your fingerprint, your ear, the shape of your ear, the folds and all that stuff is unique to you. So you can think of this as like a unique filter, and it's a key piece of how we hear sound spatially. And for example, like if a sound is coming in front of us, behind us, to the side, how our ear and our unique filter filters the sound and works with our brain to identify where the sound is coming from is very important. So what this allows us to do is utilizing this HRTF, or PHRTF for personalized for each user, is that it kind of allows us to like sort of trick the brain into hearing sound coming from specific directions, but only on 2 channels. So in the case that's discussed today is over headphones. And headphones are the perfect reproduction device for this because you have isolation between each channel, left and right. Because in a physical space, so for example, if you're trying to do this over 2 speakers, then there's a lot of interference with crosstalk from each speaker. So for example, like what's coming from the left channel, you're going to hear in the right ear and vice versa, plus reflections in the room, which can damage the spatial accuracy. So headphones are perfect for this. And here's just the overall generalized architecture of developing such a system. So you have your input audio coming in. You have your personalized HRTS, which you apply, and this is used to sort of like replicate the sound in space. So you convolve HRTFs at a specific location with where you want the speakers to be set up to sort of simulate like a virtual speaker at each location. You have your overall studio acoustic response. So this is measured for each speaker and listener location. And then also you can apply sort of like if you want to refer to it, it's kind of like an overall room EQ, so like the general characteristic of the room. Plus you have your speaker response. So this is related to each speaker's specific frequency response, so depending on brand, model, etc. Speaker delays, which you need to account for, based on listening position. You have a distance to each speaker, which you have to account for. Since this is for reproduction over headphones, you also have to account for the headphone EQs and adding this sort of like compensation filter for the coloration that each different headphone will apply. And also the last step is kind of more like the artistic aspect of it, of perceptual tuning. So this is done with critical listening by mixing and mastering engineers, and they do the fine tuning from there. And then finally, you have your output binaural spatialized audio. And the key takeaway here is that there's a lot of convolutions. So, for example, each step, like the convolution for HRTF, convolution, the overall studio response, the speaker response, headphone EQ. So just to give you an idea, so per channel, you have your HRTF, your speaker EQ, because the speaker, you might have different speakers, you might not have all the same speakers, and then the speaker reverb. So just to give you an idea, stereo is only 2 channels, but you have 6, so 3 per channel, plus an overall room EQ, plus the headphone EQ. So that comes out to 8 convolutions. Or take Alan Meyerson's room, for example, 716, you already have 41 convolutions. So it's quite a lot. So here's just an example of the measurement process. So in the actual space, at the mixer's listening position, using some sort of dummy head or binaural microphone to capture all these different responses from the speakers themselves, from the room, etc. Playing back some sort of like a sine sweep through the speakers, through the room, capturing the response there. Yeah, here's similar image of the virtualized version of the room, but here you can see in the middle is the listening position. You see there is just lines showing angles to each speaker, azimuth, elevation, distance, which all have to be accounted for. And yeah, so that brings me to convolution. So convolution is the main sort of process that's happening here. And yeah, here's just a nice little graphic from 3 Blue, 1 Brown. So convolution by itself can be a computationally expensive operation. Especially when you factor in loading impulse responses on the fly, which is what we're doing. So, if you want to model multiple spaces or if you want to switch between different headphones, then you have to consider loading these impulse responses on the fly and switching on the fly so you don't get any audio artifacts or dropouts. And yeah, as I mentioned earlier, there's a lot of impulse responses to manage. So proper management and efficient use of resources becomes vital, especially for real-time processing. And as I mentioned, the computational strain, so just convolution process by itself can be expensive. But in this case, it's not just the convolution process itself that can apply this computational strain, but also when you factor in the loading impulse responses and dealing with that on the fly. So that brings me to JUCE's convolution, which has been invaluable for us. Yes, invaluable for harnessing performance. And it helps make loading impulse responses on the fly really easy, as I mentioned, without these audio artifacts, which is very important when switching between multiple spaces. And yeah, so, this JUCE has been very helpful for us, and convolution in particular, for its performance benefits, because otherwise we would have had our own implementation. But also quickly, just to go through convolution, not dig too deeply into the DSP, but just a general overview of convolution and sort of like the convolution theorem of talking about how convolution in one domain, so take convolution in the time domain, it's equivalent to doing multiplication in the frequency domain. So you take an FFT, get your signal into the frequency domain, and multiply from there, which will apply the convolution. So in that case, luckily, JUCE handles a lot of this for us, as well as some other optimizations. And yes, optimization is key to addressing this problem and addressing this market, because I don't know, there's a room full of audio engineers. Audio engineers are always pushing the limit of the computer, trying to reduce buffer size, to reduce latency, increasing sample rates, to get better frequency resolution. And then, as I mentioned, requiring this option or this requirement of needing to switch between multiple rooms very quickly, because as an audio engineer, it's always nice to A/B your mix in different environments. So reference your mix in different environments, but also quickly A/B different environments. So yeah, we need all of this to be handled very smoothly. And then yeah, loading an impulse response into a convolution engine can be quite expensive. And yeah, you can't do this on the audio thread, so it has to happen on background threads. So another sort of friend to the convolution class that is very helpful is this JUCE convolution message queue. So this is very handy. What it does is it allows convolution objects to share background threads for loading impulse responses. Because threads like memory and disk space are a limited resource, and you don't want these to grow out of control. So it can quickly become a mess. Basically, so without using this message queue, each instance of a convolution object will have its own background thread, which it uses to load an impulse response. But using this message queue, it cleans a lot of it up. So it'll use a single shared thread between all of your convolution instances. So what you want to do is you want to create an instance of the convolution message queue, construct convolution objects, and passing in the queue upon construction. So here's just a little code example. You have your instance of a message queue where you can pass in a fixed number of entries. You can ignore my poor choice of variable naming of n. I more so want to focus your attention to the JUCE input parameter is aptly named num entries. And then from there, when you're creating your instance of a convolution object, then you pass in, it takes in this reference to the queue, which will then use this queue to as mentioned, share just a single thread amongst all your convolution instances for loading the impulse responses. So yeah, also quickly, I wanted to touch on JUCE, not just being very valuable for its engineering solutions, but also JUCE in the team management aspect. So the abstraction of JUCE it's very helpful. The modularity aspect of JUCE. And for us, it's a great tool because it's a great learning environment for developers because of both the aforementioned points of abstraction and modularity. And as developers gain experience, they can dig deeper into the lower levels of abstraction. But from a team management perspective, it allows developers of varying degrees of experience to be able to work seamlessly together on projects. Because of these different levels of abstraction, and yeah, so it allows for a very it's a very seamless tool to allow developers of different experience levels to work together and contribute equally on a project. But also, it's a really good tool for more senior engineers to also use to teach more junior engineers. So that is something that we found very valuable too. So yeah, conclusion. JUCE offers practical and effective engineering solutions. And for us, helping to address the challenges presented in developing a virtualized spatial acoustic system with a lot of these loudspeakers. And yeah, as mentioned, the benefits of JUCE extend beyond just engineering. It's a great learning environment for developers and allows for seamless collaboration amongst different backgrounds and of experience. So, yep, thank you. That's my talk.
Thank you, Scott. I was wondering, convolution operations introduces lag between the input and the output. So if in the real-time context, do you face challenges trying to compensate the lag between the inputs and the outputs?
Yeah, so I suppose that's a challenge that we face. It's like, as I mentioned with audio engineers, and especially with mastering engineers, like latency is very important. So yeah, this is something we always have to consider, and just trying to do as much optimization as we can to try to reduce the amount of latency in a system like this. So yeah, this is something that we're constantly battling. Thank you.
Sorry.
Hello, welcome to creating your own singing voice synthesizer, overcoming data collection challenges. Some agenda for today. I'm going to go over the motivation for this talk, a little bit of brief history of singing voice synthesis, some open source options we have to do this, as well as tools and techniques to building a personalized data set and/or voice bank. A little bit about myself. My name is Matt. I'm currently a master's student at Queen Mary University of London, and particularly I'm researching deep learning applications for music and music production. Previously, I've worked at Qualcomm as well as Make as an audio software engineer, and a lot of the material from this talk was inspired from my work at Make. Feel free to connect with me at the links below. I've posted my slides on my Twitter. So the motivation. So today, my goal is to inform both researchers and industry professionals about the choices for custom singing voice synthesis, as well as inspire people to build more public data sets and systems. And the key points here are custom, meaning any voice. It could be your own, it could be someone else's, and public. We want this to be open for anyone to use. So what is singing voice synthesis? Well, traditionally what it means is we take a score, that is notes and rhythms, as well as lyrics, and we have some kind of system that can synthesize a human singing voice based on the lyrics according to the score. And I do want to emphasize a few other speech and voice singing technologies that it's not. It's not the same as text-to-speech or singing voice conversion, which is behind some of the AI covers you might have heard of, voice cloning, speech-to-singing. These are all related speech and singing technology, but they're not the same. And there's some unique challenges that we face in singing voice synthesis. So I'm now going to show a demo of one of these systems in the wild. This was a recently trained model from Porter Robinson. They worked with Vocaloid and created a somewhat robotic-style voice that reflects some of the music in some of the voices in Porter Robinson's music. So I'll show a demo of that. The model is called Puta, and this is a demo song that they made.
So now I sing for you till I can't talk. I've been teaching myself to speak for when the music's not enough. I'm gonna be just like you and never stop. But since I'm made from you, do you think I could be someone like you?
Okay, so now a little bit of history. So in 1962, you might be aware of the famous experiment in Bell Labs. It was using the folk song Daisy Bell. They had a physical modeling, speech, and singing synthesis engine that they were working on, and they synthesized the short song. It's been popularized in movies as well. In the 80s, a lot of people were working on formant synthesis as a filtering kind of approach for singing voice synthesis. IRCOM famously made their chant system, but there were other players here working on formant synthesis. In 2007, Yamaha, in collaboration with UPF, created the first Vocaloid product. This was based on concatenative synthesis, and the way this works is we're stringing together sounds such that it sounds like singing. In 2010, Synzi came up with a hidden Markov model process. This is one of the first popularized machine learning approaches for singing voice synthesis. And nowadays, there's been a few products that come out, such as Yamaha's update to their original Vocaloid called Vocaloid AI, and this uses a deep neural network to do the singing voice synthesis. So some of the products today, we have the previously mentioned Vocaloid, there's Chevio, there's Dreamtonic Synthesizer V, and the way they work is they provide you with this kind of editor, as seen here. You can select, there's a bunch of voice banks you can select from. That's their names for the voices, and there's many different languages. The way it works is you can drag, just like in a DAW, you can drag notes and type in lyrics, and it'll sing those lyrics according to the notes and rhythms that you've typed in this piano roll. So you must be thinking, okay, if we wanted to do a custom solution, it should be pretty easy, right? We should be able to create some kind of data set of our voice or someone else's voices, and then import them into one of these products, and they can figure them out, right? Well, not so fast. It turns out that none of these products have some kind of this capability where you can import a custom data set to use in singing voice synthesis. And this presents us many problems for customization. So if we want to have a solution that uses custom voice, we need both a synthesis tool and a data set. And there are some open source data sets or voice banks that are available online. However, they tend to be very limited, and especially if you're trying to do a language outside of Japanese or Chinese and even English, there's not that many examples. So there's really a big problem if you want to use some kind of custom singing synthesis in a research or commercial product. And even there might be some companies that have proprietary data sets that we can't use in a similar commercial or research setting. So there are a few open source synthesis tools that I'll mention that are pretty powerful. The first one I'll mention is the Utau and its open source successor, OpenUtau. These are both based on the concatenative synthesis technology. And if we were trying to create a data set for this tool, the way it works is we'll have to sing particular sections of sounds that they tell us to sing. We'll label those sounds. The annotations are things like start time, end time, things like that. Usually we don't need too much data for this. Less than an hour can have some pretty good results. And then once we have all this data, we're pretty much ready to go. These tools offer a really nice GUI that we can just import our voice bank, as they call it, straight into it, and it's ready to go and usable. It's been around for quite a long time. As I mentioned before, the technology is a little bit older, but that's also maybe some of the disadvantages. As we're seeing newer, maybe deep neural network models come out, this kind of technology is a little bit old at this point, but it does work quite well. The two other products I'll mention today are both based on deep neural networks. They're both recent products. There's NNSVS and DiffSinger. The way to collect the data for these is a little bit more tricky. We need to have singing, and then we need to go in and label the phonemes. So these are the individual sounds our mouth is making. And this is significantly harder than doing the data collection for Utau and OpenUtau. Also, we need usually decently more data than we would for the concatenative synthesis technologies. And we also need to train the models. Unlike the concatenative synthesis, these are deep neural networks, so they need some kind of training time, and that can depend on our compute resources, which can get quite expensive. The good thing about NNSVS in particular is it does have some community guides and voice banks. And so there are some resources out there we can use to do the system. It's also modular, meaning that it's been created in such a way where pieces of it can be updated over time as more models come out. However, at least at this point in time, NNSVS's quality seems to be somewhat comparable to Utau and OpenUtau, meaning it's quite a lot of effort to get a similar notion of quality. The other system I'll mention is DiffSinger. This one uses diffusion, which is a newer deep neural network approach to doing generation. And this one is great, but it does require usually more data to get good quality and a longer training time. And it tends to be a little bit harder to train, and it can be more unstable. And unlike NNSVS, there are fewer resources, fewer guides and tutorials about how to use this particular tool. And also in general with deep neural networks, as you might know, it can be hard to know what to do when it is not working correctly. It's harder to debug, as maybe we heard from our talk earlier today. I would also like to mention a few other research projects that have come out recently. These are all based on deep neural networks. There's MuseKits, Unison, VI-Singer 2, Natural Speech 2. These are all great projects. However, they're not really usable by the public. There's no real guides or notebooks or ways to train them with their own custom data set. They're all basically in this research paper, research stage, and they'd really benefit from community or commercial support to make them more usable by the public. So I'll first go through the method of how we create a data set for the concatenative synthesis technique. So this is for our OpenUtau and Utau systems. Basically, the first thing we need to do is we need to select which type of voice bank we're going to do. There's choices like CV, which is consonant vowel, VCV, vowel, consonant vowel. There's a bunch of them. I've pointed a link to the rest of them there. And the choices is really a trade-off between the quality of the outputs we want as well as the amount of data we need to sing. As well as the language we want to sing in actually does restrict us to which voice bank we choose. So once we've chosen a voice bank, we can find a rec list, which is basically just a list of items to record. It's based on the type of voice bank we've selected. And the process is quite straightforward. We'll get this rec list. We can use a tool like Oremo and Audacity to record a bunch of these samples. We'll do what's called autoing, which is the annotations that I mentioned previously. And this is like labeling the start time and end time and things like that. We can use setparam as a great tool for that. And then we create some small metadata files, and then we're pretty much ready to go. We can import this into the OpenUtau GUI, and it's ready to be used as a custom singing voice synthesis voice bank. I've provided a link to a tutorial, as well as some public and free voice banks there. Now, for the deep neural networks, as you might imagine, it's a little bit trickier. The real main requirement is to have high-quality singing data, which sometimes can be really hard to get. And then the next thing we need to do is go in and label all the phonemes and the phoneme durations. This can be quite challenging as it requires really precise timing and to make it work well. There are tools like VLabor and Prot that do make this significantly easier. But the first thing we need to do when labeling is we need to determine which phonetic alphabet we're using. There's choices like ARPAbet, IPA, Pinyin, depending on which language you're trying to use. There are a few pre-labeled data sets out there. The best one that I know of is OpenCPOP, which is a Mandarin Chinese data set. But there's very few of these that have these phonetic timings that have been labeled. And then we need to also add some kind of musical score that dictates the notes and rhythms from previously. There's a tool that I've linked to that will do this from your data set, and maybe you can correct some of the errors, but this also is a little bit more challenging to do. I've provided a link to guide on how to do this, but also it's nice to know that this guide also has a link on how to use our finished trained model in the OpenUTAU GUI. So it is nice that we can do some cross-importing there. There's also potentially a way to do this automatically, because you might be thinking this sounds really tedious. Labeling all these phonemes might take forever, and it really can. There is a link here, and I'll talk more about this process in a minute, but it's potentially possible to do some of this process automatically. This link will only do it for Chinese, but it could be adapted to other languages. And then the next thing we need to do is we need to do the training. So once we have our data set, we need to load up the model and do some training. Hopefully we have some kind of GPU, otherwise it might take a very long time. I provided a link to a couple notebooks, but one for the NNSVS as well as Diff Singer. And another important thing to note is it is possible to warm start with the pre-trained model. So what this means is if we have a already trained voice that's similar to the voice that we're trying to get, that's in our data set, if we warm start the model with the initial voice, it will likely train much faster to get to converge on the newer data set. So especially if you're trying to do a lot of these or in a batch process, it's probably a good idea to be using this warm starting to save you a lot of compute time. So as I mentioned previously, maybe it's possible to do some of this labeling automatically. And there are some caveats to this process that I'll mention, but basically the idea would be is if you had a data set of mixtures with different instruments in them, perhaps what we could do is you could do some source separation with a tool like Demux, extract out the vocals. Maybe from there we'll do some segmentation, remove the silences, split it into smaller segments. We can use a tool like PyDub to do that. We'll need to extract the lyrics. There's a tool called Whisper that does this really for speech, but it sometimes can work also for singing. Once we have the lyrics, we need to do this phoneme extraction and alignment. There's a tool called Montreal Forced Aligner that does this. Again, it's really made for speech, but it sometimes can work decently well for singing. And from there, we'll get our phonemes, phoneme timings, and audio files. But as you might imagine, there's probably a lot of errors that get propagated in this process. And I wouldn't necessarily recommend doing this process, at least initially, because of the quality issue, as I mentioned before. We really need both high-quality audio and high-quality labels to get the best output from our deep neural networks. But maybe in the future, this could be a process that you implement, or at least you do pieces of this if you have already parts of this ready to go, and this would speed up the creation of a new voice bank, maybe for an end user. So how do we put this in a real system? Well, from the beginning, we need to get something that takes the score and the lyrics and outputs the singing voice. And from the models that I've presented before, we still don't have a way to take our score data and the lyrics data and convert it into a format that our singing voice synthesis model accepts. So we will need some kind of data processing, maybe like music XML conversion or doing those kind of editor features, maybe some kind of phonemizer, some graphing to phoneme that'd be converting the lyrics to the phonemes. And then if we're doing the concatenative synthesis, we need some kind of resampler method, which will be how do we string together the sounds to make the singing. But perhaps the easiest solution if you're building this into a product would be just to build on top of these open source solutions that already have the data processing built in. They already have scripts and tools that'll do this for you. I do want to spend a minute on ethics, because as we know, generative AI is here, and there is some precedent maybe for stealing voices is wrong. And so I think it's important to mention that if we're trying to use this process on maybe someone else's voices or a famous person's voices, it is a little tricky. And it's possible that there might be some litigation based on these processes, and maybe we're seeing other tools and similar processes coming up with these voices that might be a little bit gray area. Right now, there's really no consequences, but even user-generated content might not be immune. There also seems to be some kind of disconnect between what the users believe about the ethics as well as the developers. Perhaps the users might have one opinion or one thought about how developers are creating our tool or what their concerns are, and developers for these tools are maybe not or more unsure about what the users are thinking or wanting, or how to bridge this gap between what people actually think is going on behind the scenes and what is actually going on behind the scenes. And I think it's important, perhaps, as developers, to explain this process as much as possible to reassure the public or to provide some more context about what we're doing. And perhaps there's a really easy solution for this. As developers, perhaps we can partner with artists to get some of the high-quality data that I mentioned before and have some kind of profit-sharing scheme. Maybe this could be used for demos, multilingual tracks, or fan engagement tools, some kind of licensing scheme. In general, we'd like to maximize the outputs of artists instead of stealing them. So what now? Well, in general, we need more things. We need more research projects. We need more data sets, especially in underrepresented languages, and almost every language is underrepresented. We need easier tools to train data sets and import them. It'd be great if we could have some kind of standard format, because as maybe new research projects come out, we could just easily import our already created data set into this new research project and see how it sounds. And also democratize existing projects. There's plenty of work to be done on the previously mentioned research projects that can just make it significantly more easier for the public. So my challenge for you is maybe try creating a model or voice bank with your own voice and see what amazing results you can get. I'd like to also thank a few people who helped with this talk, and I have some references. Thank you.
Do you find that people that use this technology want to use it more as a collaborative tool or as a standalone, I'm going to replace the singer for everything kind of tool?
I've seen both. I mean, I don't know. It seems this kind of technology has been around for a while. As you see, it's mostly been restricted to people who have been hobbyists. They've been, people who've just been experimenting with creating voices or singing and just trying to see what kind of results they get. But I think recently there's been more interest in using these tools to maybe, because there's a lot of projects making this super high quality, it's been more possible to maybe replicate the sounds of artists. And I think it is at least pretty possible to maybe take some artist work and create a synth out of it. But I think it traditionally was not like that, and it's currently moving more into maybe possibly taking artists' voices.
Hi, thank you for the great talk. Do you have any ideas or comments on how to close the gap between the research that's coming out with kind of, more of a DNN or AI-focused method? Like, do you think the onus is on having the academic space be the ones to take on these open source, kind of like scaling up and transition into actually having repos and notebooks, et cetera? Or do you see that as companies' responsibilities, or, where do you see that progress happening?
Yeah, it's a really good question. I mean, at least from what I've heard, it seems like the academic institutions are quite under pressure just to put out a lot of these research projects in the first place, and they really don't have the resources necessary to spend on productionizing these code, and we've had to rely on maybe third-party people on their own time creating these notebooks. I personally believe that, at least in this current situation, we just need maybe more, at least good people from industry or people outside of the academia creating these kind of production environments. Because I think, from the academic environment, it's sometimes it's really hard to take your paper that you've thrown the code together and turned into a product. But I think in general there just needs to be more collaboration. I mean, that some industry person will put out this great paper and great code, and then just leave it and move to the next project. So I guess that's my general recommendation. But I think the onus is more on the industry for now.
And maybe one quick comment. This may sound naive, but have you looked into using like old karaoke machines as a format for timing information and
Yeah, actually, so there is a data set out there called the Dolly data set that actually has a bunch of this data of like people singing to karaoke machines and doing this. I think currently the biggest problem with that is just the quality. I mean, if we want to get high quality singing data, usually people either singing on their phone or some bad microphone tends to not be that great. But in terms of the timing, there's a lot of stuff there, and there have been people who've tried to do singing systems based on that kind of karaoke system. That's a great point.
All right, thank you, Matthew. And now Nick.
Yeah, I did mention that one.
You mentioned that one.
Yeah.
How do you pronounce P-U-O-T-A?
Pota, I think.
Good. For those of you Spanish speakers in the audience, we're safe. So let's see. Yes, today I'm going to talk about how I'm using JUCE to port GeoShred to other systems besides iOS. I'm Nick Porcaro here, and I'm one of the main instigators of GeoShred. There are a couple of others in the audience, Julia Smith and Pat Scandalis. So it's really good to be in San Francisco doing this. This is kind of my home turf. Anybody's got any questions, let me know. And the Commonwealth Club, it's just an awesome place. Anyway, in case you don't know what GeoShred is, here's a quick little demo. Let me make sure I got the audio going in the right place. Yeah, I think so. And of course, the internet's not working. Great. Well, that's why we've got backups. Let's see. There we go. Let's just play this. Yeah, so basically there's three main synthesizers that are in there. Julius's guitar model, which you heard last, and then there are the GeoSwan models, which are from audio modeling, and then the Nada models, which are from our buddy Sutu in Bangalore. And it all runs on iOS, which is great, except that it's stuck on iOS, which is not so great. So I started looking at, how am I going to, and there's a lot of UI in this thing. You can only imagine we got something like, 20 instruments in there right now and about another 10 coming in. Each of them has got a complex UI. Most of them were developed with, then there's a whole bunch of effects boxes and whatnot, and those things were mostly handcrafted in the interface builder. So it's a big job to try to get all the stuff in JUCE. Luckily, this is an example of what one of the UIs look like. This one was actually written in JUCE. And actually, this is a sneak preview of a new feature, a strumming surface I'm adding in GeoShred. And this is a JUCE UI. And this is an example of the first version of GeoShred running on Linux. And there it is running under Reaper. Okay, so again, we want to make this thing portable so we can get on Linux and Windows and Android and Mac OS, because I'm greedy and I want to make a hell of a lot of money. No, just kidding. We want to just do good and get this beauty out in the world. But anyway, so plug-in GUI magic is the trick that I'm going to suggest, or something like it. I know Tom's working on doing some stuff with web UIs that could work inside of a web browser. This is a similar kind of idea. You basically just have a big XML tree, and the idea is you basically have this big XML tree, and then you could turn it into code. And Daniel Waltz is the guy to thank for this, who did plug-in GUI magic. Now, Daniel's got a great example on YouTube that I put in here. He did a couple of videos in the audio programmer channel where he showed plug-in GUI magic, but it is fantastic. But the problem was it's designed for one audio processor. We all know what a JUCE audio processor class is, and I've got something like 20 or 30 of them. How am I supposed to deal with that? All right, so that was the number one problem. How do I have multiple editors, Daniel-style editors in GeoShred? Number two, how do I make it fast enough? Because, well, frankly, it wasn't fast enough, so we had to do some optimization. And then the other thing is, it's awfully cool for. I want to still be able to use it for all the the stop boxes, but then I want to be able to use it for the main app and for the control surface editor. In GeoShred's got this control surface editor. You could basically just, well, I don't know if you could there it is. It's all those sliders at the top over there. And what I want to be able to do is not just have that stuck in this grid with only 6 or 7 things. I want to be able to have a million things up there if you want, or as many as you can cram in the damn screen. So I want to have completely flexible UI design. I want to get somebody like Peter Drescher to design this for me, or a web designer, or somebody. I don't want to do it all myself. I got other things I want to do. Okay, so that's the plug-in GUI magic. That's the motivation why I went to something like this. I tried doing it myself. Listen, there's that whole proportion you do with laying out boxes. I call that drug dealer math. It's just not interesting. This proportion here, this proportion there. It's like it gets old really fast. So you need something like a flex box, right? So I'm kind of pounding this a little bit because it's arduous when you have a lot of UI to try to lay those things out yourself. You just don't want to do it. So, all right, so that's the UI thing. And then getting into the JUCE stuff, David Rowland did a great talk. I think it was 2017 about value trees. We use that extensively. And again, plug-in GUI magic, we leverage off the Flexbox and Grid. It's a CSS web standard, so anyone that knows CSS should be able to do it. But not only that, there's a drag and drop GUI editor, so you don't even really need to write code. So the main aspects of GeoShred that we're porting, there's a preset editor, control surface editor, there's the keyboard, and Julius has got a great start on the keyboard. Sort of this grid, this isomorphic keyboard. Romain actually did one not that long ago as well. Well, actually, it was a hell of a long time ago, but it was a cool early experiment. There's also, you could have a conventional keyboard and plug-in GUI magic. I wrote my own completely stylized keyboard for this Destroy Circuits, All Circuits project that I'm doing. And then, so once you've got all these components, you can, you've got GeoShred back together. Now, if it's running on the Mac or on Linux or on Windows, you're going to need something to control it with, like a GeoShred, which is also a great MIDI controller. All right, again, the preset format. Let's see if the internet's up for me now. It's going to give me a break. Yeah, okay, thank you. This is what it's like. It's basically, it's attributed XML. This is one of Daniel's magic files. And Daniel, if you're out there watching this, you'll wonder what the hell is UX button. Well, it's a text button, but I just kind of juiced it up to make it easy. Excuse the pun. To make it easy to have images in there and do other kinds of things and make it blink and do somersaults or whatever I want it to do. Make it bring up other sorts of menus. Okay, so each GeoShred preset now, you can just edit it by text. Just pop into Emacs or whatever, or Xcode, and then that's a layout file, and then the actual Signal processing and MIDI processing looks like this. And you essentially have a bunch of processors laid out and then a control surface. So the idea is I want to have user interface that generates this file and reads from this file. Thank you to Jutton, who turned me on to the idea of having multiple audio processors in one loop. Thanks again for that one. So that's how GeoShred works. It's a plugin, but it ticks a whole bunch of other audio processors that are also like plugins. So that's sort of the key secret of the signal processing in this thing. And that's just what I was talking about. This is Jutton's main loop over here, I'll call it. But then, boy, I'm just giving you some really cool secret here. Here's how you tick a bunch of audio processors and then mix them and run them through an effects chain. One page. Now, of course, in reality, it's not that simple. But and then Eyal Amir, a shout out for the build system. I know you're around here somewhere, Eyal. CMake, you got to have CMake. And then how the heck do we get Linux running dual boot? I leaned on Lee Smith for that one. But the key thing is if you got an old Mac, find the refined boot manager and ext4 for your partitions, and then just go crazy downloading packages and ask me if you really want to do that. Okay, I talked about the three instrument types again: Geo, Swam, Julius guitar, and Nada instruments. So this guy Sutu Nagaraj basically approaches us with this killer demo. He studied all of Julius's work and did a fantastic set of Indian and other South Asian instruments, some Chinese instruments. There's a lot of them coming. And we integrated them, he and I, into GeoShred as these audio processor classes. All right, so now I'm going to just get into it a little bit. I'm just going to go even more off script than I already have. Okay, so this is it. Am I getting audio out of it? Oh, you know what? That's the first thing, Daniel. How you change a button to make the audio go somewhere else. I want it to go there. Okay, let's see if that works. There we go. So this is a Nada cello. All right, this is sort of an early version of what GeoShred might look like. And like I was saying before, it doesn't even have to have the GeoShred keyboard. It could have a regular keyboard. The editor, the control surface layout can be anything. So the main editors, again, was like the preset editor. So now basically, you just have a big, sort of value tree. Whoever did that value tree example, thank you. I sort of zhuzhed that up a bunch. So here we basically have all the signal processing, and if you want to look at one of these stomp boxes that Pat is so fond of, oops, how did I do that? Well, I'm just using my iPad to control this thing right now. It's listening to MIDI in. So I could basically, I got the stomp box up here, there. Oh, so cool. I'm on a computer. I could just move windows around. It's not hard, and everything is just free flowing. So that's how the processing chain looks. Now, say I wanted to add another control. I just drag it onto there, and boom, there's my control surface editor. Now, say I don't like that knob, I could basically edit the layout. Now, this is Daniel. This is your toolbox running live. So basically, the editor, the live editor and the toolbox editor can run at the same time. So say I don't like the way that slider looks. I could, instead of making it a gold knob, I could make it a blue knob, or a Foley's finest knob. What the heck did I actually make it? Blue, white. I did make it a Foley's finest knob, but I will make it blue. Now, there we go. Because we're right near the bay over here. It's just sort of blue per certain times of the day. Anyway, so basically, you see, I can basically just drag in components from the patch, organize them any way I want, put graphics back there, put a video, whatever we may want to do. So that's how this thing is going. We're going to go back to the audio. Again, in case you think the UIs for these instruments are trivial, I'm going to show you that they're not. This is just something we did in our spare time because we were bored. Okay, there's a plug-in GUI magic editor out the wazoo. Okay, it's a mini Moog. It's a mini Moog and a cello at the same time. So you can see I got the fancy scope. I've got knobs here. I've got 2-state buttons there. I've got chicken heads. Turning the scope on and off, the MIDI settings. So that's where we're going with this. The idea is you basically just use that. Now, something like what I showed you for editing that control surface button, turning it gold to blue. That's how you build these things up. You'd build them for the individual processors. You'd build them up outside of the preset editor, and you just throw them all together. I think that's kind of mostly what I wanted to say. Let me look at this. Yeah, okay, so, I know there's a couple of other small things. I'm not sure when this is going to be available for Windows and all these other cool things, but I do know there's a Mac Catalyst version that will be available pretty soon, and you can always download the current GeoShred on iOS and, hit me up with any questions. Let me show you the Catalyst version real quick. That's it. So that looks very much like GeoShred on iOS, but it's running on the Mac. And then, of course, it'll run inside of Reaper, and it'll run inside of Logic. This little Reaper project's kind of hilarious because it's got... I should just buy this thing. How embarrassing. I mean, really now, they're not asking that much money. All right, so I got 2 versions of GeoShred running in this thing. There's the GeoShred JUCE as a VST3 plugin, and there's a GeoShred AUV3. they seem to like each other. So that's kind of where we're going with this, and I'll just let it go there. Anybody got any questions? Fire away. Yeah?
I'm here.
Can anybody suggest a different way to do the UI conversion? Tom? Maybe somebody should give the plug-in GUI magic a little bit more love. I'm willing to, apparently. All right. Anyway, just hit me later if you need anything. All right. Okay.
Right, it's lunchtime. There's 2 lifts going up to the rooftop. There's also stairs, so it might be quicker if you're feeling fit just to run up the stairs. And I'll be able to show you where that is. And we're just calling the lifts now. Please squeeze as many people into the lifts as you can. Thank you.
Okay, everybody, welcome back from lunch. Let's get to the right slide here. How about if we go here?
All right, welcome back. I hope everyone had a good lunch. Today we're going to start our afternoon off right, and that is with some math. We're going to be having some fun with functions, and I'm going to be showing how to find custom fast math approximations using popular Python packages. I want to thank ADCx for having me. My name is Ryan Robinson, and I'm an independent developer from Southern Oregon. And I think my background is maybe a little bit non-standard. I did spend 5 years teaching high school math before I got into software. And I don't know if you've ever tried to teach math to high school students. They're not the most receptive crowd. So I'm certainly excited to be talking to some people that will maybe be a little more interested in the topic today. I work on mainly iOS and Android apps, and I've been fortunate that one of my apps, AutoPad, has done pretty well. It's found a good following in the church music community. So I'm super excited to be here. What I'm going to be talking about is showing how to use popular Python packages to find custom fast math approximations. I'll have time to do just a little bit of high-level theory. I'll show some Python code examples, and we'll do a little bit of kind of compare and contrast, evaluation, and benchmarks and such. So first, we might want to ask ourselves, why would we even want to do this? We know that the use of these special math functions is extremely common in audio. For example, if you have an oscillator, you'd be calling some kind of periodic function, like sine or cosine. Nonlinear processing, we're using a lot of hyperbolic tangent. We do unit conversions. Pretty much any kind of special math function that you learned about in high school, we're using it, and we're using it quite a bit. And these things aren't necessarily cheap to compute. The standard library will have to be pretty robust. You need to be able to handle any kind of input. And obviously, you want full precision from some kind of standard implementation. In audio, though, we might not need all of those features that the standard library provides. Our inputs are quite often in a known range. For example, if you have an oscillator, your phase would be maybe between 0 and 2 pi. We may not need full precision. We're also under pretty tight time constraints. Anything we can do to speed up our code, we're generally happy to do. And we also might want to vectorize things. There's a lot of opportunities for parallel processing. So if something is pure arithmetic, we can use SIMD instructions pretty easily for those things. So what we will be doing to develop a fast math approximation is finding a polynomial or rational function that approximates the kind of special function that we want to know on some kind of defined range of inputs. And obviously, this huge subject area, and I'm only going to be able to scratch the surface today, but I'm going to show Taylor polynomials, Pade approximants, and minimax approximations. And then we'll just spend a little bit of time kind of seeing how we did, comparing and contrasting these three methods. So first up is Taylor polynomials. And if you took calculus, you know that you're trying to find a polynomial whose derivatives match the corresponding derivatives of your target function at your central point. That would be given by this expression here. We know that a polynomial is just a sum of powers of x. And in this case, our coefficients are just the sort of values of the successive derivatives at that point A. And we're just kind of dividing by that factorial and factorial because we have the successive applications of the derivative. These series go on forever. And we're just going to kind of terminate it when we get the desired precision. So here's the first 4 terms of the Taylor series for sine of x, just to kind of see. And if we just show this graphically really quickly, thinking about building up an approximation for sine, starting at the point 0, we can start by approximating the slope of our function. And that would give us our first term, x. And as we kind of match higher order derivatives, we can see that our approximation is going to be tracking with the true sine function for longer and longer. And as we add more terms, things get better and better generally. So to do this in Python, I am using a package called SymPy, which is a symbolic math library for Python. And it knows all of those rules from calculus, and it will just kind of do it for you. And so what I've defined here is just a simple function called getTaylor, where I can pass it an expression, a variable, a central point, and a degree. And then what we're just going to do is call series on our expression. And then we kind of have to do a little bit of housekeeping. It kind of bundles up the higher order terms of the series, and we remove those. And then we expand our polynomial. And then there's a bit of finessing to kind of get the floats out. But then we just return, in this case, I'm returning this NumPy polynomial. And we can use it like this. And I just want to give a little bit of a disclaimer. You know, these are kind of examples meant to be kind of showing the pros and cons of each method. I wouldn't necessarily recommend just using this kind of 9th degree Taylor polynomial. You'd certainly want to think about the pros and cons of each of these methods, and we'll get into that as we kind of go on. But this is how we would kind of use that code right there. I think a couple interesting things before I go on is that the SymPy library, it actually kind of interprets things as symbols. So we're actually just passing sign of x, kind of how we would write it on paper, which is a little bit different from the other libraries, such as NumPy, that we'll be using. So these are the coefficients we get. I mean, not too much to say, except that it should be fairly easy to take these things and put them into a C or C++ function. One thing we'll note is that we do actually have a bunch of zeros, and those come from the symmetry of the sine function. We saw that the Taylor series only has odd powers of x. So that's actually pretty nice. It will save us, we can essentially skip those terms when we go to compute this. And if we look at our error curve, it's fairly consistent with what we kind of expect from the theory, where we stay, and I'm looking at relative error, by the way. We stay very close to the true value, and near the edge of our input range, we kind of steer off course rather quickly and rather abruptly. So that's something we'll be looking to improve on with these other methods. So just a quick summary, I would say the pros of using a Taylor series or Taylor polynomial is that we only have multiplies and adds, and we get some benefits from symmetry in the case of functions like sine. But we do not have consistent error along the entire input range. And also polynomials in general, their end behavior isn't great for this because as you plug in larger and larger values of x, they tend to explode to infinity. So it would be nice if we could come up with some solution that doesn't kind of dramatically explode to infinity. And we'll see how to address that with actually the next topic, which is Pade approximants. And Pade approximants, you start by actually taking a Taylor polynomial and setting it equal to a rational function. And that's what we have here. The coefficients in the Taylor polynomial, these would be known values. And in this case, these a's and the b's would be what we're looking for. And it's actually fairly easy. It's just a lot of kind of tedious algebra. We move this denominator up and we multiply everything out, and then we end up with kind of a huge linear system where we can kind of match up our coefficients of corresponding terms. To just show this graphically, this is another example with sine of x. We have a polynomial for our numerator and a polynomial for our denominator. And taking those as a rational function, we see we get some pretty nice tracking for this example in a fairly narrow range. But I want to compare it with the Taylor series. And the thing to note here is that when we take a look at the kind of corresponding Taylor series, when the Taylor series does pull away from the sine function, it pulls away much more quickly, and it kind of shoots to infinity at a much faster rate. And that's because rational functions, they just have nicer end behavior. They're not going to be exploding to infinity as fast. So to do this in Python, we use SymPy for the Taylor series. We're going to use SyPy for a Pade approximant. And SyPy actually just provides a Pade function that we can just use. We do have to be careful to pass our coefficients in the correct order. And then we just tell it the degree of the denominator polynomial that we want. So here's an example of me using it. I get my Taylor series, and then I just pass those coefficients in. I'm asking for a 4th degree polynomial in the denominator, and then the numerator just sort of adds to make 9 in this case, so we'll have a 5/4 degree Pade approximant. And if we look at the coefficients, again, not much to say. We would take these, put these in some kind of C or C++ function. And we still have those zeros, which is pretty nice, which means we're still getting those benefits in the case of sine, of like the symmetry of the function. So that's pretty good. And if we look at our error curves, it's pretty consistent with what we would expect from the theory. The Pade approximant is able to hold more closely to the true value for a little bit longer. And when it does diverge, it kind of diverges less dramatically. So I would say that is definitely an improvement. We have better end behavior because we're using a rational function, and we're holding more closely to the true value for longer. However, we still don't have a consistent error along the entire input range, which we'll kind of address with the next method. And this does require division, so it's not quite as snappy as maybe just pure multiplies and adds. But I think the division is probably worth the trade-off, or worth it in this case, and that's certainly what the JUCE developers felt. They have a great little header that's a fast math approximations, and all of their fast math approximations actually use Pade approximants. So you're not going wrong if you're doing it the way JUCE does. And just for comparison, their Pade approximant for sine is degree 7 over degree 6. So just to kind of give you an idea of where my examples kind of fit in terms of the things that would actually be used in production. So to finally address the issue of kind of the uneven error or inconsistent error along the input range, we're going to turn to this method called minimax approximation, which what we're trying to do here is find a polynomial that is minimizing the maximum value of some error function along our input range. And what this does is it kind of takes all the error and forces it down into this oscillating curve where we're moving up and down between a high and low value. And there's an iterative There's an iterative algorithm for doing this known as the Romain algorithm, but I'm actually going to use kind of a general purpose optimization package for this in Python. We'll say a little bit about error. First off, the benefit of the minimax method is that you're always going to know kind of the worst case outcome for your approximation. That's what we get by minimizing the maximum value of our error function. And then we'll kind of just think about the error function we might want to use. In this case, and from my reading, I think the way to go is relative error. What that effectively does is it normalizes our error, and it makes it easy to kind of guarantee how many bits of precision we're going to be getting out of our approximation. If you take two normalized floats where you have the same exponent on the twos, it's really easy to just look at them, see where the bits differ, and then you can say, okay, I'm always going to have at least 10 bits of precision with this approximation. So to do this in Python, I'm using a package called CVXPy. It's kind of a general purpose convex optimization package, and it's certainly up to the task. It gives us freedom to choose our error function and set our constraints. So I'm going to just do a little bit of housekeeping at first in this function. We're passing in a function that we want to approximate, the degree of the polynomial that we want out, and the low and the high end of our range. And then we're just going to create an array of input values for our function, and then we're going to compute the true y values. Since we're going to be dividing by y to compute relative error, we're going to remove y values close to 0 and hope for the best. Here's the actual CVXPy code. This is just a continuation of that same function. I create a vector of coefficients for my polynomial. This is a CVXPy variable. And then I'm going to go ahead and compute a big matrix, which is the kind of x part of my polynomial. For every input value, I need to know x to the 0 power, x to the first power, x squared, and so on. And then I just create my objective, which is the quantity that I'm going to be asking CVXPy to minimize. We do some matrix multiplication. We subtract our true y values and divide by the y values. And then taking absolute and max kind of reduces all of this to a single number, which is our maximum relative error along the entire input range. One thing that's kind of fun about CVXPy, it's kind of nice, is that we can add constraints. So if our function has special values that we want to try and preserve in our approximation, we can add those, and the solver will do its best to kind of accommodate us there. Then it's just a matter of defining our problem and giving it that objective and the constraints. And then we just call solve. And we're going to return these coefficients. The vector A now holds the optimum coefficients for our approximation. So doing this with a 7th degree minimax approximation, these are the coefficients we get out. The only thing to really note here is that now we're not getting those zeros that come from the symmetry of the sine function. And that's because we're kind of using those extra coefficients to help kind of normalize our error along the input range. So I think, before pros and cons, if we look now at our error curve, we can see that we have this characteristic error curve where we're oscillating up and down between a high and a low value. So it's pretty nice. The error is controlled within the input range that we want. So I would say there's a lot of benefits to using the minimax method. It's fairly customizable. Your error, like I said, stays within well-defined bounds along the entire input range. And any of the sort of end behavior issues that come from using a polynomial are pushed outside of that. We can't take advantage of symmetry, and working with a solver, it can be a little finicky, the numerical methods. You kind of have to work with it to get it to give you what you want sometimes. If we now compare the relative error of all three, we can see that our minimax approximation stays pretty close to 0 throughout the entire input range, so that's pretty nice. Looking at the bits of precision we get out of our functions, and I'm just using these kind of simple calculations here. Our Taylor polynomial and Pade approximant do kind of suffer at the edge of the range. In the worst case, the Taylor polynomial doesn't even give one bit of precision. But the minimax approximation of degree 7 is, in the worst case scenario, able to give us 10 good bits, averaging 11. And if we take a look at absolute error, it just gives us a little bit more of the picture. We can see that the minimax error is oscillating up and down. Looks like I got to wrap it up. Let's just do a benchmark. This is just throwing these things into C++ functions and going to QuickBench. And we can see that we do get some nice improvements over standard sine. And I will just say these are all pure arithmetic, so it should be fairly easy to use SIMD instructions with these functions if we want to do that. And so just to wrap up, I know that was kind of a lot. We've even just amazingly barely scratched the surface. I showed Python examples for generating custom fast math approximations. I do have this code on GitHub, which I think is hopefully available on the Zoom event page. And we discussed pros and cons and compared error curves. And I would just encourage people to kind of mess around with this stuff, have fun tinkering, and maybe you can pull this in to your code and speed up some of your calculations. Thank you.
Are you familiar with constexpr and possible ways of, say, computing your coefficients at compile time for your functions?
Yeah, I have not tried to do this personally, constexpr, but I have messed around with constexpr and doing some kind of filter coefficients. So it certainly seems possible. I have not explored that personally.
Oh, just real quick, do you find that adding constraints, especially since it is sine function, at pi over 2 and stuff like that,
Yeah.
Greatly affects the error, or does it tend to be somewhat minimal effect?
You know, every constraint you add, you kind of lose, I guess you could say, a degree of freedom in terms of you have to use that in the coefficients to accommodate that. So I wouldn't say it's dramatic, but certainly you can't go to town with adding constraints, right? So there's certainly a balance, and there's pros and cons to be weighed with all the methods.
Very quickly, did you look at rational Ramez exchange approximation, rational Chebyshev approximation?
You know, I looked at that. I couldn't get it into the talk, but I think it would be reasonably easy to kind of modify the CVX-Pi example to do that. I haven't done it yet. I couldn't get into the talk. Thank you. Oh, sorry.
A trip on that?
Oh.
There we go.
Ooh. Save the laptop.
Okay. And can you hear me? Okay. So I'm going to talk about MIDI polyphonic expression, the profile for MIDI 2. I'm not going to talk a whole lot about MIDI 2, but I'm going to talk about MPE in general. So some housekeeping. This presentation can be found at moforte.com/news. And if you just go there, you'll see the presentation at the top. Okay, just a little bit about me. I've been in the Silicon Valley for 40 years, and I built my first polyphonic or monophonic sound-making synthesizer from a kit at Radio Shack in 1970. I used to gig with an ARP Avatar guitar synthesizer, and over here you can see these are some simulations of vibrating strings and membranes that I did back in 1982, and I was a researcher at Stanford at Karma, and I'm currently the CEO, CTO of MoForte, and the chairman of the MPE subcommittee in the MIDI Association. So MPE, I'm going to talk really briefly about it. It's a set of conventions. It's built on MIDI 1.0, and it enables independent expression for each note or row. It's already supported by over 250 hardware and software products, and it really has legs. It's taken off. One of the questions that I often get asked is, well, MIDI 2 has per note expression. Why should MPE even be brought over to MIDI 2? And the reason for that is there's so many products out there that already have MPE support, and the effort to get those products to migrate to MIDI 2 using MPE 1 is really incremental as opposed to starting from scratch. The spec for MPE was ratified in January of 2018, and a clarification revision was put out in April 2022. If you get my deck, you can take this link to go directly to the spec. And there's a MIDI 2 profile that's in the works, and it's expected to complete in 2023. Okay, MPE roots. So it's similar to how guitar controllers have been doing per string control for the past 35 years. And back in 1999, Lippold-Haken did a controller. It's a very nice controller still that has X, Y, and Z expression. It's really a precursor for MPE. And Keith McMillan, who you can see over here with Roland Lamb and Roger Lynn, did a thing in 2010 called the Cabo. And he independently came up with an idea for independent expression that he called AIM in 2014, roughly the same time that the MPE spec was coming together. The Linstrument, you can see Roger Lynn down here with Harriet Bevan. The Linstrument is really the first instrument that realized MPE, and Roley also adopted MPE for the C-board in 2014. There's a picture of Roland Lamb with one of the original C-boards. So MPE in a nutshell, there's not a whole lot to it. It's derivative of what's called MIDI mode 3, MIDI mode 4 in regular MIDI 1.0. And there's a special RPN 6, that's basically used to communicate how many channels and where a channel split might be in the MPE implementation. And then RPN 0 is used to set the pitch bend sensitivity, because MPE makes extensive use of very wide pitch bend ranges for pitch fluidity.
So it can either be channel per note, so every note gets its own channel, so you're rotating through channels, or it can be channel per row or string, like on the Linstrument or like on my product GeoShred, where every string is on its own channel. There's 3 special controllers that have been allocated for expression. There's one for X expression, which is almost always pitch bend. Rolly calls this glide. There's key Y, which is CC74. It's used for sliding forward on a key. And there's key Z, or channel pressure, which is used for pressing into a key and generating expression. There's also a manager channel, typically channel 1 or 16, and that can be used to globally send expression messages to all of the voices that are currently playing on all channels. There is a low-high split. It's not used very often, and it's not clear if that mechanism is going to be retained in MIDI 2. Okay, the importance of pitch fluidity. So pitch fluidity is an expressive metaphor. It's used in musical performances around the world. It's really important in South Asian music, in Turkish music, in a lot of different musical traditions. And MPE directly addresses pitch fluidity by supporting per note multi-octave pitch bending. And so, for instance, we see with some of our customers who are in India, slides that go a whole octave as a part of the expression mechanism. Though it's not a part of MPE, pitch rounding is super essential to enabling performers to play in tune. If you didn't have pitch rounding, you could be sliding to a note and you could stop there and you might never ever get in tune. And further, you might not be in 12-tone equal temperament. You might be in, for example, 52 ET, which is used in Turkish music. And when you get to the note, it's not perfectly in tune in Western music. And so what pitch rounding does is when you get there, it brings the note perfectly in tune with the temperament that you're currently playing in. And that's super essential for performers to be able to play in tune. Okay, I'm going to talk a little bit about modeling synthesis and MPE. So there are sample-based synthesis techniques, but there are also model-based synthesis techniques. And what's great about models is that they're parameterized and can be musically expressive through the parameters. And until recently, the options for expressing musical parameters were limited. It was basically the mod wheel. If you had a PC-1600, you had some sliders and the pitch wheel, but there was not a lot of opportunity for expression. So what MPE did is it created a standard for individual expressive control for every note or for every row, if you have a row-based metaphor. So MPE plus modeling synthesis, this is a really big deal. And when we get to the video examples, I think you'll see the degree of expressivity that's possible. It makes a whole new generation of controllers possible, whatever the instrument creator wants to dream up. It also offers an expressive performance mechanism for parameterizing synthesis. So it could be physical modeling, which is something that we do a lot of. It could be virtual analog, like what Herrit does over at Moog. It could be FM. Anything that has knobs that you can control, you can now bring that expression to be controlled at a per-note basis. Together, MPE and model synthesizer, model synthesis is greater than the sum of the individual parts. So here's some MPE controllers. I just looked around what's available. There's a lot of MPE controllers now, and some of these are really fun to play. I just got one of these Osmos, which is this one right here. It's covered with LEDs, and you can program it to be almost anything that you want. Excuse me, that's the Airy Touch. The Osmos is the one on the bottom. That is also an amazing controller. And all of these controllers are really amazing controllers. Okay, here's some modeled synths. This is just a handful of the synths that are out there. If you get this deck, Roger Lynn has a list of about 200 products, over which are half are synthesizers, and Rolly has a list of products as well. Okay, demos. This is a reel of expressive performances that are being done using MPE. Most of these are videos that we had around, so they're mostly done with using GeoShred as an MPE controller, but they could have been performed on virtually any MPE controller. And let me go ahead and play this reel for you, and I'll give you an explanation as the reel plays. This is Gerald Peter using a 3D Touch iPhone. He made a pretty well. This is also a 3D touch iPhone. It's a saxophone with overflow. This is Jordan Rudess and Mark Wood, a real violin versus a model violin. This is Scott Barenfield. He's doing kind of a fusion piece. He's using 3D touch on his iPhone to do the pressure expression. This is Gerald Peter. He did sort of an orchestrated brass arrangement. This is a group in Italy using feedback distortion guitar model, using MPE to express it. And here's a cello, again using 3D touch. This is using MIDI mode 4. It's a multi-temporal example. Every row is a different synthesizer with its own expression. It's Mahesh Raghavan from India. He makes extensive use of this fluidity. Finally, this is Jordan Rudess. He's using a real piano with this, but he's got an expressive cello and an expressive oboe. Go back to the deck. Okay, so MPE for MIDI 1.0. I'm just going to go over briefly what implementers have to think about. There's not a lot that they need to do. They need to decide if they're going to do channel per note or channel per row. There's a message that you have to send, RPN6, which describes the number of channels that are being used. There's a pitch bend sensitivity that needs to be set. It's by default it's 48, but it allows the pitch fluidity that's found in MPE. The default MIDI mode for MPE receivers is channel per note. So developers might not need to do anything if they're doing channel per note. And then you just need to send your regular channel voice messages, note on, note off. And for expression, if you've built a controller that has 3 dimensions of expression, you send pitch wheel, you send channel pressure, and you send CC74. It's all standard MIDI 1. Okay, and now we'll finally talk about MIDI 2. Again, I'm not going to say a lot about MIDI 2, but MIDI 2 is a dialogue between senders and receivers. And one of the big challenges with the current MPE is there's frequently mismatches between the sender and the receiver. And part of that is because there isn't a dialogue that's going on. So the main thing that in MIDI 2 is added to MPE is that the MCM RPN6 is replaced with profile details inquiry. And so the sender says, hey, these are the channels I want to use. The receiver says, I can use those channels, or I can't use those channels. Here are the channels I can use. And the sender says, okay, I can use those channels. So there's a dialogue that happens in MIDI 2. The rest of MPE is pretty much the same. If you are in what's called fallback mode in MIDI 2, then the messages that you'll be receiving are still 7-bit and 14-bit messages, even though they may originate from a MIDI 2 controller. But also you can use UMP, which is the new 32-bit message format. UMP messages can reach you as well. And if you can't process UMP, you can use translation to turn them into 7 and 14-bit messages. So the one addition that's been made to MPE for MIDI 2 is that there are 16 additional high-resolution controllers, because we know that XYZ are not enough. You may also want to say for this note, it's being played at a particular bow pressure. This note, it is being played at a particular bow position. There's probably any number of things that you might want to add expressively as controllers get more sophisticated and as synthesis methods get more sophisticated. And the last thing, the MIDI modes 3 and 4 just have different names in MPE for MIDI 2. They're now called polyphonic channel pressure response and monophonic channel pressure response. So MPE, it's pretty simple. We're hoping that lots of instrument creators are going to create all kinds of crazy new kinds of instruments. Maybe 5-10 years from now, we'll see a whole lot of instruments that we've never seen before. And questions? I want to thank all the people who've been supporting us for the last 30 years. There's been a whole lot of people, some of them are in this room, who've been supporting our efforts to bring physical modeling to the world. Are there any questions? Okay. Yeah.
And can everyone hear me? Hi, everyone. I'm Kieran Coulter from Cinderboss Communications, and today I'll be talking to you about workbenching neural audio DSP. Let's see. Yeah, you can follow along with the code. It's been just released. The code is my GitHub account /neuralplayer, and this talk originally stems as the second talk in a series after a talk at ADC 2021 in JUCE development for Linux and Raspberry Pi. Of course, I realized after that talk, it became very hard to get a Raspberry Pi during the pandemic. So, I started to broaden things and say, let's look at, JUCE on the periphery of embedded audio solutions, try to make a general case for embedded audio. And I took a step back from that because I realized that, maybe if you were going to wonder, what are you trying to deploy from software over to hardware, and decided to start to break this talk into several series. And that made me a little bit of a mix-up depending on where you looked what the talk topic was, but the other topic will be coming at a future ADC with a lot more context. So then I'm going to preempt myself and say, hey, maybe this is going to happen again, and are looking at it, some new FOSS features. I can't say which software, but this is going to enable a stepping stone to bring your plugin not directly to hardware, but something very similar to hardware through some open source software. I'll be adding some features to, and then you'll have the full context all the way down to an embedded solution. So let's talk about the neural landscape. I would say on the design side, you're probably going to start working with PyTorch, very high level, and you could probably test your models in the Newton ecosystem. And that's really great when you have to rapidly iterate and continuously retrain. And once you got something good, you might decide to go over the Onyx exchange and bring your model over to TensorFlow for deployment. And I'd say that's the general consensus. In the opinion, it depends if you're working in research or in industry. You might choose one or the other, and it's great that Onyx runtime and the Onyx exchange exists to bridge the gap. Of course, once you're going into embedded, the Rabbit hole doesn't end there because there's TensorFlow, and then there's TensorFlow Lite, and then there's TensorFlow Lite for microcontrollers, which doesn't even have a logo. So this rabbit hole continues, as my coworker definitely understands, and you might have to implement your own layers, implement your own operators, but pretty soon you've got a highly performant model ready to deploy to microcontrollers. On the real-time side, so basically when you're done with training, you're starting to look at inferencing. How can I get good performance? One great solution is Jatin's RT Neural. And you start to worry about, well, what kind of backend am I going to use? It's going to be Eigen, Xtend, or C++ STL. Of course, you can't really tell what's going to be the best choice until you try everything and see what works in your particular scenario. Another option, yeah, like you said, you only implement the neural layers that you need for your own project, and pretty much you have the same thing is the case for TensorFlow Lite for microcontrollers, where it's not a complete implementation. So it's great to build a community and make sure that all the layers and operators are available. I had to pick some neural DSPs to workbench for the topic of this talk. No better idea than to stand on the shoulders of giants. So everyone might be familiar with Splitter Deezer source separation, and more recently Spotify's basic pitch, just for audio to MIDI, and that's what I selected for the talk. The next thing I was going to look at, okay, has anybody used this in the JUCE community and tried to already do the same thing? I did find this as a real-time reworking of the splitter model, and this guy, James Fung, decided to see how fast he could get it using his various options depending on the platform for matrix multiply. He was using Accelerate on Apple, OpenBlast on Linux, and MKL on Windows. And he was using the Intel MKL Fourier transform on all three platforms. On the audio to MIDI side, I also found NeuralNote. It was an entry in the recent Neural Audio plugin competition organized by the audio programmer in Newton. And those guys were using RT Neural, a combination of RT Neural and the Onyx. So, I mean, this is the basic idea. We're looking at separating out the vocals from the rest of the music and then running the vocals through basic pitch. And then you need some sort of player to synchronize the playback of the audio and the MIDI. And I decided, why not send the MIDI to a Rolly Lumi, so it's nice you can see the keys, the multicolored keys being driven. And this makes it a lot easier once JUCE comes into the picture, because we can wire everything together and see what we get. So what do we have to do for Deezer Splitter? This is a basic idea. If there's one thing I wanted to convey during this talk, is that you might have your first neural DSP that you're trying to evaluate, and you're looking for some kind of course, you can hear the results, and you have that qualitative analysis of how good the separation works, but what kind of quantitative analysis can you do compared to the baseline, which in this case would be the original vocal stem. So this is what we tried to do with Splitter RT. We wanted to compare the wall clock time against stock Splitter. It's about 7x speed up. There's a plugin version of Splitter RT as well, and check the real-time render latency of that. And most importantly, ensure that the MIDI output a little bit down the line is equally accurate to the stock. You can say the biggest optimization here, if you're working in neural audio, is not like saving the stage of the ratio mask for the final spectrogram. So that saves a lot of compute. And of course, the quality is lower, but in this case, we don't really care about the audio quality. We just are interested in whether we can get good MIDI at the second stage. So if you want to hear the difference, here's the original audio. We're no strangers to love. You know the rules, and so do I. And then here we have the Splitter RT extracted vocals.
We're no strangers to love. You know the rules, and so do I.
So that output's a little bit dirtier than the what I call stock splitter. You can hear some of the artifacts left over from the percussion in many cases. So how are we going to combine these together? On the neural node side, we also want to compare the wall clock speed to stock basic pitch because we've also noticed a pretty decent speed up there. And otherwise, neural node is just a means of workbenching the first neural DSP stage. And you can also get a sense of why, from the talk earlier today, why it's hard to put this sort of thing into a plugin format because you don't have a lot of DAW supporting audio to MIDI. The other thing that's really challenging is getting these DSPs down to real time because of the types of techniques they use. And I saw this when evaluating both DSPs, that lower frequencies are going to require really long audio chunks to get the amplitudes for the lowest frequency bins. But that could be maybe solved in hardware a little bit down the line. So now you can see how this evaluation model is coming together. We run the output from the first neural DSP into the second one, and then we've devised a method of achieving qualitative analysis and quantitative analysis as well. We can hear the output, but we can also tell is the pitch accuracy at least as good or hopefully better than the baseline. At Synthesizer, we've used the exact same technique in speech noise removal from speech. So we combine the speech signal with noise, run it through a noise filter, and you can use mean opinion scoring to tell whether the average human would find the noise filtered audio more intelligible than before. But to get a good second opinion, you could also use, in this case, speech-to-text engine made by OpenAI called Whisper, and then determine whether the word accuracy is better than or equal to the baseline word accuracy. Okay, so how do we bring this all together? We built something called Neural Player. This is often the development workflow for a lot of us. You know, this is a cutaway from a 3D model like Development Planet, right? And you're trying to shoot to the moon, and you're fighting developer gravity, right? So you have your idea, right? You always go to the left first, right? You want to do something awesome, but it comes at a cost, right? Your latency starts to go up, and you have to battle it back with some tedious fix to get it back to low latency, and then go back the other way, and then pretty soon you've got something that might be considered production ready, although I guess a lot of people release it's still in the yellow. So maybe we can lower the bar a little bit. The idea I originally wanted to do for this would be real-time show control, but it's really hard to get the latency to that point. So maybe a little bit less of a context where you really need to have low latency would be a media player. Maybe if you could do you could do processing of someone's music library in the background and then have the results ready. They're not going to need absolutely that you have the lowest latency. And you should remember that this has all happened again 20 years ago. We're seeing the same scenario now with 2D convolution that we did more than 20 years ago with 1D convolution, where this principle was well understood in the 80s, but it wasn't until 1999 they were able to ship it in real time with Sony's DRE unit. So this is basically 3 different GUI screenshots from Neural Player. We have the main view in the middle here, and we have a separate hardware and software debug console. And this is mainly for people following these slides offline, but a quick and dirty UML composition of the software if you'd like to play around with the code yourself. A few notes as we went and developed Neural Player. Managing everything with CMake was definitely the only sensible choice. I started by making forks of these other open source softwares that I found and modifying them to make sure they were feasible for this type of workbenching. And it was really great with CMake. You could use CPM to manage all these dependencies. One new thing that I changed was using Git subrepo to manage the child repos rather than Git submodules. It just made it a lot easier to be able to commit changes to the subrepos, I should say, back to the upstream, working with different repositories as a single project. And finally, we built the player as an application that brings this all together. So a couple of other interesting branches in the source code. The Workbench 2 branch will allow you to compare against stock splitter or stock basic pitch yourself and compare the wall clock times, which are much longer, maybe due to adding emojis into the console. But And more recently, we added a visualizer branch. I don't know if anybody remembers Winamp, but it was a much-loved media player back in the day. And Project M is an open-source version of Milkdrop, and we decided, wouldn't it be cool if you could extract the stem from the media player that you're playing and drive the visuals just with that stem behind the scenes? So you don't hear it, but the visuals are visualizing just the bass line or just the vocals. So the results, I would say, are, roughly speaking, Splitter-RT is about a 7x speed up over the baseline. Neural Node is also much faster in its implementation, about 4x in that case. And some observations I found, and that's why the jury's still out on the results. The MIDI transcription was absent, I'd say below the alto tenor range, and this could be an optimization in Splitter-RT to avoid processing lower frequencies. The last thing I noticed that was interesting is there were some MIDI artifacts littering the upper frequency range, and this could be unique to vocals because it's a lot harder to convert vocals to MIDI than a synthesizer. So without further ado, here's a demo of Neural Player. If you have a Rolly Lumi, confirm it is connected in the settings pane. You can also enable a MIDI hardware output here. Press Load New to render a new playlist. You can press Halt to interrupt a render operation already in progress. You'll still get a partial playlist of all files rendered so far. Press Load Existing to open a previously rendered playlist. Once the render is done, select a playlist entry and press Play to begin synchronized audio MIDI playback. I want to say thanks to a few people, absolutely James Fung and the guys from Neural Note for providing the open source code to do the workbenching. Joshua Hodge, Shatton, and the guys from Newtone for developing the neural audio DSP community. I see great things ahead for us. And of course, Camille Kisiel, my coworker at Synthesizer, for clearing the way down the rabbit hole in front of us. If you want to reach me, you can reach me on my LinkedIn. And we're always looking for new projects at Synthesizer. In this case, for neural audio. So get in touch with us if you'd like to help us develop your neural audio solution. Thank you. Are there any questions?
Hello? Yeah, I have a question. That was really cool. Thank you. Question I have is, so is it always outputting the MIDI based on the vocal, or do you also have some choice in what it's tracking and outputting, like which source?
Well, we're going to add some new options pretty soon. I mean, that David Hasselhoff song was my theme song for developing the source code very quickly after the talk acceptance, So this is just the beginning, I think. Bass is going to be a problem due to the low frequency, but it's a trade-off. Basically, optimization of latency versus some of these things that are harder to deal with in the system. So I think this offline processing of your music library just does it overnight, and you have everything. I think even in DAWs, it would be great if rather than having to process in real time, you could click like a freeze button or something, and it could pre-render the MIDI and then be able to play it back synchronously.
Thank you.
Okay.
Okay. Is the microphone working? Cool. Okay, so I'm going to talk about differential reference counting. My name is Palmer Hogan, and a little bit about me is that I've been a long-time musician, music producer. I couldn't find any piano recital photos, but there's a photo of me DJing. And a little bit of a more recent programmer. After bashing my head against the big blue brick here, I came out on the right side pretty okay. So I now work at Roblox, and Roblox is a creation engine where people can create worlds and upload them to our platform and share it with friends. And a crucial piece of that puzzle is our game engine, which is what I work on. Our game engine is a 15-year-old C++ code base with tons of systems, tons of threads, and several real-time threads, some of which are recording, processing, and rendering audio. And note that I said real-time, which implies deadlines, and deadlines imply consequences for missing them. So the general rule that Chris kind of touched on in his earlier talk is we don't want to do anything that takes an unknown amount of time. That would be like system calls, mutexes, or dynamic memory management. And this talk's going to be about how you might be able to actually do the third one pretty okay. So luckily, atomics solve our problems, right? Like you have some shared data that you're passing around a bunch of threads, and you can stick it into an atomic and load a value from it and store a new value to it, and that's the talk. We're done, right? Like that solves all our problems. Unless, of course, you don't want to do this for integers. Like, what if you have some type t? Well, this doesn't generalize super well. You might be squinting at those. Those look kind of like copies. Maybe there's non-trivial constructors going on there. But we actually have a bigger problem, which is that like atomic itself is not actually lock-free. This might be using a mutex under the hood and block your audio thread if you try to use it. So then your load and store are not actually real-time safe. But atomic pointers, like those solve our problem, right? Like those are basically just fancy integers, and we can load and store those just fine. Unless you want to delete the old stuff, what's the problem with this? Well, we could swap out the current value, and that exchange is lock-free, But what if we leased out this pointer to someone and they're still reading it? Like, then we've deleted it while they're using it, and that's no good. And this is about the point where I'm starting to doubt whether lock-free programming was a good idea. But let's trim down the scenario a little bit. Let's say that we have one big blob of shared data and many threads, but it's updated pretty infrequently and on a lower priority thread. It's read arbitrarily often, and some of those readers have deadlines. Well, this is the topic of an active standards proposal. And I just want to say, like if you squint at it, it kind of looks like the previous example. You've got a method to get a snapshot of the current state. You've got another method to update a new value. And you've got this try update method. But we're mostly going to focus on the get snapshot and update method. And this alone is like so useful. You could have like an audio filter and the coefficients come in from some other thread, and you just want to load a snapshot of the current coefficients and use them. And if get snapshot is sufficiently real-time safe, then this is real-time safe. You might also have something a little bit more interesting like the observer pattern. Like maybe you have an event and a bunch of observers are watching it, and you can load up a snapshot of all of the things that are watching it and notify all of them. Now I have that bit highlighted in yellow because it's a little sketchy, like you don't know what notify is doing. And this is the only context I've heard a coworker say the phrase accidental recursion. So, you know, maybe that's what you want, but maybe not. But I want it, right? And I want it before I look like this. And maybe a more accurate title for this talk would have been Implementing Snapshot Source, How Hard Could It Be? But I wanted to give that build up to get there. And it turns out there's a really compact implementation of this snapshot source interface if we just use atomic shared pointer. You know, you have the current state held in an atomic shared pointer, and then you load and store on that atomic. And there's no locks here, right? Like, I don't see a lock. That move is a little sneaky. That move is moving a unique pointer into a shared pointer, which is constructing a reference count. But if we don't care about the update method being real-time safe, like this seems fine. But there's a little bit of a more dastardly spot that this gets you. Because I've said that a snapshot pointer is a shared pointer, and we're returning a shared pointer, essentially. Well, what happens if my filter here gets to the end of scope and it's the last one holding the bag? Then it's going to do a deletion, and that's potentially blocking. But we can fix that, right? Like we can have a list of all the stale snapshots, and then at a time of our choosing, call cleanse on them. So when we update with a new value, we exchange it out and push the old guy onto a stale list. And then we know that we can delete a snapshot if its use count is less than or equal to 1, that being like the only version is in the stale list. And here I'm kind of hand-waving away the weak pointer side of the interface, but we'll get there. And then cleaning up the garbage is a matter of iterating over the stale list and erasing all the things that have sufficiently low reference counts. So this works, surely, right? Well, unfortunately, no. Timur Dumler did a wonderful series of talks last year on how you could implement a lock-free atomic shared pointer, but the one that we have here is probably not. And even if it were, it would be doing conceptually two distinct operations. It first has to load the pointer and then add one to the reference count. And if we want to minimize this window between the two where anything else could happen, we would have to do some kind of cast loop, like a retry loop. And then, like, this is lock-free, but it's not wait-free anymore. And that's the point that I started squinting at this equals sign. Like, we're saying that a snapshot is a shared pointer, but is that actually, like, what we need? What parts of shared pointer do we need? Do we need to know how many exist? Do we need to be able to take a weak pointer and get back a shared pointer from it? Do we need custom deleters, type erasure? And I'm going to say no. The only thing we care about is don't delete me. If I have a snapshot, get your deleting hands off of it. So a very, very bare bones snapshot pointer maybe has like 5 functions, constructor, destructor, and then like ways to dereference it. And Dmitry Vyukov has an article called Differential Reference Counting that Timur actually referenced in his talk as a means to implement a lock-free atomic shared pointer. But I would argue it's even more powerful if we don't care about that, because it lets us be really lazy. The idea is we're going to take a typical reference counting scheme where the object and the reference count are next to each other, and we're going to split it apart. We're going to have an inner structure that actually holds the data, and it has 1 reference count. And we're going to have an outer structure that points at the inner guy, and it has another reference count. And the snapshot source will hold an atomic outer, of which there's only 1. The current object is managed by an outer. And we give each snapshot an inner. So it doesn't do anything in its constructor, but in its destructor, it decrements the reference count. And the scheme here is that the outer reference count only ever goes up. So, great investment opportunity. And the inner reference count only ever goes down. So, don't be like this guy. But somehow, I claim that if the reference count of the inner is 0, that means we can delete it? Like, how does that work? I thought it only went down. Like, it's going to underflow through the floor. And the way that we make that work is that in our update method, we'll modify it slightly. We're still going to, make a new inner object to encapsulate the thing we're moving in, and we'll still exchange it with the old thing and push the old thing onto the stale list. Like, that all looks the same as before. But the bit that we've added is, at the moment one of these outer structures becomes stale, we transfer all of its references to the inner structure. And this essentially makes it whole again. It was underflowing through the floor, but now we've added all of the outer count to it. So now it's, if there's nothing referencing it, it's 0 again. And this is still problematic. Like, the outer structure is too big. It's got a pointer and a 64-bit ref count. This is going to rely on 128-bit atomic instructions, which are not universally available. But we can do something about that, because there are other parts of the shared pointer interface that are kind of implied. And I'm going to go out on a limb and say, none of the devices I'm running on care if there are 4 billion snapshots of the same thing. If you've taken that many, you've probably already run out of memory, and you've got other problems. So with that in mind, we can make the reference counts 32-bit. The unfortunate casualty of this is that if we start a pointer to the inner structure, it would still be too big. So we have to also settle for an index to the inner structure. But that lets us essentially treat this outer struct as if it were a uint64. We can have like all of the index bits in the lower 32 bits, all of the ref count bits in the upper 32 bits, and whenever we want to add a reference, we add to the upper bits. And even if this overflows, it's never going to tamper with the index bits because we're adding by increments of like 4 billion at a time. So our outer structure looks a little bit different. It's moved the index and ref count to be methods rather than fields, but more or less the same. And we do some bit shifting and masking to get the index and ref count. So now our snapshot source has this kind of awkward array that we have to index into, but it's literally storing an atomic 64-bit int, which is good. And this array also kind of replaces the need for a stale list. So, maybe it's not so bad. And our get snapshot method becomes like really cheap, weight-free even, because we're just doing a single fetch add and then obtaining a snapshot from indexing. And update now may spin because this make inner call might have to look for a available slot in that array that it can put the new value into. But a note on that array, right? Like this array, I've mostly written it as a fixed size array for brevity. Truthfully, you could replace this with a container, as long as that container has suitable conditions. You would want something that has a wait-free way to index into it, and if you're going to provide a way to push new values into it, that can't block indexing. So this could be, something like a pool or a linked list or maybe some kind of deck. You've got options here. It doesn't have to be fixed size. So in summary, snapshot source is coming soon. Whether that's C++ 26 or what is up in the air. But if you're impatient like me, this pattern can be implemented today, and it can be used to great fun and profit in real-time safe code. So I want to give a special thanks to people who reviewed this slide deck and my code, namely Chris, Dimitri, Keith, Richard, and Ryan. And thanks for listening.
Anybody else? We've got 4 minutes.
So I might be missing something trivial here, but how snapshots are useful for audio? What is exactly use case for this?
Yeah, so if you have some big data blob that is too big to fit into an atomic, and you want to, in one go, pass it over to the audio thread. So I bring up filter coefficients as an example, because if you tried to pass filter coefficients over to the audio thread, maybe you've got 5 or 10 floats, and that's too much data to fit into a single atomic. They're also the sort of thing that if you read them individually one at a time, the filter might become unstable, and that might not be what you want. You could use a queue for something like that, but if you only care about getting the current value, you'd effectively have a queue of size 1, and that might be...
and a circular buffer wouldn't be...
Yeah, that's what I mean by a queue, like a fixed size queue. You could have something that's size 1, but one of the properties I really wanted is that readers can't interfere with each other. If one reader pulled the item off the queue, then other readers don't get it, and that might be questionable semantics. Timur did another talk last year on RCU that's very similar to this. The main difference with that approach is that he knew about how many readers he would have in advance so he could register them, whereas this approach works if you don't know how many readers you have in advance because it uses reference counting.
Thank you.
Hey, is this open source, and can we use this right now?
I could post something on my GitHub. I haven't yet, but sure, yeah.
So one of the parameters to your template was an n, which looked like it was like the size of the array. Is that the number of snapshots that can be outstanding at once?
Yeah, exactly. So that's why I said update may spin if you have like more than n things outstanding. But if you wanted to replace that with a different container, you totally could. Like that's one of the design constraints of using a fixed size array. But if you replaced it with, say, a pool or a linked list of some sort, that would alleviate the need for that template parameter.
And then if you have like a fixed size, did you have any tips for like tuning that number? I can imagine, some things you want just a handful of snapshots out, and others you may want a lot.
Yeah, the good news is that even if you are going the fixed size route, you're only ever making your update thread spin. You're never making the get snapshot thread spin. I don't have a good system for figuring out how many should be in that array, but 4 seemed like a decent enough guess.
Okay. If I can get this full screen. All right, let's talk about the other side of multi-threaded code. My name is Ryan Avery. I've been an audio developer for a long time now. I started at Avid working on Pro Tools, HDX, AAX plugins. I moved on to Dolby where I worked on Atmos Spatial audio content creation. Now I'm at Apple. I'm also, like a lot of you, a independent musician. I'm a violin, electronica music producer, so I love this industry, and I now know a thing or two about it. And I wanted to talk about the testing side of multi-threaded code, because thank you, Palmer, for showing that this is complex stuff. And this is stuff that you get far in your career, and you still are learning things. In this talk, some expectations. We're not going to worry too much about production code. We're going to focus on the testing side of things. We're not solving this either. This is not a solvable problem. We're just adding a few more tools to your arsenal. In fact, we're going to show some really bad multi-threaded code. Don't use any of the code that I'm showing you. There are no magic bullets to test this, but with a few simple tools, we can kind of start taming this system. So of course, that brings us to castles. I love analogies. And I want to talk about castles because we build castles as a series of fortresses to keep order, make things run efficiently, hopefully keep our townsfolk safe. Multi-threaded code is the same thing. Helps things run efficiently, allows us to scale up our processing, and hopefully keeping things safe in the process. But the thing about castles is, whenever castles exist, so do dragons. In fact, the larger your castle, the more dragons are attracted to it. Dragons are powerful when they work with you, but very dangerous if they get out of hand. Multi-threaded code is the same thing. There's always the possibility of being killed by a dragon. And the larger your concurrent multi-threaded code base, the larger that possibility, the larger that dragon. So here's some really bad dummy code. Again, don't use this. It stores some samples, uses a max and a background update thread. You can see two threads going on here. Process and update, we've all seen this. Simple stuff. There's bugs here, obviously. It's pretty easy to reason about. You can probably see several problems, but remember, we're not concerned about this code. This is production code. But hey, look at that. It's a little baby dragon. It's this little max float here that goes between the two threads. It's easy to think about and reason with. It's very small. It's cute. It's a little pet. You can probably fix this code in your sleep. Or not, don't care, you might be just getting into multi-threaded programming. But as it grows, it can be a big, big problem. So we have to tame it. How do we deal with this dragon? We have 4 ways. We can ignore it, pretend it doesn't exist. We can stress it. We can force the dragon to keep attacking our castle to see where it interferes. We can cage the dragon, give it a smaller little castle to play with, to attack, Or we can mock it. We can place a puppet and say, oh, dragon's coming. Oh, it's going to attack us. We'll talk about these things in a bit. But remember, the dragon is that magic that makes multi-threaded code so powerful. We want the dragon. We need the dragon. We can never kill the dragon. The dragon's always going to be there. So, first, ignore the dragon. Just write some single-threaded tests. If you don't currently have tests in your code because of threading, then just put some in. Pretend it's not threaded. Don't worry about concurrency. Most tests should not be thread aware. So here's a simple test. It's valid code. It says, oh, okay, we have this little test function that says, oh, 2 blocks coming in. The max of both of these blocks should be 1 because we wrote this little max meter function. Now, of course, everything is serialized in a single thread, so we have no idea what the code will do if both threads are concurrent. But it's still a valid test. Now note, you can't always ignore the dragon. For instance, if, let's say process and update are async, but in general, you can ignore your dragon and just say, we don't care about the dragon right now. We just want to focus on our logic. Next, we can stress the dragon. You can run your code a lot of times. See if it fails. Now, we could just do manual tests on the real system. But the problems we're looking for are very, very rare. These are the things that customers will find and say, oh, it crashes my system once out of every 1 million things, and you can never find this bug. These are the kind of multi-threaded problems that we're trying to tackle and tame. And in general, you should prefer the smallest reasonable test size. We don't want to have tests that run, manually via, a QA engineer. We want this thing to be, a few seconds on our test system. Now, with modern C++, it's very easy to instantiate threads, especially in tests. So here we have, our two threads. One is our update thread, and one is our process thread. We can just instantiate this in a test. It will run. It will go a million times, and usually, if there's a bug there, it will find it. Now, of course, some of the more obscure ones and things that are much more rare might not be found by this, but it's, again, a valid test. It's not going to test your logic. Like this assertion completely will not pass. This will fail because we don't know the order of our two threads, how they're, we don't have determinism in this system. But here, this is more an example of testing your threading rather than your logic. So we can cage the dragon. We can separate our test concerns. We can define our thread interactions, and this will give us more concrete entry points. So going back to our unsafe meter class, we have lots of references to max sample here, and we can start seeing the dragon is in more places than we might like. There's 4 references here. There's even some comments for code we have written but commented out here. That's a lot of places the dragon can live. So we want to limit where this multi-threaded entry points, these multi-threaded interactions are. We need to separate the logic from our async code. Part of it deals with correctness of their overall logic. The other deals with async interaction. We need to limit it to defined points. Start constructing your API around your multi-threaded nature so that most of our tests don't deal with the dragon. They don't deal with the multi-threaded nature of our code. We can get our dragon out of what we're testing for in most scenarios, or at least know where the dragon comes in, and we're in better shape. So how does that look? If we have kind of a safer meter, we have this thing, it's a little queue for meter. We recognize that, we probably have a queue that we need to do interactions with our threads, and so we'll put it somewhere. Again, this is all hand-wavy, really bad code, but we start to recognize, where the dragon is, where our threads interact with each other, and we start boiling it down to simpler data structures, queues, stacks, condition variables, simple things as much as possible. Isolate the uses of our thread-aware variables to as few methods as possible, extract into a separate class. Here can we extract storeMax, getMax in this queue for meter into this thread-aware class and leave the rest of our process function and update function blissfully unaware of the dragon. The more of the class is testable without being thread-aware, this is good. We can write tests easier this way. Now, some known cages. Once you have these known cages, we can do things like, hey, a queue. There's ways to test for the dragon. We just say, here's 2 threads. Assert that this thread puts stuff in the queue, and it comes out the other side on the other thread in an expected order. If we have a stack, we assert that there's no missing elements if we put a bunch of elements in a stack in one thread and take them out on the other side. We can expand that for multiple input, multiple output, consumer, producer kind of styles. But I'm not going to go too far into this because there's known ways of doing this online. The objective is to get things into a simpler form. Finally, we can mock the dragon. Won't talk about this too much. This gets into more sort of TDD testing style code. You can look it up online. But this is basically saying that dependencies come from outside. This is this dragon. There's this multi-threaded beast that we want to pass into our classes, pass into our functions, rather than having them as part of our classes. So we might find solutions where our class is waiting, or depending on an outside complex service, we get into discussions like when do you mock a dragon versus moving a dragon outside a class. It's all subjective. Basically, you start mocking dragons when it becomes burdensome on testing to keep it inside of the class, rather than mocking, which comes with its own burden of keeping tests in order. You make that trade-off. Now, dependency injection simply means this. We have our class to test. We have a dependency. It's our multi-threaded dependency. We just plop it in, usually in the constructor. And this can actually be done in compile time. So usually with mocking, you don't need to worry about performance, although it's something to keep in mind. But I find people tend to worry about it a bit more than they should. So let's look at test code smells, because just like production code, test code has its own smells, its bad sense as well, that could tell you something is wrong, indicating that production code might not be as testable as it could be. So the first test smell, lots of sleeps and waits. If you're starting to test your code and you see things like this little sleep, 0.1, well, that's a test smell. Tests are taking longer than they need to, first of all, because obviously this 0.1 is kind of just arbitrary. It means you know there's a drag in here. You don't know exactly what it's doing. All you know is it's likely to be done in 0.1 seconds or something that you made up because of, something. It failed when it was 0.01, so why not 0.1? I've seen this a lot. You've probably seen this a lot as well. Tests could still fail under CPU load, and you'll probably maybe increase that value. I'm not saying that, I'm guilty of this. I have been guilty of this, but it's a test code smell, and one you want to get rid of. So, a little bit better. Let's wait on a state change. Let's say, we set a host control to 2.0. It's going to wait until that value is actually received and set in the plugin. Well, this is an easy change to make because it usually doesn't require production code changes. But even better still, observers and providences. We heard about this. You've probably seen this in your code base as well. Let's actually introspect our code somehow so that we can see, exactly when this value changes in the host. That's when we can move on to our next line in our test. Now, this does sometimes require production API changes, but I would argue that this is good. We want to be able to observe and to listen to our production code. So this is a good change. It's something we might want in the future for UI or whatever. Yeah, there's our promise. There's our future, our waiting. It's still a dragon, but it's a little cute, manageable dragon. Getting better there. Even better, let's just put it in a test helper function. Set on host and wait. That way you don't have to read all that boilerplate code. It's just one line function. But as you probably see, there's still a wait. And we said lots of sleeps and waits is a test smell. So, another test smell. Every thread feels thread aware. It's fine if we're always waiting on events. You set state but have to wait on it to take effect. It's okay, but we want something better than that. Here's our last piece of code. Now, look at this. This test is named plugin can set process, not host can set control. So why would a plugin control wait on a host at all? This is really indicating that there's two tests here that we really need to do. We need some API changes. So we're going to say there's two things. There's plugin test, and there's a plugin host test. The plugin test can process. We don't care about how the control update got there. All we care about is that we assert when we have this update. Yeah, it's a gain of 2. And the host just cares about, hey, I get a value that I can set. I want to make sure that actually gets set to the plugin. So we say plugin host can update control. We use tests to drive this change. Got a very powerful side effect on both our tests, but also our usability and our maintainability of code. Cute little baby dragon, but it's still a dragon. So the best situation is stateless code. This is not always possible. Not always even desirable, depending on what we're doing. But remember, we need the dragon. If we have stateless code here, that's great, but we probably are doing multi-threading because we want to do some sort of concurrency, do some more processing. But if we can get our code to stateless, that's great, because there are no dragons in stateless code in terms of multi-threading. So one more test smell, test running in real time. Anything like internal timers, this sucks because it's a variation of bare sleep. We're just, having a test that's saying we can process. For some reason, we need to run for 2 seconds. I don't know why, but I've seen it in my code. I've seen it in code bases. You might have too. This means this test takes 2 seconds to run. It shouldn't. We should be able to run our tests in faster than real time. So the advantage that we want to go to is dependency injection. And we want to inject our timer into whatever is depending on this timer. Thus, with this one little change, now we can run our code faster than real time in our tests. This is very powerful. Give him mocks. Don't use a real timer. Do a mock timer. We can kind of tick it on our own cadence rather than having to wait for a wall clock time. So I'm going to talk about multi-threaded protection smells just briefly, because this is where we start putting the test-driven in TDD. If we have scattered standard atomic member variables all around here, those are all little dragons. I'm not saying atomics are bad. They're very good. We want them. But remember, every time we have an atomic, that's a dragon. That's something we need to control. We need to either cage or tame or do something to not have it propagating around our fortress, scaring our townspeople. Too often you probably fix a crash with an atomic. We say, just put an atomic. It's, doing multi-threaded. Once you put an atomic there, it's fine. Move on to the next thing. Well, we need to know that that just is a smell, and we need to keep that smell somewhere in its own little thing. Similar thing with scattered uses of atomics. They're all dragons. Put them into its own thing. Just have an exchange. Make sure that wherever you use those atomics, you're doing it with great care and great knowledge. Similar smell, async calls in classes under test. Here we have this update class, which I want you to look at this briefly and say, how do we test update? We can't, because we're starting up a thread that calls update under the hood. With this API, there's no way to test update in isolation. So instead, have an updatable. Use dependency injection. Put it into your class. Thus, updatable contains the audio logic. This my class now is all the threading logic. We've separated our concerns. Things get much more testable. So, lastly, I'm going to say it takes a team to tame a dragon. One of the people on your team is not a person at all. It's this compiler, static analysis, instrumentation. I recommend looking these things up. The best time to add a static analysis to your code is right now. Or what is it? The best time was yesterday. The second best time is right now. You know what I mean. These tools are old. They've been around for a long time, but they're very useful in telling you kind of where these smells are, where your dragon can live. Make sure that your dragons stay small. Final points. Most of your tests should be thread unaware. Make sure your thread aware code is separate from your logic code. Distill your concurrent code into these basic structures. Don't just place them willy-nilly everywhere. Remember that the first test is usually the toughest, as it requires refactoring your production code base sometimes to be able to instantiate something under test. But put that first test in there. Think about where your dragons may be. Keep your fortress safe, and now go out and tame your dragon. Thanks.
There was a slide on how you put in the queue. It was early in the talk. It was for updating and
no one. This is where it online gets slow. Yeah.
Sorry.
It's okay. There it is.
Was that it?
Was it?
Yeah. So what happens if you called update twice in a row without processing?
I don't know. This is really bad code.
Okay.
No, literally, that's why I have the disclaimer. Do not use this code. There's lots of dragons here. And all I'm kind of trying to illustrate here is usually things will distill themselves down into these queues or these stacks, usually with audio processors as queues. And just know which structures you probably have, get them into this cage, and then get them out of the majority of your code base so you can test them in isolation. To answer specifically your question, I don't know. I never ran this code. I just put it up as an illustration.
Okay, and my follow-on would be, with dependency injection, especially for locks and other things like that, have you done that in production code, and have you had success? I found it's one of these, it's very pernicious. So you start doing dependency injection before you know it's like everything.
Dependency injection does tend to breed itself, but it is a code style that I really like because it becomes modular, because you can kind of makes everything modular, reusable. But yes, it ends up kind of informing how you're developing this code. And so if you look at a code base that's heavily DI'd, yeah, there's either a factory methods everywhere, or there's constructors that have lots of incoming parameters. I find it really useful because I can just look at the test and say, oh, this is exactly how you use this one class, and here's like the kinds of things that it needs, whether or not I'm using the mocks or the actual things. Obviously, as I mentioned before, it's subjective. So you might say, I don't want to use dependency injection or mocks. I want to stick to this other stuff. That's for you to decide. These are just kind of some tools that to think about. Cool.
I've got one thought, maybe a little bit out there.
Whenever I've dealt with code like this, I usually do that, standard atomic hack, is just to sort of think I'm going to be able to get away with it. I wonder if there's a way, I haven't messed with those sanitizer tools too much, but wouldn't it be cool if we could have like a visualization of what's going on with threads, almost some like sort of 3D graphic thing of like gears moving around and then, the state of variables. Because, we do this with audio, with oscilloscopes and stuff like that.
Sure.
Have you seen anything like that?
Not exactly what you're talking about, but certainly if you get in the depths of either Visual Studio or Xcode, there's some really incredible tools there that kind of show you, maybe not statically, but once you've run your code dynamically, it will show you sort of your call graphs
history,
and maybe a couple of different threads. I've not seen something that is the oh my God, this is the tool that will save multi-threaded code.
Right, because if you can imagine just like watching this thing going, oh no, the dragon's going to crash into the bear. This isn't cool.
Right. Yeah, if there's a way to do that and that tool exists, that would be amazing.
So going back to dependency injection, I found that while it is useful for testing, sometimes I find it makes it a little more difficult to reason about the code, because before I knew exactly what this was doing, now it's being injected in, it could do anything. So what's a good way to think about that so I don't feel that way anymore?
I think for me, the power thing about dependency injection, the way I think of it is it allows me to abstract the things that either I don't control or I don't care about. So, if you have an audio processing loop that is very much an algorithm, like, okay, it goes from the filter to the delay line to this thing, like, you can use dependency injection there, but as you indicate, it probably will interrupt your kind of flow and your thinking about analysis. But if you suddenly have, like I said, kind of, here's a timer that needs to come in, or even more to the point, like, here's some database, or here's some network thing, or if you're doing something more than just, straight audio pipeline, that's when I think dependency injection becomes very powerful, because you can say, I don't care what this thing is doing. All I know is it's going to give me the things that I want. Or in the case of multi-threaded and dragons, like, I know that this is where the dragons are. It's just going to slow down my test code. It's going to be real time or slower than what I want my tests. But again, like the point before, it does require a little change in thinking. And I'm not advocating for it 100%, but I find it very useful, and I would strongly encourage everyone to think, where could I use this to help switch around my thinking a bit?
All right, everybody.
Sorry, no concrete answers there.
Brian, thank you. Okay, it's time for a break, everybody. Do some networking, get some coffee, report back to the auditorium at 4 o'clock. See you in about 40 minutes.
I'll hold everyone else up with another question.
Yeah.
I don't know. I was wondering
Hope you all had a nice break. So hello, everyone. Really excited to be here at ADC. Big thanks to the organizers for the opportunity to present our work. I'm Nikhil. I work on audio algorithms for hardware products at Google.
My name is Wilson, and I am an electronic music enthusiast currently working at Waymo.
And today we are here to present DDSP VST, a cross-platform audio plugin powered by machine learning. So this talk is split up into the following sections. We'll begin with a brief introduction on what DDSP is, and then we'll dive into some of the engineering and UX challenges of turning this into a real-time interactive experience that can be used by artists and musicians. So DDSP stands for Differentiable Digital Signal Processing. It lets you combine the interpretable structure of DSP elements, like filters, oscillators, with the expressivity of deep learning. For this project, we leverage DDSP for timbre transfer, wherein you can transform a given audio signal into any musical instrument using its extracted features like pitch and loudness. Here's a really cool demo by one of the original authors of the paper, Hanoi. Awesome. So since 2020, we've been able to leverage DDSP's efficiency to power a variety of creative web experiences and offline demos. However, there's one question that we always got. That's really cool. When can we get that plugin? So how do we turn this offline research experiment into an engaging and interactive experience? This talk aims to address the engineering challenges in that. So we arrived at the following requirements for this plugin. It needs to be cross-platform. It needs to run in real time for experimentation and live performances. It needs to provide intuitive controls for the parameters for timbre transfer. And lastly, it needs to be customizable so that users can upload a piece of audio, train their own models, and drop it directly into the plugin.
But before that, I'm going to give a quick primer on the underlying magic that powers DDSP. So the core concept of DDSP and almost all machine learning, in fact, is that as long as a function is differentiable, you can propagate the gradients of a loss function across that function to modulate the weights of a learned machine learning model. Well, it turns out a lot of DSP primitives, such as additive synthesis, FFTs, and FIRs, are in fact differentiable and can be composed in interesting ways to form an end-to-end synthesizer. So how can this be used in an audio context, in the context of timbre transfer? Well, in the original DDSP paper, there are three main components. The first component is this encoder stage, where we extract interpretable features from the target audio, such as pitch and loudness. This then goes into the decoder stage, where we output the harmonic amplitudes and filter noise coefficients. These outputs go into the last and final synthesis stage, in which it is used to resynthesize the target audio. So where does DDSP come into play? The thing I want to draw attention to is the synthesis stage, this third modular component. By making these individual components differentiable, you could then learn a unique instrument model, a black box ML algorithm that captures the unique timbral characteristics of an instrument, learned by making it reconstruct a 10-minute segment of audio. After training, this specific model can be exported and then reused in a real-time inference context, in which every other module, specifically the encoder and synthesis modules, can be replaced with any other functional analog. So that's kind of the magic of DDSP, where you could hot swap these components with their non-machine learning counterparts. So that's a really quick primer of DDSP, and if you want a more in-depth explanation, please check out David Trevelyan's talk at ADC 2022. Now, DDSP isn't the main focus of the talk. I think the main focus is how we actually turn this to work in a real-time plugin. All right.
All right, so let's take a look at our stack. Have you all heard of JUCE? So we use JUCE to build the cross-platform part of the audio plugin. And then for model inference, we chose TF Lite. There's two reasons behind this. One, TF Lite allows us to use our trained models in a way that's optimized for inference across major OSs. And secondly, DDSP was originally built using TensorFlow, and it's pretty straightforward to convert like TF models to TF Lite models. And lastly, it was complicated to integrate TF Lite with JUCE initially. This was because TF Lite was built using Bazel, and this caused a lot of hair pulling, especially on Windows. So we were quite excited when both JUCE and TF Lite added support for CMake. It made the build process seamless and led to a significant boost in productivity.
So next, I'm going to talk about some of the real-time challenges in getting this model to work in real time. And if you work in real-time audio, then you deal with strongly timed audio callbacks. And to give a quick primer, every set amount of milliseconds, your audio card says, hey, please fill this audio buffer with ones and zeros. And if you don't, I'm going to play anyways. And if you don't fill it in time, called a buffer underrun, bad things happen. This usually involves in glitchy noise sound, or maybe you might pop your listener's eardrums. That's not good. So what does this mean in the context of AI? It means that the AI inference speed actually matters, since we have a finite amount of CPU cycles per input frame. So there was a lot of care in actually reducing the inference latency of all of our three components. First, I want to talk about the F0, or pitch encoder. So as we said before, we could substitute these components with any real-time analog. So we actually tried different real-time pitch detection algorithms, such as Yin and Spice. However, we noticed that our trained model was extremely susceptible to bad pitch detection. So this usually manifested itself with octave jumps and jittery pitches. And we realized the end result just did not sound good. There were a lot of phasey artifacts, and this was not a good product that someone could use in a real performance. So we realized we had to use the original model used in the original DDSP paper, and that was the CREP-full model. But there was a problem. The inference time was too long to be used in a real-time context. So we settled on the solution of distillation. What distillation is we trained a tinier CREP model called CREP Micro with only 160,000 parameters. This was done by training it to predict the logits of the largest CREP-full model. And this was crucial in reducing the plugin latency from over 500 milliseconds to 64 milliseconds. There were also a lot of non-trivial changes in the instrument decoder. We noticed in the start that we trained a much smaller recurrent neural network than the original paper, and found that we could increase the time between predictions from 4 milliseconds to 20 milliseconds without much change in audio quality. This meant a 5x boost in efficiency, since we were making 5 times less TF Lite inference calls. We also had to pay special attention to not incorporate any non-causal convolutions, like the web versions of DDSP. And this is because the original offline model was able to look into the future. Obviously, you can't do that in a real-time context, so if you could look into the future in real time, well, you deserve a Nobel Prize. So we modified this to be non-causal. We also had to fight TF Lite in the meantime, and if you worked with TF Lite before, you know that TF Lite has a limited selection of built-in operators. However, a lot of our operators in the original DDSP paper relied on were not supported in TF Lite. So we actually had to iterate on different types of stateful neural networks, such as LSTMs and GRUs. We settled on the GRU, which is a gated recurrent unit, and also had to store the state natively in C++. All of this resulted in a TF Lite binary reduction from 150 megabytes to 5 megabytes.
All right, so that was the pitch encoder and the instrument decoder. Now let's talk about the synthesis. So the synthesis consists of two components, the harmonic audio and the filtered white noise. The parameters for the synthesis are generated from the instrument model. That's 60 harmonic components for the additive synthesis and 64 noise magnitudes for filtering white noise. We replaced the differentiable TF-Lite model with more performant DSP components implemented natively in C++, and this was one of the original intentions of the DDSP paper. This native implementation improved the performance by about half compared to the TF-Lite model. All right, putting it all together, how do we actually make this plugin run in real time? So one of the implementation challenges that we faced was differing frame rates. So we have two processes that are running at different rates. The audio callback runs at a variable rate, as it depends on the sample rate and block size selected by the user. And the model inference runs at a fixed rate of 20 milliseconds. We solved this problem by using resamplers and FIFOs appropriately at the input and output stages, as well as running inference on a separate thread. Here's a block diagram of our overall plugin architecture. So just take you through it. You get a chunk of input audio that gets pushed into the FIFO. Our end-to-end training in the Colab was done at 16 kilohertz, so we downsampled to 16 kilohertz. And now we run inference on the modified models we touched upon previously. And we generate a chunk of synthesized audio. We resample this back to the sample rate selected by the user, push it in the output FIFO, and then the audio callback pulls the appropriate number of samples from this FIFO. Now, at this point, we were running everything on the audio thread, but we ran into a problem where we were hearing audible glitches for smaller block sizes. In a typical DSP use case, the amount of computation load scales with the user block size. However, for us, the computation load is fixed for 64 milliseconds worth of audio data. So we decoupled the ML inference from the audio callback, and we achieved this by running inference on a separate thread at an interval of 20 milliseconds. This also resulted in consistent behavior across OSs for a given combination of block size and sample rate.
Cool, now we have a working real-time plugin. The next question is usability. So one of our guiding goals at Magenta has always been to democratize machine learning for artists and musicians, empowering creatives to decide for themselves how to use this new technology in their creative process. So besides the default models that we provide, we also allow users to train and use their own custom model. However, there's a problem. Not everyone has a beefy $2,000 GPU lying in their basement, especially an everyday artist. So to solve this problem, we actually created a custom Colab notebook that anyone can use. So to use this notebook, anyone could, click this link, upload a 10-minute snippet of monophonic audio, hit train, and this will send it to some random Google server running in Montana, and it'll spit out a TF-Lite model that you could drag and drop into this VST. So this allows anyone to train their own TF-Lite and DDSP model.
Okay, so the next section of usability is UX. So each instrument has its own range for pitch and loudness. Flutes play high, basses play low. But what happens when you feed lower pitches into a model that's been trained on higher pitches? We get some fun, cool new textures. And with that, we introduced tone shaping, a control that allows us to easily explore the space of sounds. So what you see here, the bouncing ball is a visual indicator of our current pitch and volume. You see this when you're playing real time or just playing back. The range of volumes and pitches the model was trained on are shown by the highlighted box. It's a little hard to see that on this screen. Maybe on that screen you can see it's like a highlighted purple box. When the ball is inside the box, we can expect a faithful reproduction of the timbre. And when it's outside the box, you can hear how the prediction breaks down in fun and creative ways. And we enable this by modifying the Colab to save this model metadata, that's the pitch and loudness ranges, in a way that's interpretable by our VST. All right, here we have a demo on how tone shaping works. That's now going through DDSP. Now we turn it on. That's resynthesizing the same thing. Change it to a flute model. So now you can see that the ball is kind of in that highlighted region. But you can also drag that box and do fun stuff with it. So as it moves to the left, you kind of hear a low pass effect. As you move to the right, you kind of hear like the higher harmonics being added in. All right. Oops. All right, and here we have Jesse playing the guitar and changing some timbres. Hard to see which model it is. Clarinet, to melodica, trumpet, violin. And next, so we were scouring YouTube and we found this really cool demo that a user uploaded. A quick look at that. So that's a guitar that's being transformed into a saxophone. It's one of our most popular models. And lastly, this plugin was used live at the Google I/O 2022 pre-show by the artist Miha. Got a quick video here. Oops. Oh. In the interest of time, we'll skip this one.
You can trust us.
Yeah. All right. Next steps.
Yeah. So if you guys watched the clip earlier, DDSP VST works and was able to be used at the 2022 I/O pre-show. So what are the next steps? I think there's a lot of lower hanging fruit to really improve on this plugin. So I think the first step is better pitch detection. As we said before, kind of due to the way we shifted things to be non-causal and how we really distilled the pitch detection algorithm, we still hear a lot of phasey and zippering artifacts in the plugin. So if anyone has any ideas on how to do better real-time detection, like we're all ears. We could also improve the rendering quality by running inference at a higher sample rate. As we said before, inference was running at 16 kilohertz, so we could probably bump that up to 44K. We could also improve plugin by enabling GPU support, probably for both the GUI as well as TF-Lite inference. And lastly, the original DDSP model, there's a learned impulse response for the convolutional reverb. So another option is to make this even more realistic to the original audio that it was trained on, is to store the impulse response in the model itself, somehow in TF-Lite.
And here are some links if you'd like to learn more about the project or check out the code. It's all open source. And another benefit here is that if you want a reference for building machine learning plugins with JUCE and TF-Lite or any other ML framework for that matter, please check it out.
Yeah, and something I do want to call out here is although you don't have to use TF-Lite as your inference framework. A lot of the lessons here can be reused if you want to do neural audio synthesis, such as distillation, and really cutting down the inference time of your model, and also how to deal with different frame rates.
Right.
Yeah, thank you. This was a massive cross-functional effort in collaboration with the Magenta team. So thank you, Megan, Jesse, Soren, Simon, and many others that helped. Yeah, thank you so much for listening.
Yeah. And we'll take a couple of questions. A bunch of questions.
Hey, great talk. For your pitch detection, I've seen some people use like self-supervised learning to try to get better quality pitch detection. Do you consider this for replacing your pitch detection model?
Great question. And I think that is the SPICE model, which also came out of Google research. I think it's a self-supervised, if I remember correctly. It did work great, but it was pretty heavy.
I will also say there has been a lot of developments in audio since 2 years, since we made a lot of engineering decisions during the architecting of this model. So the state of the art might be massively different, but I do see a lot of space, especially if there's an open source foundational model for audio being used in the context of pitch detection. So probably in the future, if I remember correctly, CREP was made in 2018.
Yeah.
So 5 years old, and that's like a millennia in AI world.
Hi. So my question is, I guess my understanding from what you presented is the decoder is basically creating parameters for an oscillator bank and a filter bank on this noise, and then you're rendering that audio still in the inference thread. So my question is, why don't you just pass those parameters to the audio thread and actually run those traditional DSP blocks on the audio thread instead? Would that not solve the sample rate issue that you were mentioning?
You can, and it's just something we haven't gotten around to. And so yeah, you're right. So since it's all done end to end, we just kept it all as one block. So you decode the pitch, do DDSP, and then do the synthesis. Even though it's being done natively in C++, it's all being done in one function. But yes, you can absolutely do that on the audio thread as well.
I think we actually tried that at some point, but didn't watch enough ADC talks on how to do programming. So I think that question, yes. Now with the knowledge that we have now, I think to the second question, I think the frame rate differential still exists. So you still have to kind of manage different frame rates on what the model was trained on, and I think that's still a problem.
How feasible is this to work with other synthesis models if you don't want to be like so faithful to the original? Like you want to have imposed like a quality of like, can you use this with FM or wave shaping or other kinds of things?
That is a great question. I don't know if I have the right answer, but I would think yes. It just comes down to how you transform those harmonic components and the noise magnitudes. So how do you render that?
I think it's also really how you recompose those differentiable elements and in unique ways, as long as, I think the core concept here is as long as the composition is differentiable, then you can learn whatever your arbitrary black box ML function. That's more upstream. So if you have a way to rewrite, say, FM synthesis or wave shaping, I would guess that it's possible. I hope so.
Any opportunity to use MT3 to start doing poly note detection with DDSP?
That would be a question for Jesse, but I'm not sure.
I think off the top of my head, currently how DDSP operates is monophonic, so I think there might have to be bigger changes to the overall model to get things working end to end. Basically re-architecting the entirety of the paper.
Got it. Thank you.
Thank you so much.
What is all this? Just continue, huh? I guess. What in the world? Never.
You can quit that and it'll just work.
Okay, back then or just red?
dot.
There you go. All right. Well, that's the right front page. Let's see if this thing works. Nope. I guess I don't really need it. Let me go back into full screen mode. Eventually. It gets in funny modes. Hey, it works. What do you know? So I'll try to get us back on time. So I'll shorten down to 15 minutes, something like that. Oh, I see. We got a timer. Okay. Well, okay. So I don't want to shave anything off the break. So my talk today is about using JUCE. Well, I don't need to sell JUCE to this crowd, but Faust maybe. So Faust is my sell here. Well, actually, I just want to tell you what I'm doing and why. And so I don't need to explain JUCE, but and you've seen Faust in a few talks already, so I don't really need to explain that either. So what I'm going to talk about is how I integrate it and why I'm doing it that way, and some interesting experiences along the way that I want to relate. So I'll talk a little bit about Faust. Does this thing have a pointer? Oh yeah, there's a pointer. Wow. So except that it's kind of wild. So I'm going to talk a little bit. I'm going to go quickly through Faust and then how I integrate in Faust and JUCE. I'm happy with it finally. I had to think about it a bit, and then and some interesting attempts at using ChatGPT to do some of that. So I'll show you that. So everything I'm saying is motivated by this one goal. Okay, it's how do you develop C++ as fast as possible? You know, you want to just get it done now. So you want to write it, and you want it to be right, and you want to move on to the next thing. And so for me, the answer to that really is to write it in Faust by hand. And I get a solid order of magnitude speed up over just writing C++. Now, part of that is that I'm not a great C++ programmer. I'm still on the learning curve. You know, I'm getting better. ChatGPT is helping with that. And JUCE helped me with that. Thank you very much. Thank you for the excellent practices that I learned from. And so, but even though I'm, getting there, that I don't have to look up at everything when I write, it's still faster, and I'll try to explain why, to write in Faust. So ChatGPT, I gave it a chance. It is not faster than writing in Faust because it doesn't know Faust well enough, and it doesn't actually know JUCE well enough either. It knows C++ really well. And if you start writing signal processing code in ChatGPT, it just is out of its depth. It actually just doesn't know very much. And so you get really toy implementations, sometimes just completely wrong. It's just not there yet. But for general purpose C++, it's very good. So the things that I've noticed that it's really deficient in is elementary signal processing, especially if it gets into complex variables. It knows something about everything, right? It can talk about it, but when you give it a problem where it's got to set up an integral and solve it, it needs a lot of coaching. And I try to make myself coach it through to the end so that they'll have the training data. I think the human reinforcement feedback is reinforcement learning human feedback. I think it is giving us a lot of weight, so I'm believing that and spending the time. But the bottom line for getting the signal processing written is writing it in Faust by hand. That's the current winner. This is just a screenshot of the Faust IDE, the Integrated Development Environment. That is, it's a lot of fun. You can hit play, and this is the block diagram automatically drawn by the compiler from the code here. And you can select the DSP and see it running and get your GUI primitives and try them out on a sound file that you can loop, or you can play it from MIDI and the MIDI, keyboard. So it's a great environment for prototyping, getting things working, and learning about it. Oh, and I should mention you can pop up all the examples and take a look at all the libraries up there. So I just wanted to mention that as a good entry point. And I'm going to breeze through this overview because I think you've seen some of it, and you can. Mainly, I just want to say it's a really great domain-specific language for specifying block diagrams. And so you're not programming samples, you're programming block diagrams. You're slinging signals. So you're writing in terms of signal processing at a higher level than samples. And I think that's really a huge acceleration You don't have to do any allocation. You don't have to do for loops. You can't really do for loops. So it's no debugging on the sample level. And this is the key. When it looks right, it's usually right. You look at that block diagram, and if those blocks are tested and you've built something, it doesn't matter how big, if it looks right, it's probably right. And this is basically where I get my order of magnitude. And another thing about Faust is that it'll generate all these languages. So, and more than these. It includes some good embedded options as well. And so I mentioned the GUI primitives, and so we'll see those again. And the way you bind a general purpose Faust program into a particular environment is by means of architecture files. So you can think of it as kind of a standalone program or plug-in that you then insert. It has hooks in it for the compiler, the Faust compiler, to insert the general purpose C++ that it generates. And so there are many, many architecture files for reaching all these platforms, which is really great. You know, I'm normally on Mac or iOS, but you can also go to these embedded options down here, VZP Rack. There's really quite a lot of nice options. Now this is an example I like just to show you the generality. So here's this one-liner. So process is the only required functional programming language, so you've got to specify the function process. And so in one line with these definitions, you can specify a completely general state space model. So that's the general causal linear time varying system. And so each of these matrices, these 4 matrices, can change every sample. And here's the initial conditions if you have them. And your state variables are these feedback delays. So you get a delay automatically when you feed back a signal. So those are one sample delays, and that's where your state variables go. This is a completely general linear time varying network, anything you want. And of course, you can also do nonlinearity. So you can saturate the outputs and put sigmoids in there and switches and all that sort of thing. So we've already seen the Minimug. I thought I'd throw it out again. This is the Qt interface that's used. Totally standalone Faust. This is a Faust standalone app. You just say Faust to Core Audio Qt in this case. And so you can see the 3 oscillators and the voltage control filters, the contour, you know, the envelopes and the usual things. The switches are all there, and even the feedback from the output to the input. So it shows you how much you can do, more or less, with the built-in GUI primitives of Faust. Horizontal groups of vertical groups of horizontal groups, etc. And there's all these knobs are either horizontal or vertical sliders, and if they get long and skinny, they pop into the right orientation, that sort of thing. So, so integrating JUCE. Well, the easiest thing you can do is just run Faust to JUCE. That's a bash script, and you. What it does is just use the right architecture file and spits out a JUCE project. You know, you just open Producer, build it for Xcode or whatever you want to use for your IDE, and build your standalone plugin, and there you are. And so it looks a lot like the Faust Core Audio thing, but it's got your JUCE look and feel. You know, you're in JUCE, and at that point you can take it over and do whatever you want. But there's one more level that you should consider, that I had to consider, and that is, while the standalone apps are great for initial testing, and the script will get you into JUCE, you can't bypass pieces of that. So that all those oscillators and filters all running at the same time, and if you're not using 1 or 2 of your 3 oscillators, you're still paying for it. Your CPU is still running. And so if you need to bypass pieces of it, then you're going to want multiple modules. And so you normally would have like an oscillator.h that's generated from oscillator.dsp. So it's a standalone Faust module, just doing an oscillator, nothing else. It's sort of your minimum runnable unit. And then you instance that as many times as you need in C++. And so you do that for all your modules. And then you do any bypassing in C++. You know, if you don't run it, it's bypassed because all the processing is in place in JUCE. And so another reason you might want to do something more than just Faust to JUCE is to take over the GUI. And so I'm told that most people just really write it directly in C++ using the paint function. You know, just write their own paint function. That's a lot of work. And I like Nick, I heard about the WebView-based GUIs coming. So we're looking forward to that. That'll be great. And my own GUIs are really just research prototypes. I don't really want to spend any time on them. And so if I could just translate the Faust GUI, I'd be really happy. And I was actually quite happy with the GUI editor in Producer, but now that's deprecated, so looked around for something else. And I also found that plugin GUI Magic was nice. Daniel Waltz's system is really nice. Here's a screenshot of it. You saw it earlier today. So there's the editor on the left, and you can, you know, this is basically your value tree here. for the GUI, and you can select something and set its properties and hook it up to parameters, and that's all you do. So to integrate your Faust into JUCE, all you have to do is define an audio processor parameter wrapping each DSP parameter, each Faust parameter, and then once you do that, it'll be here in the menus. You can just dot it up and hook it up, and life is good. So Faust parameters are different than JUCE parameters. In the Faust world, the Faust parameters live in the DSP module, essentially the slider state. So every time you drag out a GUI element, that provides a kind of a controller interface, and it's got its own state variable, and it's in the DSP module, not the interface. So when you make an interface, it just gets pointers to the state variables. And so you can have any number of interfaces, and they're just all pointing into the state variables of the DSP module. And so another interesting difference is that the parameters are all Faust float, and those usually just float, and they're assumed atomic in hardware. So in JUCE, you'll see standard atomic pointers to the parameters, but in Faust, it's just use atomic hardware primitives. So on a 32-bit machine, you expect 32-bit float to be atomic, and so on. And I'm told that ARM and Intel have this worked out, and we're okay. And I've never run into an issue, but it's something to know. So in the JUCE world, you'll have your plug-in parameters. They have to be in the audio processor because the editor is optional. And then if the editor is up, then it will have its own copy. And they have to they have to synchronize each other. So they use listeners primarily for that. So each GUI element has listeners, parameters have listeners, and a GUI element will attach to a parameter, and the parameter will listen to the GUI element. And so that's the pattern there. But I was really happy to learn about the raw parameter pointers. This is very much like Faust, and if you use these, you can basically use the same kind of parameter scheme, and they can be brought together very efficiently, and that's what I'm going to show you now. So the question, though, I had was, can we get it down to one? So can we make the audio processor parameter raw pointer to the parameter refer to the DSP state variable? Wouldn't that be slick? Because then you would have exactly one instance of that parameter. You wouldn't have to synchronize anything. It would just, if you change it, everybody gets it, and make it standard atomic. So I asked ChatGPT, can I do that? And so I had set up a little context, and then I said, can I make my JUCE game parameter refer to a pre-existing memory location? And it says, yeah, you can do that. You just create your own custom parameter class inheriting from ranged audio parameter and override these methods. And here's an example. And the example was very good. It did not quite run, but it had to be finished. And but it was a good idea. I mean, I thought it was the right answer. As far as I know, it's the right answer. I got the people here to correct me if I'm wrong. And it was very simple to take a look at the audio parameter float source and finish it off. And I think that's the answer. So do we do that? Is it worth it? And I decided it's not worth it because of the atomic float star raw pointer. You can refresh just when the parameters change, such as a MIDI controller event. MIDI controller, if you're in a high performance MIDI pipeline, you're probably just running from MIDI, right? Because those are the ones that are time stamped. You get them with your audio buffer, and you want to come in and update parameters, and then those parameters want to get propagated instantly on the audio thread. No thread switching, please. And so here's some pseudocode to just illustrate that. And really, you can just look at the synthesizer voice to see essentially the same algorithm. You just basically run. You go through the MIDI messages and see if the timestamp is in the future, and if so, you compute audio up to that time, and then you execute that MIDI message or propagate it out. And it will then possibly change parameters. And if a parameter gets changed, then you want to propagate that forward to the DSP module. And so here that is. So it's just a standard atomic writes Faust float. And that's a negligible amount of work compared to just processing the MIDI message. If you go down into that, you see gestures beginning and ending and notifications and so on. So that's good enough. I think we're done. Okay, so that's high-speed integration, no wasting, no messing around, right? So for the last usage of AI to get from Faust to JUCE, I encountered a situation where I actually needed to translate Faust as a language to C++. Even though Faust compiles to C++, I needed to actually translate it. And there can be some reasons, for example, to add SIMD. There's no SIMD support as far as I know in Faust. And, but the case that I ran into was I needed to convert the pattern matching macro arguments. I think of them as macro arguments. They're compile time constants that get manipulated by the pattern matching system. And they have to be known at compile time. They're not changeable at runtime. And so I needed that because I needed the filter design primitive to run at any order. I needed to be able to instance a filter at any order because I needed essentially all orders up to 50. And so I didn't really want a giant array of precompiled Faust modules for each and every little order constant, right? So I just wanted to change it to C++ so that I could have a constructor that had that order. I don't mind it being at construction time, but I need it to be, at least that. And so can I rewrite the low-pass primitive, which is Butterworth, in C++ using ChatGPT? And the answer is yes. It was actually quite easy. And I was using 3.5. This was before 4 came out. And it got me almost all the way there in one iteration. But it was funny because it didn't really know Faust. It was really just kind of translating functional syntax from Faust into C++. But it was helpful. It was helpful. And then later, and I also converted all the comments to Doxygen format, which was helpful. So it was really happy. And then I also had good luck, better luck actually, going from MATLAB to Python or MATLAB to C++. So those translates, if it knows the language really well, you're going to have better luck. But it's a good translator from any language that it knows to any other language that it knows. And so it also writes decent unit tests. So the conclusion is it works. And what we need now, though, is JUCE GPT. So in my last 3 minutes, I want to emphasize that. So just get something, Copilot, get over what you want from Amazon or Google or OpenAI, and fine tune it on the latest JUCE distribution and all the updated examples, and life should be really smooth at that point. And so next Saturday is Faust Day at Karma, and I'm giving a talk. I'm going to go more in detail about this Butterworth to C++ translation, because there were some really interesting things that I observed. And I'm going to go, I have an hour-long talk there, I can go farther. And it's free online and in person, and there's a link here that should work in the overheads if you grab them. And so just to summarize or conclude, the ChatGPT 4 is really useful for general purpose C++ development, not signal processing development. It's good for any well-known language translation. The quality of the model seems to be proportional to the amount of data that hits that case in the latent spaces. We know this since the LMS algorithm in signal processing. Is that it's the data that drives the convergence of the weights in the model, and so that's a billion-dimensional, hundreds of billions of dimensions, and you've got to go push all those little corners of the latent space forward with training data, or else they're going to be dark, and who knows what you get. And we enjoy that too. And it's also been writing unit tests, but in signal processing, you have to debug them quite a bit. In JUCE, you have to debug them quite a bit. Formatting comments is just great, and there can be more. And I can see I'm down to my last minute, so I will leave you with a limerick. So I asked, write a limerick about JUCE. And I had to edit even that. So you heard my edits for the human feedback, reinforcement learning improvement. If you disagree with my edits, then let me know afterwards, and I'll submit a correction. So I think I'm actually on time. So more on Saturday. I'm trying to find that link. Actually, it's cached. Any questions? I guess we have 2 minutes, 1 minute for questions.
Is ChatGPT any good at SIMD?
Yes, I've.
Oh yes, is ChatGPT any good at SIMD?
Yes, I've had very good luck, just introducing SIMD into my code with using ChatGPT to get it started, and it knows about all sorts of header files that I don't know about. It's just a great way to get started on something like that, and it will alert you to various distributions. You can then You can see the header files that it's bringing in. You can search for them, and before you know it, you're in all the right doc. So it's a really good first thing to do, is just ask ChatGPT. I leave it open all the time.
Hi. So I'm a big fan of using ChatGPT when I'm coding. I think it's really interesting to generate boilerplate. But one of the things that it does is kind of push the impetus from you writing the code to you reading and auditing it.
Yes.
Like, have you come up with, I know this is a super new idea, but have you come up with any ways to like verify correctness? Because obviously it hallucinates and goes off the rails a lot, but the boilerplate part is a real benefit. Have you come up with any solutions to verifying correctness and not falling asleep and allowing some bug through?
Well, the two things, I run it and debug it, and I usually have to do a fair amount of debugging, and I make it write its own unit tests. But of course, I have to debug those. But at least you get a lot of, and you can really, see that the coverage is good. So you can try to get 100% coverage unit tests, and once they all run, you can see what they're trying to do, and they're reasonable. And after a fair amount of flailing around, it's good, solid code in my experience. And of course, you understand everything and can read it. And if I don't understand something, I learned some C++. I learned about the raw string literal beginning with capital R that way. I asked it to create parameter layout for me because I don't want to write 2 screenfuls of code just to get my parameters. I wanted like an old Music 5 computer music style notation that was like 5 lines, right? And so I tried to teach it as an example. Take this little terse description and turn it into 2 lines of audio parameter float instance. And it wrote me a program that accepts my syntax in a raw string literal at runtime. So I will never write another create parameter layout again. I will just give it that string, and it returns the layout, and I'm done. I'll never have to see a page of code for 12 parameters. So I was so happy with that. I did the same thing in 3.5, and it just wrote it. It wrote it, as you would expect. But in ChatGPT 4, it gave me a language translator, or a syntax or a macro processor, whatever you want to call it. It's really, really very nice. So you have to work hard, but when you look back on it, you've saved at least twice your time, I find. And if you're lucky, 10 times. It's a 10x speed up. And people are talking about 10x programmers, and I think that's where we're all going. We're all going to be 10x programmers pretty fast. It's going to be good. Keep recognizing people. I guess I better take this.
All right, 1 second here. Screen decided to go black on me, but that's okay. Much better. All right, how's everyone doing? Good, we're almost there. Try to get us back on track. My name is Ryan Frias. I'm a software engineer at Skywalker Sound. I've been there for a little over 11 years now in different parts of the building. For those that don't know, Skywalker Sound is a post-production sound company, that is. We've been in the business for over 40 years doing sound for film, video games, TV shows, you name it. We're located at Skywalker Ranch, which is just north of the Golden Gate Bridge. Has anyone been there before? Awesome. We're honored to be here today, so thank you for having us. I'm here to talk to you about processing audio post-production deliverables at scale with microservice architecture. Mouthful. Let's go into it. Okay, so in the past 5 years, we've seen an enormous growth in both content production and the audience that content is delivered to. In general, more media is being made at incredible scale, and every company seems to be producing media, such as Disney, Warner Brothers, Netflix, Comcast, Amazon, and so forth. At the same time, the rise of direct-to-consumer streaming has driven faster adoption of technical formats, codecs, and standards. So when you combine this higher number of titles with more languages and in more formats, it creates a really big matrix of hundreds, often thousands of audio deliverables to create for a given title. So why are there so many versions, you might ask? In the world of post-production sound, this means that for each language, making unique soundtrack versions for different purposes, like the web, your phone, mobile, obviously, DCPs, archive, home theater, marketing, audio description, different loudness versions to hit different territorial requirements, encoding formats, and so forth. For example, there could be a 712 requirement for a set of loudness specifications, a 5.1 soundtrack with the same loudness specs but with different head and tail leaders. There could be a requirement for stereo at a target frame rate that might differ from the 5.1 and 712. And I kid you not, there could even be a mono guide track or deliverable that the marketing team might need. Yes, mono is still a thing in 2023. The list goes on. It's a lot to produce and manage. So how do we deal with this? Well, traditionally, creating those unique versions requires rounds and rounds of manual tasks that take time away from the creative process. These are expensive tasks. The work is done by re-recording mixers sitting on a real mixing stage in a theater. We have a number of them at Skywalker, and a bunch of sound editors that are standing by to assist the mixer in creating these versions. There's all sorts of special equipment involved. Obviously, you have speakers up above, around you, mixing consoles, a lot of computers, a central machine room, and also all the support personnel that kind of goes along with that. It's common for this process to take a couple weeks for a feature film. So our challenge then was how could we dramatically improve the speed and quality of this process when each show is so unique? Coda. I'm here to talk to you about how we're achieving this all with Coda. We've put all of our institutional knowledge that we've learned over the past 40 years into Coda, all while maintaining top quality sound deliverables. We've used Coda on a ton of titles, about 170 plus titles, including Mandalorian, Moon Knight, WandaVision, and Andor. And we've reduced the time it takes to create versions from 1 day down to 30 minutes. The creatives have embraced Coda because from their viewpoint, the system creates versions that they can't simply do with existing tools given an allocated amount of time. They see great results on time savings. This means the sound team can focus their time creating a better soundtrack for your enjoyment. And with production schedules getting tighter and tighter, and post-production being one of the very last steps in the post-production chain, any time saved is huge for us. So what is Coda at a high level? Coda is a system that takes in a soundtrack and generates all the technical versions or adaptations from it to hit all the different distribution endpoints. All of our core DSP is written in-house. But to do this in any flexible way, aside from a super strict pipeline that has precise inputs, outputs, and steps, we design an intelligent workflow engine. This engine looks at what you're passing in as input, and it looks at what you want on the output side, and it generates, it dynamically figures out the best processing path to take. It also reuses mezzanines and intermediate files so that nothing is ever, we're doing efficient processing, and not, processing material that we could have reused. So for the workflow engine to know how to arrange the skills, we have this concept of skills in Coda. Each skill represents an ability. This one is a loudness correction. We register it against Coda using a JSON API document. And these skills aren't sound specific. These could be file handling, encoding, packaging requirements, different output format specification. So it's not limited to DSP in particular. Here's a list of skills that we have. It ranges from loudness correction, true peak, frame rate conversion, encoding, data I/O is our transfer, accelerated transfer network, summing, dynamic range control, file renaming, adaptive downmixing. Because they all implement a common interface, it makes adding new modules relatively easy. For example, if another encoding technology, say from Dolby, comes out, we can easily insert it into our pipeline. We dynamically assemble all these skills to form a pipeline to produce the output deliverables that you want. So for a given set of input files, the pipeline might look like this. So input files coming in on the left, and we figure out, based on what you want on the output, what sort of steps we have to take to get there. We certainly optimize it as much as possible, like I said, using shared mezzanines so that no other process is stepping on each other. The graph might look completely different from another set of input files, but using the same output specification. It basically reacts to what you give it to us, and we figure out the rest. We've kind of abstracted it all away from you. So let's talk about these skills. So what are these skills on a lower level? Well, they're really just Docker containers. We containerized all these components so that we could scale them with Kubernetes. Has anyone heard of Kubernetes here? Awesome. The containers spin up on a per job basis, so they're ephemeral. They spin up, process the audio, spin back down to meet the demands of the workflow. They're never sitting idle. So our compute resources are efficiently used. Separating these components out into different microservices or containers lets our teams develop or improve just a single component of the entire platform without affecting the rest of the chain. The components use semantic versioning. That's just what we use internally. And the benefit is that we can reuse these components elsewhere at Skywalker in our internal processes for internal tools, external tools, and so forth. So as an example, here's a modest-sized job and all the containers it would spin up in Kubernetes. The input is coming in on the left, and all the outputs are kind of flowing over to the right. It's a ton of nodes that actually get spun up in Kubernetes as Kubernetes jobs. In reality, it's just a big, giant graph at the end of the day. Kubernetes helps schedule these containers across multiple nodes, but we're leveraging Netflix's Conductor, which is an open source project that you can find online, to help us execute these workflows. So this giant graph, higher level graph, all boils down into a conductor graph, which looks something like this. It goes from top to bottom. We have an ingress node at the very top that gets files into Coda platform, and then it flows down into our DSP graph here, which we dynamically compile based on your inputs and what outputs you have declared. And then we start to package them, and then we send them off to their destination. Okay, so like I said, Kubernetes helps balance these containers across nodes. Kubernetes helps round robin these containers so that, for example, frame rate conversion ends up on one node, down mixing and true peak on another, DRC, dynamic ranging control, and summing end up on another node. And we could also scale horizontally too. So we could just keep adding nodes to our cluster, and then Kubernetes will help us balance and round robin those across all the nodes, which is pretty cool. If we take a step back, we could actually deploy jobs or Kubernetes jobs across different sites, so on-premise, private clouds, public clouds. We actually have an accelerated data transfer network that when the files are done processing in Kubernetes, we actually can ship them to their destination. And a lot of what we do at Skywalker is really finish the job, but then there's a whole laundry list of people that we have to send those deliverables to. So we've automated that as well. And this is a fun slide. I could actually talk a whole hour on this, but this is our stack from low to high. At our core, it's C and C++, of course. We end up creating a lot of static and shared libraries that we can actually link against to in Python and in Go. We have a lot of C++ code at Skywalker. There's a lot of Python code. Our R&D and ML team love Python. More and more stuff is going to Python. PyTorch is a framework that our ML team is using. More recently, within the past 2 weeks or so, we were looking for solutions for cross-platform apps that is not Electron. So we went with Tari and Svelte, which gives us Mac, Linux, and Windows client-side apps. It's where Rust kind of makes an appearance in our back end here, or in our stack. We have a lot of Go code at Skywalker. It's very quick to compile, super rapid iteration. We end up binding some elements of C and C++ libraries against our Go code so that we could hand off the DSP to more performant code there. Our UI team is using TypeScript and Next.js. Going up the stack, we use in our local dev environments, and in CI, we use GNU Make, of course. Tilt is really awesome. It's an open source project that allows us to spin up the entire Kubernetes stacks right on the laptop. So that entire architecture I'm able to spin up on this thing right here with Tilt. So you could actually bring up all the components for that Kubernetes stack right on your laptop, which is really nice. We take testing very seriously at Skywalker, so Google Tests, which was shown earlier in the day. We do a lot of testing in Go, Python. We try to have a sensible code coverage percentage, 80%. If we don't get there, we don't get there, but it's worth a shot. It's something that we strive to do. At the core of our software development lifecycle is GitLab. It's all all-inclusive. So everything is sort of managed in our GitLab, our private GitLab instance. Every time we push and do a semantic release version number for C code, it builds all the static and shared libraries that we could pull into the Docker containers, which ends up getting security scanned by Sneak, and makes its way into Red Hat Quay, which is our container registry. So every time we push code, or git push, or actually tag it, we actually end up running a ton of security scans against the open source manifest as well as the container image, and you'll be surprised how many security vulnerabilities pop up because of that. So we're able to actually, in almost real time, identify what the security vulnerability is, make a patch, and in the base container image, and off we go. So we get 2 layers of that at Sneak and Red Hat. Conductor, like I said, is made by Netflix, so that's what's helping our workflows get executed. You don't have to have Kubernetes to back a Conductor to execute the workflows. You could use curl on a local terminal, and it'll use your compute on your laptop to kind of execute the graph, which is really nice. We use MySQL, good old MySQL, for our basic backend. We use Redis as our in-memory store database. We use it as a message conduit between the containers and Kubernetes. We also use it as our caching layer, pub submodels, and all that sort of fun stuff. We have a presence on Amazon, so we use DynamoDB for our authentication layer, which we'll see in the next slide. As we work our way up the stack, we have Terraform, which helps us deploy and version control of all of our deployments for Coda. Kubernetes, we've been talking about the whole time, helps schedule the containers on different nodes. And AWS, we have a presence on there with Lambda, and we've built an authentication layer on top of AWS Cognito, which we're calling Sprocketauth. We wanted to conveniently aggregate multiple IDPs into a single platform, and AWS Cognito ended up helping us out there, which is really nice. We're using Resilio Resilio Connect to do our accelerated data transfer to Kubernetes and out of Kubernetes to the destination clients. So thank you for listening. We have 3 minutes left, so if there's any questions, feel free to ask.
Check. Oh,
Hey, that was fantastic. Two questions. So one is, what is your solution for observability? Because I'm sure if things go wrong, you're going to get paged in the middle of the night.
Yeah.
And then secondly, how do you quality control the output? You must have some kind of automated, quality control.
Yeah. Great questions. Datadog is our first one. So we have a Datadog agent sitting on Kubernetes that helps us actually visualize the entire call stack, which is really nice. Go has excellent built-in metrics that we use as well. For your second question, how do you validate the outputs? GitLab, all-inclusive. We could schedule cron jobs. I have a cron job that runs every morning at 2 a.m., and we could validate the outputs of that, writing basic bash scripts, what have you, to assert the output. We'll have a set of golden masters or golden images that we process the graph to, and we assert the output of each sample.
Great talk. When you're doing this containerization, are these individual processes operating on the entire piece of content and then it goes to the next process, or are they kind of more block-based? And then separately, are all like the individual movies different? Like I imagine there's some efficiencies you can gain by batching some of these things up across different titles.
Yeah, that's a great question. Our DSP team would probably be more inclined to answer that one. But yes, so we're file-based, so we have access to the entire file. We could seek through the entire file if we wanted to. They operate on them on blocks. And your second question was, I'm sorry, what was that one?
Efficiencies and parallelizing.
Oh, right, yeah. So a lot of that stuff, you notice in the conductor graph, there's, within each horizontal row, there's processing blocks that could be parallelized there. Obviously, there's some pieces of content. It's content dependent, so large action movies with, loud explosions and stuff may be processed a little bit more efficiently. Not as many peaks to catch than a narrative form. So we gain some processing efficiencies there.
Follow-up to the QC question that was asked earlier. Versioning often takes so long because producers want to watch, every single version themselves to make sure it looks good. And you mentioned there are some automated workflows in the pipeline, but I'm curious as to whether that is actually, like on the client side, is that actually accepted? And you mentioned time saved earlier in the whole process. So I'm wondering if actually on the client side that is true, and do they actually still have to watch through every version themselves, or is the automated workflow sufficient for, on the client side for their confidence level?
Yeah, that's an excellent question. A lot of our mixers like to just naturally take a listen to everything in the end, but yes, it has become an accepted pipeline and trusted pipeline at Skywalker. Obviously, we have had a number of titles use the platform. A lot of what you hear on those platforms are generated through this pipeline, which is really cool. So yeah. Yeah.
Yeah, just quick, I can be probably loud enough.
Sneak.
Yeah.
What? I understand this is all your own stuff. Where's the security malware issue coming in here?
Yeah, so Sneak, in containers, you have a base image. It could be Ubuntu. It could be some form of that, and those inherently have operating system level vulnerabilities. Like Log4j, when they came out, all of our CI pipelines were bright red. So you end up going in there and fixing every single one of them. We try to use distro lists from Google, distro list containers, which have the bare minimum of OS dependencies in the container images, so that we don't have to deal with any unnecessary dependencies like libcurl or something like that.
Yeah, I see what you're saying. Since you've got third-party dependencies in these distributions, something bad could happen.
Yeah.
Well, I got to say, I am blown away by the complexity of this thing. I mean, it's kind of amazing what you're doing. Now, this example you were showing was basically just for one movie, say, making all the different formats and just having this massive parallel jobs to do all the signal processing.
Yeah.
At once.
At once, yeah.
Wow. In a half hour.
Yeah.
I give up.
Thank you.
You can turn that off for now. Okay, let's see. All right, so hey everybody, I'm the last talk of the day. My name is Aurelius Prohaska. Closing this conference is a real honor. This is a sequel to a talk I gave a keynote address I gave at the 2018 ADC in London, and that was a great experience. So I'm glad to be back again. That talk was also called Democratization of Audio Development, and I know I have a lot of friends in the audience today who may have seen that talk, and I also gave a version of the talk to the Bay Area Music Tech Meetup. So some of that is something some of you are familiar with, but if you don't know it, don't worry, I'll get you all caught up in a few minutes. First, let me just define democratization, just so we're on the same page. It's just taking a technology and making it available to everyone. Obviously, all the presenters today, to a certain extent, want to get their ideas out to an audience. And we're streaming this to the entire world. So we understand that the need to get information out to people so that they can feel comfortable in their audio creation experience. And so I think I don't have to tell that to you too much. I think this is a good idea. So let me give you a little bit of my backstory to tell you why anyone would want to listen to me about this topic. More or less, I'm here today because I created a framework called AudioKit. All right. Yeah, okay. Yeah, and believe me, I see both sides. I think we all have a love-hate relationship with all our tools, whether it's our computers or operating systems, languages that we've chosen, IDEs, for heaven's sakes. Audio frameworks are just another one of those things. But my relevant experience is not in my coding ability per se. It's about acting as the steward for AudioKit for the last 10 years. AudioKit may not exist without me, but it would have not grown to what it is now if I hadn't adopted an open philosophy of opening the development to everyone. AudioKit is free because I didn't have the qualifications when I started to warrant charging for something that I was creating in this realm. AudioKit is open source, kind of for the same reason. I was hoping to get bug reports and user contributions. But to me, AudioKit is not a framework. It's a community of people. All of them I consider friends. Some of them have graduated feeling like family members. And, from the day when I was just learning about audio development, we've grown to a company, and we've released tons of apps, some of them open source and free, some of them closed source and paid. We've released about 20 apps using AudioKit, just AudioKit Pro. Hundreds of people have used it to create their own apps, but just AudioKit Pro is about 20 apps, about 2.5 million downloads of synthesizers, and I think over $1,000 made. No. But yeah, AudioKit is a collection of repositories with I think we have over 10,000 stars on GitHub. Those repos include some sub-audio kits which specialize in a certain type of DSP. And we have a whole collection of reusable UI components that anyone can put into their apps. There's a microtonality repo that's all of Marcus Hobbs' work with scales. And Tonic is a music theory library that Taylor and I wrote. In fact, all the stuff Taylor has a huge part in, and wouldn't be possible without him. where we definitely want to get our tools out to the world. We put a lot of work into that. And I'm just trying to show you that a lot of good things can happen to you when and one slide I forgot to put up here, someone actually wrote a book about one of our synthesizers. There's a book about Synth 1 and how to do DSP with it. So we're all, I think all framework developers, JUCE, everybody, we're all about getting our tools into other people's hands. Cycling 74 is this cool rainbow thing they just came out with, and Jules is doing C major. There's a lot of innovation happening. And my mission with this talk was update my previous talk in 2018 to see in the last 5 years how we're doing with democratization. So I did what a lot of people are doing these days, especially Julius Smith. I asked GPT. In fact, I asked it to write my entire talk. So speaking as me, the creative audio kid, and the keynote speaker, blah, 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 how are things going? And it did this a few times, and it hallucinated a lot the few times. But eventually, it came up with this answer, which I recorded, and it's pretty good. And if I'm just going to like read it to you, I don't know, that's probably not very fair to you guys. If AI can write your talk, then, you know, why bother? We're humans, we should have more to add. So I thought, well, maybe AI could help me see how we're all doing with audio development from the standpoint of beginners or new users. I was curious, did we save our own careers by not documenting audio development well enough? or did we doom ourselves to not having that tenfold increase in productivity that everybody else in other fields are having? So yeah, I really feel like the internet, for all its greatness, and I've been doing stuff on the internet for like 30 years, like it's going to be remembered in history as the training set for AI. Like that's going to be the main thing. Everything else we thought was so amazing about all the relationships, doesn't matter. It was all that it trained AI. And so I figured, well, if it's doing all this, it can be used as a measuring stick for how we're doing with audio development. And so Julius pretty much scooped my talk, just 2 talks. This might be the fastest response to a talk ever in the history of this conference. But my experiment was I was going to try to use ChatGPT to create a siren sound in a variety of audio platforms. So I started so I just asked it as a complete beginner, I want to write a siren sound. And so it understood what a siren was, and it decided to use Python. Now it's machine language, it's the AI. Of course it's going to do Python because it's the language of machine learning, right? So, and it created it, worked fine. But I didn't want to use Python. I wanted to do something that I was more familiar with, an actual a tool that was for audio. So I started my audio development career using Maxime-ESP. So I asked it to create me a siren using Max. And it proceeded to give me instructions on how I would do this in Max. Now, I don't want computers telling me what to do. I think that's exactly what we don't want out of AI. This is telling me, okay, I'm the ruler now. So it eventually did give me some code, but it was very hard for it to write this code, and it didn't work. I don't know if it was a hallucination or it also kind of just got bogged down. So I don't exactly know what was happening there. But like Julius was saying, if you have a little bit of inside knowledge, or if you can tell us and give it some more information, you can guide it along. So I said, that code didn't work, but I'm using Max 8, and it says Max 5 patcher. Can you give me something in Max 8 that would work? And so it again gave me some instructions, and this is all real time. This is exactly how fast ChatGPT 4 is these days. I almost wanted to do this talk live with ChatGPT, but it was too dangerous. It's still too volatile. So it gave me this code for Max 8, and it did load. And it gave me this. So it did not wire up the boxes properly. Interestingly, it laid it out as if it were a flow from left to right, as opposed to up to down, which is the standard for Max. So I don't think it did a very good job with this. And I wonder if it's it could be a bad thing for Max, because Max is us thinking about how we want sound, and then we have to think in a graphical frame of mind. So then the computer makes sound for us. And I think large language models have a hard time replicating that. And I think that's kind of unfair, unfortunate, because like I said, I think the Rainbow project for Maxime-ESP is quite cool. But box line development, at least currently, is not working so well with AI. So I'm the AudioKit guy. I say, how will it do creating a siren sound in AudioKit? And well, thank you. It's a powerful audio synthesis framework. Yes, I like you, AI. The only problem is, and it's kind of flying by here, but I can tell that this was written in AudioKit 4 syntax. ChatGPT is very 2021 centric. So it gave me something that wouldn't work if you had the most recent version of AudioKit. But I had that insider information. I said, that's the wrong syntax. Can you use version 5? And it said, sure, which kind of annoyed me, because why would 4 would ever be better to 5? Maybe there were more examples online with 4. So it got this right. It used a timer, which I didn't like. So again, I had some insider information. I said, well, I really want you to use something called AudioKit operations to get the siren sound. And again, it's, oh, yeah, you can do that. And it finally produced the output that I wanted it to produce in the beginning, the one that would have been the best one to do it. But it didn't do it without my insider information, with my coaxing, which is, that's the trick here. On the day before I gave my keynote in 2018, JUCE announced Soul. So I thought, well, that's nice. 5 years later, how does ChatGPT do with Soul? And interestingly, it sometimes would tell me I can't write in Soul, so here's some pseudocode, and other times it would say, okay, well, here's the processor. And it never worked, but I wasn't sure if that was ChatGPT's fault or just the Soul IDE online was not working or something. So I said, well, JUCE has moved on to C major. Maybe you can write me something in C major. And not to poke at JUCE or anything, but it says we don't know about C major. In fact, sometimes when I would ask it this question, it would say, I think you mean the chord, right? Because that's the context I know a C major in. So, I got the feeling that maybe it's just languages that are older, frameworks that are older, ChatGPT AI would be better at. So I asked it about C-Sound. Now, C-Sound and I have a very complicated relationship. We're kind of divorced. And I didn't like using it. I went away from it as soon as I could. I didn't like that I found a bug in C-Sound, and they said they won't fix it because it might change some professor's piece that he wrote in C-Sound from the past, and it would just sound different. So it can't compile to the same output. We can't fix that bug. We can document it, but we can't fix it. But to my surprise, ChatGPT not only wrote working code, but it did it almost the same every time I asked. It was very consistent. So having the C-Sounds, if you like it or don't, I don't, but it's consistent. And it's been there for a long time. So it's been, AI's well-trained in it. So I tried a bunch of other platforms, and I'm sorry I didn't, SuperCollider's not on here, but I did try it. And so I had these kind of how was the initial response? How much tweaking would it help, and how consistent was it? And so, like, I don't think anyone really, well, different platforms did differently, and everyone's experience is different. Like, I think the ones that say consistent here, like AudioKit was consistent but old, C-Sound was just consistent but crappy code, and the one that I found most interesting actually was Faust. Faust, not every time, but this time, it gave me a very quick description of what a siren was and what it was going to do, and then it wrote me in like almost an even quicker code to do it. And it boiled down my question into a series of inputs and a one-liner about how to do it. And it was a one-liner that I could plug that code into the online editor, and that's what you guys heard earlier. I actually had this, you can turn up the sound a little bit now. So yeah, you can turn it down now. I asked ChatGPT to do something for me. Sorry, I'll go back to my slides here. And it did it, and I could immediately test it. And so I think that's pretty good. In fact, let me go back to this slide for a second. I found the recipe for success is good documentation for our frameworks, text-centric languages, a stable API, and a quick and easy way to test the output of ChatGPT. So you could, like with AudioKit, you'd have to run it in a simulator on Xcode. It's a little bit harder than just going to an online editor and pasting it in. To your point too, like there is just because ChatGPT is not well trained in our frameworks, I don't see why we can't take the large language model that it made and train it ourselves on our specific documentation. In fact, I think future versions you might be able to say like, go consume the documentation at the C major URL, and then now write me the siren. It doesn't do that yet, but I think that's really a reasonable, probably something we're going to see, another 90 minutes of development. We'll probably see that one coming up next. Yeah, and the other thing is, in the end, I actually don't necessarily care how the sound is created, especially as the person I was pretending to be online. I just wanted to create a siren sound. All the things that we worry about as developers, like dropping frames, glitching, threading issues, I kind of feel like all this stuff really should be taken care of by AI. And when people program user interfaces, how often do they worry about a pixel on the button they created having a flickering, a flickering pixel or a wrong color? It's not thought about. Now, it's great to have a conference where we can talk about differential reference counting and logging, real-time logging, but I think that computers should handle that stuff for us. I spent 10 years thinking about how humans can tell computers how to make sound, and I'm not alone. A lot of the people who work with JUCE and all these other frameworks, they all think about this. How can we tell computers what we want to do with sound? And Jules has done this like 3 times now with JUCE, Sol, and C major. And that's over the last 10, 15 years. But now in a short time, AI has learned how to understand human communication with a great deal of subtlety. I'll even say that computers have to do a better job of understanding us than we have of actually understanding even a reasonably sized program of any kind of complexity. Like human minds don't read programs very well. We don't know all the things that could happen. And I'm not the only one saying this. I saw a Lex Fridman podcast with Stephen Wolfram, and he was saying the same thing. So computers are doing a better job of speaking to us than we've been doing to speaking to them. So I'm almost ready to bet that none of the current ways we're doing things are going to outperform just writing down in plain language what kind of audio processing you'd like and have AI give you a few options. This is what some people are calling like prompt engineering, but I don't think that's giving it enough credit. I think that the value we provide as humans is not to sift through the details, but be creative and describe what we need in our own natural language. Thank you. Any questions? We have all night. So anybody wants to ask anything? TJ.
What value do you think there is, if any, in humans understanding something lower level than ChatGPT, plain language, in terms of expression, and how it informs the art?
I think that there will always be a reason for people to be pushing boundaries and stuff. But I'm hoping that more and more of those details are going to be taken care of. We do want to be on the cutting edge, and that's how we make profit sometimes, by being slightly faster or slightly better than the next guy. So it's not coming like immediately that we won't have any use for us. But on the other hand, I don't think that we're going to outperform AI in actually understanding how computers work at a very deep level. Maybe in 5 years. Invite me back in 5 years, ADC, and we'll see.
We probably have somewhat similar backgrounds coming to audio, like initially not knowing what to do and learning about it as you go. By that I mean not having computer science degree, speaking for myself.
Me too.
But I have to disagree with you in letting computer handle all the low-level stuff. I've recently been following Casey Muratori videos that talks about CMD and just intrinsics and really, really nerdy stuff. And it makes sense to understand that for a developer, although you might not, same thing with DSP, although you might not even write FFT, why would you? It's been done. But understanding those principles and just forcing your brain to get there is essential, in my opinion. If we don't do that, then we're going to end up with relying on hardware like we do right now to handle all the things and having overly convoluted code. That's just my perspective.
Well, I would say there's a difference between understanding some fundamental concepts. I have spent so much time on the DFT books of yours, maybe days or maybe weeks of time, just really understanding concepts that are important, that are actually fundamental concepts. But low-level details, I don't know that we will be better than a computer can be at thinking that stuff. And I welcome. I don't know, but this is how I feel, and this is what I'm willing to put on video for now. Yeah.
Yeah, quick question. So I've noticed the performance was better on a functional programming language. Do you think that has something to do with the level of abstraction and the greater amount of guarantees guaranteed by static analysis?
I don't know. I was actually surprised. AudioKit has a very Englishy philosophy. We don't say OSC, we say oscillator. We try to make all the words explicit. And ChatGPT didn't seem to care much about that. It wasn't so much that it was a human language as it was a consistent language. And I only listed Faust as moderate reliability for ChatGPT because it still sometimes chose kind of hokey versions of functionality. It got it right once. So I would like to believe that functional programming is somehow better because I think it's elegant, but I don't know that for a fact.
I'm curious, did you ask ChatGPT to fix that bug in C-Sound for you?
No, I don't even remember what that bug was. That was so long ago. Yeah.
Thank you. Great talk, by the way.
Thank you.
Hey. What are your thoughts on, because I feel a lot of satisfaction in actually building that thing. Do you feel that there's something lost in the creativity process through just telling the prompt to create something for you?
You know, I spent 10 years doing this. For me to say that I don't think that frameworks are a worthwhile thing is kills me inside, right? I would like to believe that all our work is valuable, but I see the speed of how well it understands us compared to how well we've been able to describe to it what to do. It just doesn't compare. Like, maybe right now we're still feeling we can tell it how to make audio better than it can figure out from our words, but I don't think that will last. I think we're going to be outperformed. We'll see.
I have some similar experience with you with the prompting. If it's something that I know about and I could be more specific, and I have some special knowledge, then it's going to do a much better job. To the point what the last guy was saying is you're missing something. It's like, you can try to talk to ChatGPT, and you're going to find out where your knowledge breaks down, where you just don't know what you're talking about. I mean, right now, if I wanted to write a function that I think would take me, an hour to figure out, I'll spend 15 minutes writing up some pseudocode for it, and it'll get pretty close.
Yeah.
So you don't have to feel guilty about it, and and if it can do something you didn't think that you were capable of, well then you just got lucky. We got a limited amount of time on this planet. There's more fun things to do, for Christ's sakes.
And by the way, to your point, when you're fixing its output, it's not losing that data.
Right.
It's going to remember that it gave somebody a solution to that, and they tweaked it to this better. So we should be talking to our AIs and
we should. Don't be afraid of it.
I mean, it may destroy the world, but in the meantime, we'll do some cool audio things.
Last one.
Hi, Aurelius. Thank you.
Sure.
So I'm on board with this idea. I don't want to worry about real-time stuff, and I do think that these computers should take care of that. But I hope I'm echoing a lot of other people's thoughts that there's a feedback loop because it has learned because ChatGPT has learned these things because someone wrote a bad example and posted it in Stack Overflow 10 years ago, and we can't stop doing that. So there is still a feedback. So we still, I guess, continue writing examples, because how will we train future?
Well, we are training when we're telling it didn't do a good job. That's part of the training process. But I definitely think we should be blogging more as audio developers. We should be explaining things multiple times. I guess multiple languages doesn't matter that much anymore, but certainly different people have different takes on how to explain how they did something in a variety of frameworks can only help everybody.
To follow up on that, it seems like its understanding of these frameworks are based on good documentation and good code examples that exist online. And I was wondering, kind of based on what Julius was showing, the block diagram of Faust itself, I wonder if there's a higher level sort of language it could understand to learn some of these lower level processes, like train it on your entire website.
Yeah, your guess is as good as mine. I have a feeling that AI is going to be better at doing low-level stuff. Other people disagree. Is that it? All right.
All right. So, how did it go? Was it a good day? Love to hear that. It's inspiring. I have a few thank yous and I'll maybe a couple Q&As if you want to ask. Big thank you to all the speakers and to everyone who proposed talks. I wish we could have programmed them all, but it just inspires us to do a bigger event next time, maybe with multiple tracks. There's clearly enough folks that want to give these kind of talks, and we should do it again. It's great. I want to do a really big shout out to the Commonwealth Club. It's a beautiful building. They were great in making this happen. I want to say thank you to Mark, who inspired me to bring this here. So that Mark has been running AV in the back, and Mark's team has just been incredible to work with. They've been handling all the live stream today that's been going on, as well as the recording of the talks. The live stream can be watched right away, but we will go back and make sure that we process all the talks so that they're up in high resolution and the slides are all made available. We'll try to get that done as soon as possible. And then very important, I wanted to shout out, thank you to the sponsors. So what happened was at ADC 22 last year in London, we did a really great sponsorship drive, and we did have some money left over after ADC 22 London. And we committed to all the sponsors that we would use the leftover money for something important. And Andrew, maybe say some words about that. What are we doing?
Yeah, I mean, we had talked about doing a pop-up. We had people saying LA. There's a very strong interest. I'm with Pace. We're the current stewards of both owners, but I consider it stewardship of both JUCE and thus the ADC. And there had been talk about doing an ADC in Tokyo, and so there's still some interest there, but cost and a lot of things. But I was over there a couple months ago speaking with some of the JUCE users, and there's a high interest. There's just we've got to find a way to put it together. Money's tight and it's hard, but these sponsors really stepped up at the end, right before the November event last year in London, and we had a little bit of leftover money. We run a really tight budget, despite appearances and all the art and everything that looks very professional, thanks to Ralph and other people on our team. But when I am here today, you've just like lifted me up. I'm ready to, go get sponsor money for the event in November. It's to see what we can do for the community. I service many people in pro audio through my core business, which is Pace Anti-Piracy, and if you know iLock, that's us. And so, and I've seen many of those customers become sponsors and really step up. So there's more and more interest now, and when they see the kind of talks and the community, it just feeds itself. So we want to continue doing that. So anybody who has time, money, any ideas, we've talked about doing single-day pop-ups at universities and other places, meetups, just anything to get more people involved. And so we're going to continue to do the best we can to support that.
Absolutely. I also want to say a shout out to Sophie. So you saw Sophie running around with the Q&A mic. But believe me when I say these events are not possible without Sophie. These lovely catering selections to running a tight ship on, making sure the talks happen on time, and Bobby, get off the mic, that kind of thing. But she's amazing. Also, the JUCE team, incredible. Tom Poole, who really helped me with curating the talk schedule for this event, and many other things like the tech stack behind the Zoom events that also was the back end for doing registration. Lots going on there. I think we're committed to doing more of these, and certainly coming back to San Francisco. I look forward to it. The good news is we're done. Upstairs, there's a lovely reception set up for you. We got some live music, we got some drinks, we got some snacks. Hopefully the fog has stayed away, and let the networking continue. That's what it's all about. So thank you for being here.
Thank you all for coming.